Hey guys, in this video the lovely Mr. B is going to take you through all the skills and techniques that you need for your CCEA GCSE in further maths. Now to go with this video there's a checklist that you can download for free and you can just tick off the bits when you know them, identify any gaps when you don't know, and then if you do find any gaps, go and look at the specific video and Mr. B will take you through 9 examples at 3 different levels of each of the skills. If you then want to practice that skill even more, over my website there is the huge course covering everything that you need to know, tracking your progress as you go along, and then if you want to go old school and write on paper, there's the workbooks for you as well.
The subject of a formula uses the same principles as solving equations. So let's say we have y is equal to 11x minus 4. If we were solving the equation, what we would do is try and get x on its own, and we would add 4 to both sides. And that's what we do. And that gives us y plus 4 is equal to 11x. Now, when you're solving an equation, in the position of a y, you would typically have a number that you can add 4 onto. Now, in this situation, we've got a y there, so we can't add 4 onto it. So just leave it as y plus 4. When we now do the next step, and we need to divide both sides by 11 to get x on its own on the right-hand side, again, typically the y plus 4 position would have a number that we can divide by 11. In this case, we don't have that. So how can we do it? Well, all you do is you write down y plus 4 again, and then you make it into a fraction with 11 as the denominator. And what this does is it shows that you're attempting to divide by 11, but at this time you are unable to divide by 11 because you don't have a value for y. And so this is the essence of how you change the subject, because now we have an x equals, and now we have a formula to find x, whereas we started off with just a formula to find y. So let's have x take away 9, and all of that is going to be squared, and it's equal to y. So again, we want to get x on its own. So we have to kind of unwrap the layers of mathematics around x to get it on its own. Outermost layer is the squared symbol, so we need to root both sides. That will leave us with x minus 9 on the left-hand side, and then we're going to have to square root the y. Once we've done that, we can add 9 to both sides, and we get x is equal to the square root of y plus 9. And again, typically here, y would be a number that you can square root. And then that'll give you a number that you can add 9 to and get a value for x. But when we change the subject, our answer is going to be another formula. So we started off with a formula to find y, and now we have a formula to find x. Let's look at something with a few more steps. So we've got 5x plus 2y, all divided by 5, is equal to 7. So again, we want to get x on its own, and we have to kind of unwrap all the layers around it, the outermost layer being the divide by 5. So we multiply both sides by 5, and that moves the 5 over to the right-hand side. 7 times 5 is 35. So in this case, there is actually some maths we can do. We can do 7 times 5. So it's not always going to be maths that you can't do. Next, we can take 2y away from both sides. And finally, we want to divide through by 5. Now, x is equal to, and then we're going to have 35 minus 2y, and we're dividing all of that by 5. And note that I said we're dividing it by 5, but I haven't actually divided it by 5. Because while we could divide the 35 by 5 and get 7, we can't divide the 2 by 5. You could actually do something here. So we could do 35 divided by 5 is 7. Then we could do 2 divided by 5 is 2/5. So actually, this could actually be a simpler form. So both of these outcomes are fine. It's just depending on if you want, a large division, a large fraction, or if you want a smaller fraction involved in this. And again, note with the 2 divided by 5, I couldn't do 2 divided by 5, so I just wrote it as a fraction. I'm indicating that I want to do 2 divided by 5, but I can't at this time. Let's look at one last example. So we're going to have 10 plus 14x all over xy, and that's equal to 7. So this question, the change here is that sometimes you are going to get multiple sets of the thing you change the subject to. Unwrap some layers here. So let's multiply both sides by xy, and that will give us 10y plus 14x is equal to 7 times xy. And our aim here, now we've undone the fraction, we want to get x on its own. We have 2 sets of x's. So we need to get the x's onto the same side. So what we could do is we could take away the 14x from both sides, and that will give us 10y is equal to 7xy take away 14x. And once you've got all the x's to the same side, what you want to do now is factorize both x terms to get a single x. So both of the terms with an x in, they've both got an x, but they've also both got a 7, because we've got 7x and we've got a 14x. So we've got a number factor as well. So we take 7x outside of brackets, then we divide through by 7x. 7xy divided by 7x will leave us with just y. And 14x divided by 7x, 14 divided by 7 is 2, and x divided by x means we're multiplying by 1. And so there's our next line. So by factorising, we now only have 1x. What we can do now is we can divide both sides by the bracket, and that will mean that the bracket is going to be dividing the 10y now, and that's going to be equal to 7x. Now, at this point, what we also want to do is get rid of the 7 on the x, and we'll be dividing that as well. So we've already divided, and we've got another divide to do. All we need to do is add the 7 to the denominator as well. So the 7's going to join the denominator. It's going to be multiplying the things that are already there. And there's our answer. The last thing you might want to do, you could expand the brackets if you prefer to. That's something you could do. So we could have 10y over 7 times y, and 7 times negative 2 is equal to x. So there we have 3 examples of taking the subject. And again, it's exactly the same as solving an equation. It's just sometimes you won't actually be able to simplify it at various points. And so you'll leave divisions as fractions, for example. With expanded brackets, you should already be familiar with the basics of this. So for example, if you have a number and a bracket, then inside the bracket, by the number on the outside, like so. Remember to multiply both of the things inside the bracket. A common mistake is not multiplying both. You have the same thing with letters on the outside of brackets. X times x is x squared, and x times 4 is 4x. So we did 2 multiplications. Or you could have a mix of the two. So 3x times x is 3x squared. The numbers and letters separately. X times x is x squared. 3 times 1x, 3 times 1 is 3. And then 3x times 4, 3 times 4 is 12. And then we've got an x. So this is the basics. You may also be familiar with double brackets. And with double brackets, you're going to have an x in both. You're going to have some kind of expression in each one. And then you have to multiply everything by everything else. So we're going to multiply the x by x to give x squared. We're going to multiply the x by 3 to give 3x. We're going to multiply the 4 by x to give 4x, the 4 by 3 to give 12. We can combine the middle terms because they've both got an x on them. 3x plus 4x is 7x. So altogether, we have x squared plus 7x plus 12. So this is the basics of expanding brackets. You should already be familiar with. Now, this isn't what we're going to be revising here. What we're going to be revising is ways to expand triple brackets and even beyond triple brackets. So let's have a look at the methods. So let's look at a question. So let's say we've got 2x plus 3, x plus 2, and x minus 4. And we want to expand the triple brackets. Now, the first method is to split it up into 2 sections and do 2 double bracket questions. So we are going to, for now, only look at the first 2. I'm going to ignore the third bracket for now. So just doing the green section, we're going to have 2x times x is 2x squared. 2x times 2 is 4x. 3 times x is 3x. And 3 times 2 is 6. You lose track of that. Again, just use the arrows to remind you of the 4 multiplications you need to do to expand double brackets. And then with our answer, we can combine the middle 2 terms. So we have 2x squared plus 7x plus 6. So once we have found that answer, then, and only then, do we then include the extra bracket. So we had an x minus 4 bracket, and now we're going to write that in. And the answer we just found, we can put that into brackets, and now we've got another double bracket question. So then we do 2x squared times x, which will be 2x cubed. 2x squared times the negative 4. So 2 times 4 is 8, so that'll be a negative 8x squared. And now we've done the first term. Then we move on to the second term, the 7x, and do the same thing with that. So we're going to do 7x times x, which is going to give us 7x squared, and 7x times negative 4. So 7 times 4 is 28, so that'll be negative 28x. Then we do it with the third term, x times 6 is 6x. And then 6 times negative 4 is going to be negative 24. And what we want to do now is combine all of the terms together. So looking at the cubed section, we've got 2x cubed. Looking at the squared section, we've got a negative 8 and a positive 7. So that'll cancel out to a negative 1. Then look at the x section, we've got negative 28 and a positive 6. That'll be negative 22x. And then we've got the negative 24 at the end. So we'll just combine up all the terms and we get our final answer. And so this is what I would call the manual method, where you expand the brackets one at a time, each time adding on another bracket. And let's say we had 4 brackets here. Then we'll take our final answer. We multiply all 4 terms by the 2 terms in our new bracket and continue the process. But as you can imagine, doing that is going to lead to a lot of maths, a lot of simplification. So is there a faster way? So what we're going to look at next are kind of general cases of expanding brackets. So let's say that we have x plus y in a bracket and it's squared. That's going to give us x squared plus xy plus y squared. And you can try explaining that yourself and see if you get the same thing. Now, what if we have x plus y cubed? That's going to give us x cubed plus 3x squared y plus 3y squared x plus y cubed. Again, you can try expanding that and you'll see that this is the case. So what if we had x plus y to the power of 4? What would that give us? Well, the key here is knowing the coefficients on the numbers. So, for example, the 3's on the xy's, and knowing the powers. For example, we've got the power 3, the power 2, then the power 2 again, and then power 3 again. So here's how it works. The first thing to talk about is a little pattern called Pascal's triangle. Now, the way Pascal's triangle works is that you start at the top with 1. The next row is 1 and 1. The next row is 1 and 2 and 1. And what happens with each row is you put a 1 further out at the edge. The next number is the 2 above it added together. 1 plus 2 is 3. 2 plus 1 is 3. Then you finish off with a brand new 1 at the end of the row. So the next row, come out a little bit with a 1. Then we have 1 plus 3 is 4. 3 plus 3 is 6. And 3 plus 1 is 4. And then we have the 1 at the end. And you can see this triangle is symmetrical. Now, how does this relate to what we're doing? Well, each row of the triangle corresponds to the coefficients on the numbers. So, for example, if we look at the row 1, 3, 3, 1, that corresponds to the cubic row, where we have a 1x cubed, then a 3xy, a 3xy, and then a 1y cubed at the end. So 1, 3, 3, 1. I also know that I've made a mistake on expanding my quadratic because it should be 1, 2, 1, and I've got 1, 1, 1. So actually the xy, that should have been 2xy. So how can we use this for the fourth row, where we have x plus y to the power of 4? So we're starting off with 1, 4, 6, 4, 1. So we're going to have a 1x, then we're going to have a 4xy, we're going to have a 6xy, another 4xy, and then we'll finish off with a 1y. So that's the coefficients on each term: a 1, a 4, a 6, a 4, and a 1. The next thing is the powers. So you start off with one side, just one letter to the power of 4. So x to the power of 4 on the left-hand side. On the right-hand side, we're going to have y to the power of 4. And what happens is, each time you move along, the letter's going to lose or gain a power. So, for example, the x's, starting on the left, we've got 4, 3, 2, and then 1x. And at the end, we have 0 x's, which is where we have y to the power of 4. Y goes the opposite way. So from the right, we have y to the power of 4, to the power of 3, to the power of 2, to the power of 1. And then on the left-hand side, there's y to the power of 0, so we don't write it in, so we only have x to the power of 4. So there's 2 features we need to take into account: the coefficients on each term and the powers on each term. The coefficients come from Pascal's triangle, and the powers go down from one side to the other for one letter, and then up from one side to the other for the other letter. So let's do one more. And I need a bit more space for this. Let's do x plus y to the power of 5. So firstly, look at Pascal's triangle. Start a new row. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And finish off with a 1. So we know we're going to have 6 terms with these coefficients. We're not going to start off with just x, that's going to be x to the power of 5. We're going to add it on to that. We're going to have a coefficient of 5 with our x and y, a 10 with our x and y, another 10 with our x and y, then going down to a 5 with our x and y, and then finishing off with just y, and that y will be to the power of 5. So we've set up the terms and the coefficients. Now we do the powers. So the x's are going to go down, so 5, 4, 3, 2, and then a 1x, and then a 0x, we don't write x at all. Y is going to go up as we go along. So the 0, 1, 2, 3, 4, and then 5 at the end. So that's all well and good, but how do we use this to answer a question? So let's have a look at an example. So we're going to do 2x plus 3 to the power of 3. I'm going to use this method. Now, the first thing to do is identify what x and y are going to be from our formula. So from our formula, x is going to correspond to the first term, which is 2x, and the y corresponds to the second term, which is 3. And just keep in mind that the x that we're kind of using for the formula is different to the x that's in the question. Let's make it clear that this is not part of the question. So we write out our sectional formula. So x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And all we're going to do is substitute. Anywhere we see an x, we're going to substitute in 2x. Anywhere where we see a y, we're going to substitute in a 3. Let's just do some colour coding here. So we'll do the x's in green and we'll do the y's in pink. And just go through the formula systematic way. So x cubed will become 2x cubed. Then we're going to add on 3 lots of x squared y. X squared will be 2x squared and y will be 3. Notice how the things I'm substituting I'm going to put in brackets. I'll make things easier in a moment. Then we're adding on 3 lots of x y squared. X was 2x and y was 3. So that'll be 3 squared. And finally, we're adding on y cubed. So y was 3 and we are cubing that. So now let's expand all the brackets and see what we've got. So our first term, 2x, and it's all cubed. That means we're going to cube the 2 and the x. So 2 cubed is 8, so that will give us 8x cubed. Then we're going to add to that 3 times 2x cubed times 3. So the thing to do here is look at the numbers first. We've got a 3, we've got a 2, and we've got a 3. Well, if we multiply those numbers together, just be aware that the 2 is inside some brackets and it's being squared. So actually that's going to be a 4. So we're going to do 3 times 2 squared, which is 4, and then times the 3. And altogether, that gives us 36. So we looked at the numbers. Then look at the letters. We've only got an x, and it's x squared in there. Then move on to the next term. Now, again, we're going to have 3 things to multiply together. We've got a 3, the 2, and then we've got a 3. Again, with that 3, it's being squared. It's actually going to be a 9. So we're going to do 3 times the 2 times the 3 squared, which was 9. And altogether, that gives us 54. Then you look at the letters, and we've got a 1x in there. Then for the final bit, we've got 3 cubed, which is 27. 3 times 3 times 3. And so now we've expanded our cubic. Now compare the lengths of these methods. So our first method took half the page. There was a lot of calculations. It was essentially 2 questions in one because we multiplied out a quadratic and then multiplied out a third bracket to make it a cubic. With the method that we've just done, it's only taken really 3 lines of working out, so it's a lot shorter. The thing with this is, though, with the original method, you don't need any special knowledge to do it. You're just kind of brute forcing it by multiplying everything out. With the method we've just done, you need to know the kind of general method of it, where it's x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And if you haven't memorized that, then you need to sketch out Pascal's triangle, for example. But I think even if you go sketch out the first couple of rows of Pascal's triangle, it's still not going to be as much working out as the first method. The last thing to mention is that while the method we've just done is shorter, it's a little bit more limited in that all 3 brackets had to be the same. We had 3 brackets and they were all 2x plus 3. Now, with our original method, all 3 brackets were different. And so if you do have 3 different brackets, then you need to use the first method. But what you'll tend to find is, particularly when you've got brackets to the power 4, to the power 5, to the power 6, you'll always be given the same numbers in every single bracket, and it'll be written out as a single bracket with a power instead. So you just need to be aware of the positives and negatives of both methods. With factorisation, you should be familiar with kind of single bracket factorisation. We might have something like 4x plus 20. And when you factorise it, you think about what the highest common factor of the two numbers are. So we've got 4 and 20. And so the highest common factor of those is going to be the 4. And you remove that outside of a single bracket. Inside the bracket is going to be the result of dividing your expression by 4. So 4x divided by 4 is 1x, and 20 divided by 4 is 5. This is something that you should already be confident with. What we're going to focus on with this bit of revision is quadratic factorisation. So you might have something like x squared plus 9x plus 18, and be asked to factorise it into a set of brackets. So how would you do that? Well, the key thing is that you want two numbers inside these brackets that add together to make the 9, and they multiply together to make the 18. Now, you might be able to figure that out just by looking at it, but there's a method if you can't. So what you do is you take the 18, the number you need to multiply for, and you list all the possible options of numbers that multiply together to make 18. So you can have 1 times 18, 2 times 9, 3 times 6. We can't divide it by 4 or 5. We can divide it by 6, so we finished our list. So note how I did that. I divided it by 1, wrote down the answer. Divided by 2, wrote down the answer. Divided by 3, wrote out the answer. Tried 4 and 5, they didn't work. And then when I repeated myself with 6, I knew that the list was complete. So what we need to do now is think, well, which ones of those numbers are going to add together to give 9? You have a look through, you'll see that 3 and 6 make 9. So what do you write in the brackets? Well, we need an x in both, because we need to have x times x is x squared. Then we're simply going to write in the 3 and the 6 in either order, it doesn't matter, and they were being added on. They're positive numbers, so we're going to write an add symbol. And that's it, we've factorised the quadratic. So let's look at some harder ones. Next, we're going to look at x squared plus 4x, take away 32. So we're going to have some negative numbers here as well. Now, we still want two numbers which add together to make 4 and multiply together to make 32. So you write a list of factors with 32. You can divide it by 1. We can divide it by 2. We can't divide by 3. We can divide by 4. We can't divide by 5 or 6 or 7. And we can divide it by 8. We've already got 8 written down, so we must have finished our list. So we look through the list and we think, right, which of these numbers add together to make 4? And at first glance, none of them will add together to make 4. So we know we write the x and the x in the brackets. What else do we write in? Well, because the multiplication is a negative, it's a negative 32, we are allowed to use negative numbers. So when you look through the list, you think, well, if I'm allowed to take away, how could I get a 4? So 1 and 32, you could get, you could get 33, you could get 31, you could get, negative 31 or 33, depending on these negatives or not. So that's not going to help us. We can eliminate that one. 2 and 16, we can add them to get 18. We could take them away to get a 14. That's not going to help us. And 4 and 8, we can add them for 12. We take them away. 4 take away 8 is negative 4. Well, this looks promising. What about the other way around? 8 take away 4 is 4. And so we found our answer. So we write in the 4 and the 8. Again, in either order. It doesn't matter which way around they are. What does matter is the way around the negative numbers are. And you think very carefully about how you got a positive 4. And it'd have to be a positive 8 and a negative 4. 8 take away 4 is 4. So in the brackets, we need a positive 8 and a negative 4. So always be looking out for negative numbers as well, if you can see it in the question. And be thinking about takeaways. When we talk about, two numbers that add together to make the middle term, we are allowed to take them away as well, or have any kind of combination of negative numbers that you need. Lastly, we'll look at two special cases. So what if we had x squared take away 9? So you're thinking, I need two numbers, that multiply together, or two numbers that, multiply. When you look at this, there's only one number. So, is this going to be an adding or a multiplication number? So if you look back at the previous questions, the numbers you have to add always have an x on. And the numbers that you have to multiply are just numbers. So it's going to be two numbers that multiply together to make 9. But what about the addition bit? Now, it is actually there and it's hidden. So x squared minus 9 is the same as saying x squared plus 0x minus 9. And so you want two numbers that multiply together to make -9, but they add together to give 0. That's what it means. So when you have your double brackets, there's only going to be one option for something like this. And it's going to have to be the same number twice. So to get 9, what's the same number twice that gets 9? That's going to be 3 and 3. So it's a square number, and there's a missing term. Just kind of square root it. And it's going to have to be a +3 and a -3. And then what's going to happen is, when you add those two numbers together, 3 and a -3 will make the 0 for you. One other special case is, rather than having the addition part missing, the x term missing, you might have the multiplication term missing. So you might have something like x squared minus x. Now, in that situation, this isn't going to be a quadratic because you want two numbers that multiply together to make 0. So what that means is one of the brackets is going to be a 0. So when you have your double brackets, it's going to act like a linear kind of factorization. So you see you've got an x in both. So we take out the x, and then we divide both by x. So x squared divided by x is x. Negative x divided by x is going to be -1. And that's going to be our answer. Again, coming back to, want two numbers that multiply together to make 0 and add together to make -x, -1. One of the brackets is missing. The x on the outside doesn't have a number with it, and that's how you get the 0, because effectively it's x plus 0. However, rather than overthinking it, just treat questions like this with a missing number on the end as a linear factorization. Now, the next stage of difficulty after this is something like 4x squared minus 18x plus 14. And with this one, when you open up your double brackets, before we were writing x and x, because x times x gives us our x squared. However, with this question, it's not an x squared, it's a 4x squared. So you could have 4x times x, or you could have 2x times 2x. So it's going to be one of these two alternatives, and you don't know which one it's going to be. So that's the first difficulty. The second difficulty is when we look at our factors for two numbers that multiply together to make 14. So look at the factor list for 14. We can divide it by 1, and we can divide it by 2, and we can't divide it by 3, 4, 5, or 6. So these are the only possible factors. Now, we need to add or subtract these to get a -18. And these numbers are all too small. You are not going to be able to get a -18 out of these numbers. So what on earth do you do? Well, you are allowed to multiply by the coefficients on the x. Because when you expand the brackets, these numbers are going to get involved. So if it's the first alternative and it's 4x times x, you can multiply one of the numbers by 4, and you can multiply one of the numbers by 1. And this will give us a fresh list of alternatives. So we could have 4 and 14 if we multiply the first number by 4 and the second number by 1. Or we could have 1 and then 14 times 4, which is 56. Same thing with the 2 and the 7. We could multiply the 2 by 4 to get 8 and the 7 by 1. Or we could multiply the 2 by 1 and the 7 by 4 to get 28. So we've got a larger list of possibilities. So this is our 4 and 1 list. Let's just box it off. Let's make a list for 2 and 2. So we can multiply the 1 by 2 and the 14 by 2. Or we could multiply the 2 by 2 and the 7 by 2. And since they're both the same, you can't do it the opposite way around because it'll just give you the same answer. So we've only got two alternatives for the 2 and 2 option. So what we need to do now is look through this list and think, well, which ones of these could make 18? So 4 and 14 can. 8 and 7 are going to make 15 together. That's not going to work. 1 and 56, that's way too big. 2 and 28, I mean, we could take away the 2 to get 26, but that's still too big. 2 and 28, we do a take away, we get 26, that's too big. And 4 and 14, again, from a different method, that could also give us the 18. So now we're going to think about which one it's going to be. Now, we want to add them together to get a -18. So it'd have to be a -14 and a -4 in both cases. Now, we write these into the brackets. We don't write the 4 and 14. We write the original numbers they came from. So it's going to be the 1 and the 14. You're going to think really carefully about which way around they are. Now, the 14 stayed as it is. So that's going to go in the bracket with the 4. And the 4, the 1 was multiplied by 4 to get 4. So the 1's going to be in the opposite bracket to the 4. Because when you multiply this out, to get that 1 multiplied by 4, it can't be in the same bracket as it. So we've got that the correct way around. And then, of course, in the second alternative, because they're both being multiplied by 2, it doesn't matter which way around they're going to be. Now, the second alternative is multiplied from the 2 and the 7, multiplying them both by 2. So we're going to have the 2 and the 7 in for that alternative. So now we're going to think, well, how do we get a negative 18? Well, they've both got to be negative. And so now we've got 2 possible answers. It's actually quite unusual to get 2 possible answers. But there we are, we've got 2 alternatives. There's 2 different ways to factorize it. And whichever one you use depends on what's going to happen next. If the question is just to factorize, either one will be a correct answer and you'll get full marks. If you need to do something else afterwards, then there'll be some kind of clue as to which of these 2 is going to be the most relevant. Which brings us on to the next thing we'll look at. So you could get something like this. You can have x squared plus x minus 20 all over x minus 4. Now, in a question like this, what you're going to do is factorize what you can. And you can factorize the quadratic on the top row. Now, I'm not going to go through this in detail because we've already revised that. So the answer to the factorization is going to be x plus 5 and x minus 4. And what you'll notice is that one of the factors is the same as the denominator of the fraction. So all you need to do is divide them by each other. If you divide a number by itself, you get 1. And if you multiply by 1, the answer stays the same. So effectively, by factorizing, we can actually cancel down the fraction, and the answer is x plus 5. Now, we can also do this with more complicated ones. So let's say we had 10x plus 15 all over 8x squared plus 4x minus 12. Now, normally, if we were going to do what we did with the 4x squared question earlier on, how many alternatives are there for 8x squared? We could have 8 times 1, you could have 4 times 2. You know, there's a few different options there, and you're going to get like a long list of possibilities potentially. But there's a clue in the question because it's a fraction. You know that it's probably going to end up being cancelled down. Now, on the numerator, we've got 10x plus 15. Now, if we have 10x in a bracket, that's not going to multiply by anything to get 8x squared. But you can factorize it as a linear factorization. And the 10 and the 15 have got a common factor of 5. So you could write 5 and then 2x plus 3 in the brackets. Now, this is a clue that one of the factors is going to be 2x plus 3. And this is going to shorten down the list of possibilities that you have for this question because you know you want to get a 2x plus 3. So we want to get a negative 12, for example, at the end by multiplying together the 2 numbers. So the only way to get a negative 12 is for the other factor to be negative 4. And then with the x's, we want to get 8x squared. We're going to multiply 2x by something to get 8x. So it must be a 4x. And what we can do is we can test it out and make sure it works. So maybe you can multiply it out to check. 4x times 2x is 8x squared. Negative 4 times 3 is a negative 12. 4x times 3 will give us 12x. And negative 4 times 2 will be negative 8. So 12 and negative 8 will give us that positive 4 in the middle. Looks like it works. So now all we need to do is divide the same factors by each other and cancel them out. What we're left by is 5 over 4x minus 4. And that's your final answer. And so you can see by having that clue in the question, it's a fraction, we're probably going to be simplifying the fraction. We could guess what one of the factors were going to be, and it shortened the calculation down for us to the point where we could do it in our head quite easily. Algebraic long division is all about factorizing things that are larger than quadratic. So, for example, a cubic. So you might be given something like factorize, and you'd be given a cubic. So let's say x cubed minus 5x squared plus 8x minus 4. And you might be given a clue. So you might be told that one of the factors exists. So, for example, that x minus 1 is a factor. Alternatively, rather than full factorization, you might be asked to show that x minus 1 is a factor, but it's going to be the same maths. So what we do to solve this is do something called algebraic long division. So we set up a division. Now, with this division, we're going to have x minus 1 as a thing we're dividing by. And the thing that we're dividing is going to be the x cubed minus 5x squared plus 8x minus 4. You might be thinking, well, this looks horrific. You know, how on earth are we going to divide these? And we use a little bit of a trial and error, and we go step by step. Now, what we're going to do is we're going to focus on dividing by just the x, and we'll deal with the minus 1 after we've attempted dividing by x. So we're going to go through one term at a time. We're going to start off with the x cubed. We're going to divide x cubed by x, which gives us x squared. We're writing x squared. We're not going to write it in the first spot above the cube section. We're going to write it in the squared section. So our answer is going to go here. Now, once you have done that, what you need to do is then check that this is actually the right answer, because we didn't divide by x. We should have been divided by x minus 1. So we kind of have to work backwards now and make sure we've done this correct. So we take our answer, I'm going to multiply it by the term at the start. So we're going to do x squared times x is x cubed. And we're going to do x squared times negative 1, which will be negative 1x squared. If we've got x squared as our answer, the part of the calculation we've dealt with is x cubed minus x squared. But there's still a lot of the calculation left to go. So what we do now is we work out how much of the calculation is left. And the way we do that is we are going to take the parts away. So we're going to do x cubed take away x cubed 0. Then negative 5x squared take away a negative x squared, double negative there, so it'll be an add. Negative 5 plus a 1 will give us negative 4. It'll be negative 4x squared. And then there's nothing to take away for the next two sections. They stay as they are. So this is the part that we've got left. And now all we do is we repeat the process. We're going to divide by just the x. So our next term is negative 4x squared. We're going to divide it by x, and that gives us negative 4x. We'll write that down in our answer. And then we're going to check that we've done it correctly. So we're going to bring that forward. I'm going to multiply it by the thing we're dividing by. So we're going to do negative 4x times x, which is negative 4x squared. And then negative 4x times negative 1, which will be a positive 4x. And then we check how much of the equation's left over by taking away. So negative 4x squared, take away negative 4x squared, will cancel it to give you 0. 8x take away 4x is 4x. And there's nothing else to take away, so the minus 4 will stay as it is. And then we'll repeat the process again. So now we've got a 4x left over at the start. We divide that by x, and that gives us 4. So we write in 4. We bring that back to the front, and 4 times negative 1 is negative 4. We then check how much we've got left by taking them away, and you can see now that we're going to have 0 left over. So we have finished. And if you have 0, that proves that it's a factor. There's no remainder. We've completed it. If you got an answer that wasn't 0, that would be a remainder. And it means that what you have isn't going to be a factor. So now it's proven that x minus 1 is a factor. How do we factorize this? Well, we know that x minus 1 is a factor. And we know the answer to our division is a factor as well. So that's going to be x squared minus 4x plus 4. We know that that's also going to be a factor. So all you have to do now is take quadratic and factorize the quadratic as well. So you can do that using any method you like, but if you factorize the quadratic, which is something you should be more comfortable with, that should be x minus 2 in both. And now we've got our full factorization. So not only does the algebraic long division prove that something's a factor by having a remainder of 0, but it also will give you, for a cubic, it will give you a quadratic that you can then factorize for the rest of the factors. So now let's have a look at another example. So let's say we need to factorize x cubed, take away 5x squared, plus 3x, plus 9. And this time we are not going to be given a clue. So how can we factorize it? Well, a good thing to look at first is to think about the number at the end. We've got a 9 at the end, and it's cubic, so we're going to have 3 brackets. So we're going to think, well, which 3 numbers are going to multiply together to make the 9? And you don't have a lot of options, really, for some numbers. So for the 9, you could have 3 times 3 times 1, for example. Now, that's not the full story, because we know we have a negative number in this, and we're factorizing it. We're going to be getting a negative 5x squared. So some of these need to be negative. Now, given that 9 is a positive number, 2 of them are going to have to be negative. So then that gives us a lot more options. We can have negative 3 times negative 3 times 1. Or we could have 3 times negative 3 times negative 1, for example. So here are a few different alternatives. And, no matter which one you choose, you could be wrong. So if you can't figure out exactly which one's going to be correct using logic, you're just going to have to give something a go. So I'm going to have a go, and I'm going to use x being equal to 3. So we're going to set up another algebraic long division. We're going to divide through by x plus 3. I'm going to divide through the full number. So like we did with the previous question, we're going to divide through by just the number at the start, which is the x. Let's free up a little bit of space here. So we've an educated guess. I'm going to guess that x plus 3 will be a factor. Let's check to see if it is. So take your first term, which is x cubed, and divide it by x. That gives us x squared. So we can write x squared in as the first part of our answer. But then we didn't take into account the plus 3, so we're going to bring that back to the start and check the plus 3. So we do x squared times x is x cubed, and x squared times 3, which will give us 3x squared. So we've not just dealt with the x cubed, we've dealt with an x cubed with a bit extra as well. But we need to see what's left over before we carry on. X cubed take away x cubed is 0. Negative 5x squared take away 3x squared will be a negative 8x squared. And the rest will stay as it is. So now repeat the process. Now at the front we have negative 8x squared. We're dividing that by x, and that will give us negative 8x. But then, of course, we haven't dealt with the plus 3, so we need to multiply that by our original number. So negative 8x times x is negative 8x squared. Notice how this always gives us the same number at the start. And then negative 8x times 3 will give us negative 24x. So we take away to see what's left over. So the first term always going to cancel out, and the next term, negative 3, take away a negative 24, double negative there, that will give us a positive 27x. And we're adding 9 to it. That didn't change. So now we take the 27, we divide it by x, and that gives us 27 as our answer. So then we, again, multiply that by the start to see what we have left over. So 27 times x is 27x, and 27 times 3 is going to give us a 81. Then when we take these away from each other, what's going to happen is we're going to have a remainder. We're going to have 9 take away 81, which gives us negative 72 as a remainder. Since we don't have 0 at the end, that means that x plus 3 is not a factor. And so we've guessed wrong here. And this might happen in exams. So if this happens, don't worry about it. Okay, we've done some working out. At least we've proven that we can do algebraic long division, even though it's not something that's helpful to us factorising this. So we've got a few marks already. So what we need to do now is we need to rub this out, and we need to try again. Now, I know that 3 definitely has to be factoring to this somehow to get that 9. So rather than being a positive 3, let's try a negative 3 instead. And let's see what this gives us. So we proceed the same way. We have x cubed at the front, and we're dividing it through by x, and that gives us x squared, which we can write in as our first answer. We haven't taken into account the negative 3, so we need to multiply that by the numbers at the start. X squared times x gives us x cubed, and x squared times negative 3 gives us negative 3x squared. So now we're going to see how much of the equation is left to do. So the first terms cancel out. Negative 5 take away a negative 3. It's a double negative, so we added negative 5 plus 3 will be negative 2. And the rest of it hasn't changed because there's nothing to take away from those two terms at the end. Then we'll repeat the process. Now at the front we have negative 2x squared. We're dividing through by x. That gives us negative 2x. Write that down as an answer, but multiply it by the numbers you're dividing by just to make sure the negative 3 is being taken into account. So negative 2x times x is negative 2x squared. Again, matching up with the previous number. But negative 2x times negative 3 will give us a positive 6x. So we take that away to see what's left over. A positive 3 take away 6 will give us a negative 3x. The 9 will stay as it is. Then we repeat the process one more time. We have negative 3x. We're dividing it through by x. That will give us negative 3. We multiply the negative 3 by the numbers we're dividing by to take into account the negative 3 in the divider. So negative 3 times x is negative 3x. And negative 3 times negative 3 is a positive 9. So we take these away from each other. We get 0. So it's 0. Therefore, x minus 3 is a factor. So we're seeing that you can have an educated guess on which numbers to look at. Sometimes, particularly squared numbers, then the square root might be one. Very often, -1 or +1 are factors. They're things you can look at. And need to keep dividing until you find your first factor. Once you've found your first factor, then you can make some progress because now we know that x minus 3 is a factor, but also the answer to the algebraic long division is a factor. The x squared minus 2x minus 3 is also a factor. So then you factorize the quadratic using easier methods. Now we know we need to get a 9 eventually, so it's a safe bet there's going to be another x minus 3 to get the 9. And it's going to be positive. We can only have 2 negatives in there for positive. We have 3 negatives, then it would be a negative. So the last one must be x plus 2. So I've used a bit of logic there to factorize it. I know I need 2 3's. We know that x plus 3 isn't a factor, so there must be 2x minus 3's to get the 9, for example. If there's no logic like that you can use, then you can just factorize the quadratic using the methods you've used before. With linear equations, you have to collect all of the x terms on one side and all the number terms on the other. So, for example, let's say we have 5x plus 10 is equal to 35. What we want to achieve here is have the x terms on one side and the number terms on the other side. So we have a value like x equals something. We're trying to find a value of the x. Now, the way that you solve these is through kind of patient, systematic, step-by-step changes to both sides of the equation. So, for example, with this one, we can take 10 away from both sides, and that leaves us with 5x is equal to 25. And so what we've done is we've made the equation simpler, but we haven't changed the values of anything in the equation because we did the same thing to both sides. Then our next step, we can divide both sides by 5, and that leaves us with x is equal to 5. And now we have the answer that we were looking for. Sometimes when solving an equation, you might have multiple values of x. So, for example, you could have 5x minus 20 is equal to x minus 12. Now, in this situation, the first step should be to get all of the x values onto one side. So, for example, here, we could take x away from both sides. We're getting rid of the smallest value of x. And that will leave us with 5x take away x will give us 4x. So 4x minus 20 is equal to negative 12. Now we've done that, we can add 20 to both sides. And that will give us 4x is equal to a negative 12 plus 20 will be a positive 8. So now we divide both sides by 4. And that will give us that x is equal to 2. So the important things here are knowing which order to do each inverse operation and knowing what the inverse operations are. Generally, it's easier to get rid of plus and minus first, and then do multiply and divide. However, you need to be careful about things like fractions, square roots, brackets, powers, which may alter the order in which you need to do things. One way of solving equations which makes things look very different is when you have a quadratic with an equation. So, for example, we could have x squared, take away 14x plus 49 is equal to 0. Now, you should have already covered factorizing quadratics. If you haven't, you need to go and revise that first, because I'm not going to go through it here. But essentially, when you factorize this, you'll get something like this, where we have x minus 7 and x minus 7 in brackets. And the difference between factorizing quadratic and solving a quadratic equation is you just have this equal 0 on the end. What we don't have here is the kind of x equals a number we're looking for. But there is an easy shortcut we can use to do this. And what we want to look is, we want to make one of the brackets be equal to 0. Because if one of the brackets is equal to 0, then it's multiplying the other bracket by 0, and then you get 0. So how can we make the brackets equal to 0? Well, you have to look at the values of x. You have to think, what could x be to make each bracket be equal to 0? And you might get multiple options. So for the first bracket, highlighted in green, x would have to be 7 to make that bracket equal 0. You have 7 take away 7 is 0. So no matter what the second bracket is, you're always multiplying by 0 and you get 0. Highlighted in pink, the second bracket would also need to be 7 for everything to equal 0. And so for this one, we can see that x is just equal to 7. Now, why have I bothered to look at each bracket separately when they have the same answer? So let's look at another example. So let's look at x squared minus x minus 56 is equal to 0. Now, again, knowledge about factorizing to factorize the quadratic part of this. And if you factorize the quadratic, what you should get is x minus 8 and x plus 7. So then again, we look at each bracket separately when you think, what could x be to make the bracket be equal to 0? Because then the other one doesn't matter, because you multiply by 0, you get 0. Well, for the first bracket, x would have to be 8, because then you get 8 take away 8 is 0. But for the second bracket, x would have to be equal to -7, because -7 plus 7 is 0. So we have two possible answers. So which one do we choose? Well, actually, all you need to do is say that x is equal to both of them. It's equal to 8, and it's equal to -7. The only time you have to choose between the two is if this was part of a practical question and a negative value will be impossible if the context is some kind of real-life problem. This method works even if you have something more complicated like a cubic. So let's say we had x cubed, or let's do 3x cubed, plus 27 x squared, plus 72x, plus 48 is equal to 0. Now, again, I'm not going to go through how to factorize this, but you're probably going to be using some form of algebraic long division to do it. But you're going to end up with values in 3 brackets, and it'd be equal to 0. There's more than one option for this one, but you could have x plus 1, x plus 4, and 3x plus 12. So again, what you need to do is look at each value of x and think, what could this value be to make the entire bracket be equal to 0? So for the first x, it would have to be -1, because -1 plus 1 is equal to 0. The second one would have to be equal to -4, because -4 plus 4 is equal to 0. Then the third one's more complicated because it's taking the form of an equation. So we have 3x plus 12. So what we want is we want the 3x to be equal to -12 for it to equal 0. So sometimes a little more complicated to figure out what x is. And if 3x needs to be equal to -12, then 1x needs to be equal to -4. So now we've got all of our alternatives. We can write down our answer. And x is going to need to be equal to -1 or -4. And because two of the brackets have -4 as a value, we only need to write it down once. Just like with our first example like this, both brackets are equal to +7. So we can just write 7 as our answer. So only write down multiple options if they do take different values. Now, the last thing we'll do here is that with so much on the page, it might not be very clear which ones are the answers. I'm just going to highlight all the answers in purple now. The first example, x was 5. The second example, x was 2. In the third example, x was 7. In the fourth example, x was 8 or -7. And in the final example, x was equal to -1 or -4. With simultaneous equations, it isn't a matter of getting all the letters on one side and all the numbers on the other, and then getting a value for the letter, because you're going to have more than one letter involved. So, for example, we might have something like 2x plus 6y is equal to 56. But we can't solve this using the methods we've used previously for equations because we have two letters. But because it's simultaneous equations, we'll be given a second equation with the same x and y values to help you solve it. So we're going to have x plus 5y is equal to 42. Now, our aim here is to eliminate one of the letters. Now, there's a few strategies for doing this, but the easiest one is to multiply one of the equations or both the equations until you have either the x or the y values matching up. Now, you need to spot how to do this. So have a look at the letters one by one. So, for example, if we look at the y's, we've got 6y and 5y. Now, there isn't a way, really, to get these equal to each other easy in multiplication. You'd have to multiply 6 by 5 and 5 by 6, so they're both equal to 30. If we look at the x's, we've got 2x and we've got 1x. Now, this is easier because we could multiply x by 2 to get 2x. And so that's what we're going to do. We're going to multiply all of the second equation by 2. And then this will give us a new question. We've got 2x plus 6y is equal to 56. And then multiplying by 2, x times 2 is 2x. 5 times 2 is 10y, and 42 times 2 is going to give us 84. So you're going to find some sort of way to make one of the variables line up, and now we have the x's line up. Once you've done that, you need to think about, can you add or subtract these to get rid of one of the numbers? And so with the 2's lining up, what we can do is we can do this as a column takeaway, and we can do 2x take away 2x is 0x. It's gone. That's why we did it. We can do 6y take away 10y is -4y. And we can do 56 take 84, which is -28. Now, both of these are negative, so a little trick here is we're going to solve an equation now to find what y is. So what we could do for our first step is that we could ignore the negative numbers. We could just say it's 4y equals 28. And we're only allowed to do that if we do it to both sides. Effectively, the maths we've done to get rid of the negative sign on both sides is to divide by a -1 or multiply by a -1. They'll do the same thing. Then we can divide both sides by 4, and we'll get y is equal to 7. So now we've got our first variable, y is 7. All we need to do now is take one of our two equations. Doesn't matter which one you choose. So the smallest one's normally easier. So let's take the x plus 5y equals 42. We know that y is 7, so actually x is going to be plus 35 because 5 lots of y is 5 lots of 7. So x plus 35 is 42. So what do we need to add on to 35 to get 42? We're going to have to add on another 7. So we can see that x is also equal to 7. At the end, you might just want to make your final answer really clear because the working out for them is both in different places. So you could write out the answers again, or alternatively, you could highlight them or something. Usually there'll be an answer line to write the full answer onto. So y is equal to 7 and x is equal to 7. Now, simultaneous equations can get more complicated. So let's look at some more complicated examples. So let's say we had 2x plus y squared is equal to 12. And again, because it's a simultaneous equation, we are going to need to have another equation to go through it. So we're going to have x plus y is equal to 6. Now, again, there's going to be a few different methods we can use here, but the gist of it is we've got two letters, an x and a y. We want to get rid of one of the letters. Now, we could do what we did with the previous question, and we could multiply the second part of it by 2 to get 2x and 2x and take them away from each other. And that'll be one method. Another method is that we could rearrange the second equation to be x equals something or y equals something. So we could say that x is equal to 6 take away y, just by rearranging it. And then once you've done that, you get your original equation, which is 2x plus y squared. But we know what x is. X is equal to 6 minus y. So we swap the x with what we've rearranged to get x equal to. And then we add the y squared onto that, and that's equal to 12. So let's expand the brackets. 2 times 6 is 12. 2 times negative y is negative 2y. Then we've got the y squared, and it's equal to 12. And now let's rearrange it to have the larger powers first. So we've got the y squared, taking away 2y. And then on the left-hand side, we've got 12. So normally we'd write plus 12. But on the right-hand side, it's equal to 12. Now, we could write it out like this. If we take 12 away from both sides, we'll get a quadratic. If we take 12 away from both sides, then it's going to be equal to 0. So now to find what y is, we need to factorize the quadratic. We're going to have y in both because y times y will give us the y squared. We want two numbers that multiply together to give us, well, there's no number on the end, so it'll be 0, and add together to give us -2. So that's going to be a y plus 0 and a y minus 2. So then when we're writing down what y is, we're going to make the brackets equal to 0. So we could have y is equal to 0, or we could have that y is equal to a positive 2. And so that's how we get our first number. And then to find x, we can substitute into x plus y. So we want x plus y to be equal to 6. So if y is 0, x would have to be 6, so it equals 6. And if y was 2, then 4 plus 6 would be equal to 6. 4 plus 2 would be equal to 6. So x would have to be 4. And so that gives us two possible answers. We can have x is 6 and y is 0, or we could have x is 4 and y is 2. So when you get a squared number, you get a quadratic as part of the simultaneous equation, you might be getting more than one set of answers, so be careful with that. The last thing to look at is when we have 3 sets of variables and even 3 sets of equations. So we could have something like y minus x minus 2z is equal to 17. We could have x plus 2y plus 2z is equal to -35. And we could have 2y minus 2x minus z is equal to 13. Either the two methods we've used before. So the first method is called elimination, where you try and make two of the variables hold the same value and add them or take them away to kind of cancel them out. Or we can use the second method, which is by substitution, where we rearrange to make one of the letters a subject and then substitute that in to get rid of it. If you want to use elimination, you're going to need to have two of the variables be the same. So for example, what you could do is you could multiply the top equation by 2, and that will give us y times 2 is 2y, negative x times 2 is negative 2x, negative 2z times 2 is negative 4z, and 17 times 2 is 34. And one of the other equations matches up with that. It's the bottom one, 2y take away 2x take away z is equal to 13. Now, what we want to do here is we want to do something to eliminate the variables. And if we take away, we get 2y take away 2y is 0y. Negative 2x take away a negative 2x. So it's a double negative, so it'll be that. Negative 2x plus 2x is 0. That's gone as well. And then negative 4z take away a negative z. Double negative there, so I'll give us negative 3z. Then we can do 34 take away 13, which is 21. So we solve the equation. What we'd get here, if we divide both sides by negative 3, we get z is equal to negative 7. So that's one way, try and eliminate two variables at once, and you can find the value of the third one. I'm not going to do the rest of this. What you could then do is substitute z in. So every time you see a z, swap it with a negative 7. And then once you've done that, you can do another round of elimination, this time only eliminating one variable because we've already got rid of the z because we know what value it has. Alternatively, another method is that we could do a substitution method. So taking that top line again, we could change it into y is equal to 17. And then we can add x to both sides and add 2z to both sides. And then what we would do with this is then we would swap the y's in the second and third equations with 17 plus x plus 2z. And then that would give us, once we collected all the like terms, a regular simultaneous equation where you can then use, again, you might want to use elimination again this time, or you might want to do another substitution afterwards. So you have two options. So the top option being by substitution, and the bottom method being the elimination method. But no matter which method you choose, you then continue through and you find the values of x and y as well. And again, at the end, make sure the answers are really, really clear. So maybe write them out for a second time, maybe highlighting them, and just making sure that the answers are very, very clear. And for that last question, you might want to try it yourself. And what you should get is that z is negative 7, y would be negative 6, and x would be negative 9. With inequalities, the majority of the rules of these follow the same rules as equations. So let's look at an example. So let's say we have x over 2. We're taking 6 away from it. Now with an equation, we'd write something like it's equal to 3. With an inequality, we don't have the equal sign. What we have instead is an inequality symbol. And for this question, it's going to be less than or equal to 3. But for the purposes of solving the inequality, we're going to assume, kind of treat it as a equal sign. So to solve it, we would add 6 to both sides, giving us x over 2 is less than or equal to 9. Then we would multiply both sides by 2, giving us the answer x is less than or equal to 18. So as you can see, it works exactly the same way as solving an equation. It's just rather than say that x is exactly equal to 18, and if you ignore the numbers, x can be any number which is less than or equal to 18. So x could be 18, 17, 16, for example. And you can show these answers on number lines as well. So on a number line, you just do a small segment of it. So let's say we have 19, 18, 17, 16, and 15. We would put a dot over 18, an arrow pointing in the direction of the allowed values. And then if it's allowed to be equal to, we colour in the dot. So it's an empty dot, we're not allowed to use 18, but we can use numbers that are smaller than 18. For example, 17.9. But if the dot is coloured in, that means we are allowed to use 18 itself. Now, what we're going to focus on are situations where inequalities don't follow exactly the same rules as equations. So our first example like this will be negative 2x, take away 5 is greater than 3. So we'd go through and solve it. So we'd say, right, we add 5 to both sides. Give us negative 2x is greater than 8. Then we would divide both sides by 2, giving us that negative x is greater than 4. Now we have the negative symbol on the x. And what you might be tempted to do is you kind of divide both sides by negative 1. And you might be tempted to write that x is greater than negative 4. Now, with inequalities, this isn't true. And what you need to do is that when you kind of flip the signs like this, you also need to flip the inequality symbol. So greater than is going to become less than. The other exception is when you might have something like this. We might have 18 is less than or equal to 4x plus 6. And 4x plus 6 is less than or equal to 34. So because it's not exactly equal to, you can then end up having multiple inequality symbols. But again, while you work it out, you would treat it like an equal sign. So we're going to take away 6 to get 4x on its own, but we take away 6 from all three segments. So 18 to take away 6, 4x plus 6 take away 6, and 34 take away 6. Then when we divide by 4, again, that happens to all three segments of this. So we do 12 divided by 4, 4x divided by 4, and 28 divided by 4. And your final answer will look like this. And we're saying that x is in between 3 and 7. Now, if we look at how we put these on number lines, so let's say we have 2, 3, 4, 5, 6, 7, and 8. And we have a line. The way you would show this is you put a dot at 3, a dot at 7. And rather than arrows, you would join them together. It says that any value in between those two dots is allowed. So that would be 4, 5, and 6 are allowed for whole numbers. Now, given that it's less than or equal to, we are going to colour in the dots as well. So that means we're allowed 3, 4, 5, 6, or 7 if the answer is a whole number, it's an integer. However, there's nothing to say in this question that decimals aren't allowed either. So you could have, 3.1, 4.5. You could have any decimal in between. And just so we've got good notes, let's go back to the previous question and do the number line for that. So let's do the numbers around it. So it's -4. So we could do -2, -3, -4, -5, and -6. We're going to draw the line. And since 4 is mentioned in the question, we put the dot at 4. It's not coloured in because it's a less than. It's not a less than or equal to. It's going to be equal to colour it in. That means we're not allowed -4 itself, but we are allowed anything on the left-hand side of it. So, for example, you could have -4.1 or -4.01. You can get really close to -4, but you can't be -4 itself. Now, where this gets trickier is with quadratic inequalities. So you might have something like x squared minus 4x plus 3 is greater than 0. And again, we can treat that inequality symbol like an equal symbol and solve it like we normally would. So when you have a quadratic, you want to factorize it. I'm not going to go through how to factorize a quadratic here, but you should end up with something like this. So it's plus 3, so we need a 3 and a 1 as our factors. We need x, and to get the -4, we need to take away 3 and take away the 1. So it's factorized. Now, once you factorize it, if it was equal to, what you would then do is say, well, I need to make the brackets equal to 0. So if it's x minus 3, x must equal 3 to make the bracket equal to 0. Or for the second one, x must be equal to 1 to make the second bracket equal to 0. Because 3 take away 3 is 0, and 1 take away 1 is 0. And you only need one bracket to be 0, because that multiplies the other bracket, whatever value it is, by 0, and multiplying by 0 gives you 0. Now, the issue here is that it isn't equal to 0. It's greater than 0. And so what we need to do is we need to think about what symbol to put in between the x and the number. And it's not going to be as simple as saying they're both greater than. You say x is greater than 3 and x is greater than 1. Well, anything greater than 3 is also greater than 1. And so one of the answers becomes irrelevant. So, maybe that's the case. But what we can do is we can check on a diagram to see what the value is going to be. Now, to draw the diagram, you need to remember that a quadratic like this, where it's a positive x squared, has this shape. If you can't remember it's that shape, you're not going to be able to check your answer effectively. Now, what do we know about this? Well, we know that the kind of factors of this quadratic are 3 and 1. So what we can do is we can draw a line through, and we know for sure that this coordinate, the x coordinate, is going to be 3, and for this coordinate, the x coordinate is going to be a 1. So see the curve goes in between 1 and 3 on the x-axis. Now we need to think about the y-axis, and this is where the greater than 0 comes in. So let's just highlight the greater than 0. What part of this graph is greater than 0? Well, it's everything above the x-axis. So you can see, if I highlight everything that's greater than 0 on this line, I have two different segments. And then look at the 1 and the 3. The first highlighted section is going before the 1. If it's before the 1, then it's going to be a less than 1. The second highlighted section is after the 3 coordinate. So that's going to be greater than 3. So saying that x is more than 3, or it could be less than 1. So how can we show that on a number line? So again, write values around the number you've got. So we could do 4, 3, 2, 1, and 0. I'm going to draw the line. And I'm going to draw circles at the 2 places mentioned. So at the 3 and at the 1. And they won't be coloured in because they're not equal to. It's just greater than or less than. Now, with a 3, x is greater than 3, so we point towards the right, so all the numbers greater than 3. And on the left, x is less than 1, so we point towards the left at all the numbers that are less than 1. So we're allowed 0, we're allowed 4, we are not allowed 2, and we're not allowed 1 or 3 either. So this graph really, rather than showing which values are allowed, it'd be easy to show which values aren't allowed. We're not allowed anything in between 1 and 3. Let's look at another example. So we'll look this time at a negative x squared, and it's going to be taking away 5x and 6. And the whole thing is going to be greater than or equal to 0. Now, there's a few ways of doing this with a factorisation. Well, a negative x squared, so we're going to have a negative x multiplied by a positive x. It's going to be greater than 0. And then what we need to be thinking here is 2 numbers that multiply together give us 6. If we 1 and 6 are 2 and 3, let's try 2 and 3 first. And then we want to get a negative 5. So both these numbers will have to be negative. So we can have a negative 2 and a negative 3. However, that negative 3 will be multiplied by the negative x, give a positive 3. We don't want a positive 3. So if we make this positive 3 instead, then we have negative x times positive 3 will be negative 3. Also, this negative 2 times positive 3 will give us a negative 6. So we've factorised it. Let's look at x needs to be. So x will need to be related to a 3 to make the second bracket equal to 0. And for the other bracket, x is going to be related to, now if it's a 2, that negative 2 take away another 2 is negative 4. That's not 0. So it can't be negative 2, it must be a positive 2. And how do we get a positive 2? Well, it would have to be a double negative, because then we'd have negative 2 take away 2. And negative 2 is positive 2. Take away the 2 is 0. But which way around do the symbols go for these? So again, we're going to draw a graph for this. And again, you need to remember this shape of the graph. And it's going to be the opposite way around because it's a negative x. So positive x is going to be a U shape, and a negative x, it's going to be a N shape. And what do we know about this? Well, we know that it's going to go through 3 on the x-axis and negative 2 on the x-axis. And we want the portion of it that's greater than or equal to 0. So we need to find that on the graph. So look at the y-axis. We'll move above the x-axis. So the y-axis values are positive. It's the middle section. So always looking for the bit above the x-axis, what's greater than 0. Now for this one, we can see there's only one section. Look at negative 2. We can see the arc goes above negative 2 to the numbers larger than negative 2. So x is going to be greater than or equal to negative 2. And for the 3, the arc is before 3. So x is going to be less than 3. And that's a decent answer, but we can improve it. And what we can do is combine these together. And we can see that x is going to be less than or equal to 3, and negative 2 is going to be less than or equal to x. So we have 2 different ways of writing it. And then on a number line, you just look at the previous example with the x being in between 3 and 7. You'll do the number line exactly the same way, with a solid dot at negative 2, a solid dot at 3, and then you're going to join the lines together. So with quadratics, the big thing is that you can solve them like a normal quadratic, but at the end, you need to sketch the graph to see if it's going to be less than or greater than for both variables. Trigonometric graphs show the ratio between sides in triangles, depending on which 2 sides you're looking at. And it all goes back to think about the SUVAT. So if so, we've got O and H. So this graph shows that as an angle goes through different values, it shows a ratio between the opposite and the hypotenuse. You also have negative values. Now, these normally aren't possible in triangles. So what these refer to is if you have a triangle on a kind of coordinate grid and one corner is at 0, 0, then you could have kind of reverse triangles, which theoretically might have a negative measurement, but really the triangles are reflected in the opposite direction. So for example, all the positive values could be a triangle that quick sketch looks like this, whereas the negative values could be a triangle that's reflected that looks like this. So when you're using these real life objects, you just ignore the negative numbers. Negative numbers are just referring to the rotation or the reflections of the triangle. Now you've got the adjacent and the hypotenuse, then the ratio has the same pattern as sine, but it's all shifted. So you can see we've got the same kind of peaks and troughs. They're just happening further along. It's all shifted by 90 degrees. So cosine starts at 1, 90 degrees after sine starts at 1. The sine's at 1 at 90 degrees, cos is at 1 at 0. So there's that 90 degree shift. Tan's a little bit different. It's the ratio of the opposite and the adjacent. Now it rapidly increases and it actually goes past 1. And this is going to continue up and up and up and up and up to a little sketch. Now, what is this dotted line that's next to it? And this dotted line means that you cannot have a triangle that compares the opposite and the adjacent at 90 degrees, because that's going to be an impossible angle to draw. So when we say the graph's going up and up and up and up and up, what's going to happen is it's never going to touch this green line. It'll get infinitely close to the green line, but it will never touch the green line. Now, it normally kind of cuts it off at 1, but it might be useful going up to 2 sometimes as well. And then what happens is, after 90 degrees, tan resets, and it starts infinitely close, and then by the time you get to 135 degrees, it starts to show up back on the graph. But again, this line's going to do the same thing as we get infinitely close to the next dotted line. I've got a name for these dotted lines. We call them asymptotes. So it's a place on the graph with impossible values. And you do need to show it on the graph. The graph will be wrong if you have to sketch it and you don't show the asymptotes. Very important that it's known that you can't go through those values, which on this graph is 90 and 270. And they're 180 apart, but what you'll find with all three of these graphs is they can continue infinitely on forever. So we're only looking at a snapshot of the graph, the most useful part of a graph, in between 0 and 360. Another thing to mention is that these graphs all show values in degrees. And degrees is when you split a circle up into 360 degrees, which we mentioned with the geometry revision that it's 360 degrees. It's got a lot of different factors you can divide it by. It's been chosen by a person in the distant past as a good number to use. There's no particular mathematical reason why it's 360 other than it being easy to divide it up. Whereas a lot of maths kind of like comes out of kind of like universal rules with the universe. So it's kind of like we kind of don't want to just choose a random number. We want to base it on something. So there's another way to measure these graphs, and it's called radians. But basically, radians is rather than cutting a circle up into 360 degrees, in radians, you're going to cut the circle up into 2 pi degrees. And so because pi is a number that comes out of calculations with circles, and we're dividing up a circle, that it seems like an appropriate thing to use. And using 2 pi does make some equations in some contexts easier to use. So what we're going to look at now, important values on all three of these graphs. So we'll look at important values on the sine graph, the cosine graph, and the tangent graph. Now, the first important value is where we start, and we start at 0 degrees. And in radians, we just call that 0 radians. So on the sine graph, you can see at 0, we're at 0. I'm just going to highlight it on the graph. On the cos graph, we start at 1, and on the tan graph, we start at 0. This is the first important set of values. Now, if you type sin 0 into calculator, you'll get 0. If you type cos 0 into calculator, you'll get 1. But you might get this as a non-calculator question. You might need to memorize these values. Also, if you have to sketch the graph, it's important to know these so you know where to start drawing it. Particularly with sin and cos, which are the same graph shifted along. So it's important to know that cos starts at 1. The next important value is at 30 degrees. In radians, we call this pi divided by 6. And that corresponds to the same part of the circle as 30 degrees. Now, on the sine graph, if you look at 30 degrees, so these graphs up in 15s, so you can see that if we go across 2 lots of 15, which is 30, we're halfway up. So the value is a half. On the cos graph, at the same point, halfway up, we're nowhere near 30 degrees. So actually, when we look at 2 squares across, it's actually quite close to 1, isn't it? Now, there is an exact value for this, and we call it root 3 divided by 2. So we can't get like a whole number, integer whole number. It is an irrational number, but it is something we can display without any decimal places by saying root 3 over 2. So we call it an exact value. And with tan at the same part of the graph, again, you know, we're a distance up the graph. That's got an exact value. It's 1 over root 3. The next important value is 45 degrees. So that's 3 rectangles across on the diagram. You can see it labelled. And for sine, you can see it's up here. And for sine, that's going to be 1 over root 2. On the cos graph, you can see it's also got an odd value. And that's going to be also 1 over root 2. So that's a point where both sine and cos have the same value, although sine's going up at that point and cos is going down. And then on the tan graph, if we go 3 across, you can see that's where it hits 1. I should mention that in radians, 45 degrees is pi divided by 4. Next, we'll look at 60 degrees. So 60 degrees, in radians, that's pi divided by 3. On the sine graph, it's root 3 over 2. On the cos graph, it's a half. And on the tan graph, it's root 3. Now notice how the sin and cos values, root 3 over 2 and a half, are the reverse of the same at 30 degrees. So it kind of shows that, you know, sine and cos are similar graphs. They're going to hit the same values. They're the same graphs just shifted along. Tan, of course, is going to give you something that is completely different. The last important value is at 90 degrees. Call that pi divided by 2. So 180 degrees will be pi, and 360 is 2 pi. And on this one, sine is 1, cos is 0, and tan is where we have an asymptote. So 90 degrees for tan is an impossible value. It's something that we can't have. So we're not going to write down an answer for it. A good way to write down what tan 90 is to say that it's undefined. Now, one last thing we can do with these graphs is use them to make predictions. So for example, if you want to know what sine of 30 degrees is without a calculator, then you can go to the graph, you can find where 30 degrees is, you can draw a line up from 30 degrees, and you can draw a line across, and you can see that 30 degrees is equal to a half. And so you can write the answer a half in. That's the first thing you can do. Now the second thing we can do is the inverse calculations. So let's say we wanted to do, let's do cos for this one. Let's say we wanted the value of inverse cos to a half. So this time, rather than finding 30 on the x-axis and going up and across, we're going to find a half on the y-axis and go across and down. So you find a half, you go across, you go down, and we can see that 1/2 on cos corresponds to 60 degrees. So we could write 60 degrees as our answer. Okay. But here's a weird thing. What if we continue going across at a half? We end up getting another value. And we go down from here, we can see it's 15 below 315. So this is 300. So we can see that cos to the -1 over half is 60, and it's 300 degrees. And as I said, these graphs do go on forever. We've only got a 0 to 360 snapshot here. So you would have more values than this. So the important thing here is that when you're going from an angle to a number, you are going to get a single answer. If you are going from a number to an angle, you will get an infinite number of answers. So what we need to do is restrict the range of these answers. And so, for example, for these graphs, got sin x, cos x, and tan x, we would say that x is in between 0 and 360. And so we can write out like this. And that's true for all three of these graphs. So if you get a question and it says the range of values is in between 0 and 360 with this confusing looking notation here, all that means is that there's infinite answers and you only want the answers in between 0 degrees and 360 degrees. And you might see different ranges. You might see -180 to +180, for example, or you can see ranges written in radians. You'll know it's radians because it will have pi written as part of the angle. So one last thing to look at is a prediction with tan. So let's do tan to -1 of 0. Now, when we look at our table, we've got this value in already. Tan 0 is when we're at 0 degrees. So we can write 0 degrees in straight away as one of the fixed values that we know, one of the exact values. We look at the graph. If we start at 0 and work our way across, we can see we've got 0 degrees. Tan graph also meets that point at 180, and it also meets that point at 360. So actually, tan 0 degrees and 180 degrees and 360 degrees. So we've got three different answers. So then going back to our table of exact values, you can also find multiples of these values within the graphs by looking at the kind of symmetry of the graphs. So for example, sin 30 being a half, there'd also be another half. There's a half 30 degrees after 0. When the graph repeats, there'll be another half 30 degrees after 360. So sin 390 is also a half. So also expect to find multiples of these values. Now, these link to 90. You can see with the sine graph in particular, the second part of it is negative. So if you think then sine a half being at 30 degrees is 30 after 0 when it crosses through the x-axis. It crosses through the x-axis at 180. So what's 30 after that? Well, it's going to be 210. And you'll see at 210, there's going to be a negative version of a half there. And so you get negative a half on the graph. So there's way more exact values in these. You just have to use the symmetry of the graphs to find the rest of them, as you can see with tan minus 1 and cos minus 1 over half and 0 respectively. With trigonometric equations, we're going to use trigonometric graphs to help us solve equations. So let's have a look at three types of equations. So the first type is you might have something like sine theta, and then we're adding or taking away something from it. So for example, it could be taking away 20 degrees from it. And that's equal to 0.37. So how do we solve the equation? Well, we want to get theta on its own. So our first step is doing sine to the minus 1 to both sides. And that will leave us with theta minus 20 degrees is equal to, if you do sine minus 1 to 0.37, you're going to get 21.7 to 1 decimal place. So I have rounded this. So we've converted 0.37 into an angle. The last thing we need to do is add 20 degrees to both sides, which will leave us with theta is equal to 41.7 degrees. And it looks like we managed to get the answer without actually using the graph. But there is an issue here. And the issue is with the step we did inverse sine 0.37. Now that gives us 21.7 degrees. Let's try and find it on the graph. So 0.37, the graph goes up in sets of 0.2. So 0.37 is going to be just below 4, so around about here. We go across from there and we go down, then this is where we're getting the 21.7 degrees from. But this isn't going to be the only answer. There is another answer, because if we continue that line onwards, it's going to hit another point of the graph and give us another answer. And the unfortunate thing here is the graph is so complicated that we can't really read off an accurate answer here. We know it's going to be somewhere in between 135 and 180. We could narrow it down a little bit more, but we don't know the exact angle. Or do we? Because we can use the symmetry of the graph to get the exact angle. Now, what we're looking at with the symmetry of the graph is that the part where we got our first answer was 21.7 away from 0. These graphs are symmetrical, and there is a line of symmetry going through the peak if we only look at the first 180 degrees. So we're not looking at the second half of the graph. So if our first answer is 21.7 degrees away from where the curve starts to rise, looking at the symmetry, our other answer is going to be 21.7 degrees away from the end of the curve. And where does it end? It ends at 180 degrees. So we do take away 21.7 degrees, and that gives us our second answer. And it gives us 158.3 degrees. So using the graph, we've now come up with a second answer. Theta is equal to 41 degrees, and theta is also equal to 158.3 degrees. Now, there's one more difficulty, and that is that's the value of theta. And what did we do? Well, we added 20 to it to get our final answers. So actually, what we need to do now is add 20 to it as well. So a proper answer is going to be 178.3 degrees. So it's important to know at which point that second answer comes in. So look at the symmetry with the 21.7, then it comes in at the same place as the 21.7, which was halfway through our working out. The second type you might find, rather than adding or taking something onto theta, with our next question, we're going to have cos of theta, but we're going to multiply it by 3 and have cos of 3 theta. And that's going to equal negative 0.77. So again, we follow the same process, and we're going to try and get rid of the cos first and get theta on its own. We need to do inverse cos to both sides. That gives us 3 theta is equal to the inverse cos of negative 0.77. That gives us 140.4 degrees to 1 decimal place. Then we need to divide both sides by 3 to get theta on its own. And so if I just take the entire number, so I'm not rounding it here, I'm just using the full number of characters on the screen, I'm now going to get 46.8 degrees to 1 decimal place. So we've got a single answer by solving the equation, but again, we're going to need the graphs here because we're going to find a second answer, at least a second answer. So we go to our graph, and we're looking at the negative 0.77. So if it's going down in 0.2, so that's going to be just under 0.8. So we're going to look across. Don't worry about being too accurate with this. We'll look across. We hit the line. We go up. And we're hitting just after 135, which is about right because that should be the 140.4. Now, what we're looking for here again are multiple answers. So we go across from the 177. We're going to hit our second answer. Then we can go up, and we know roughly where the second answer is going to be. So what we need to do now is think about the symmetry of this graph and how we can approach this problem. Now, the sine graph, the symmetry only really applied to the first half when we're kind of looking at the x-axis. With the cos graph, we can put the symmetry right down through the middle because the entire graph is symmetrical. So then looking at the symmetry, our first answer is 140.4 away from the first side, which starts at 0. So with the symmetry, we're going to be 140.4 away from the opposite side. Now, the 140.4, we're starting from 0. Going the other direction, we're starting from 360. So we do 360, take away 140.4, and we're going to get our answer. And it's 219.6 degrees. Now, again, that's rounding to 1 decimal place. We're going to do something else to it. So we want a higher level of accuracy. So what I'm going to do is, I'm going to, on the calculator, do inverse cos negative 0.77. Get the full level of decimal places. It's 140.353889. I'm going to take that number away from 360. Now, with that number, remember, this comes in at the 3 theta section. It corresponds to 140.4. So what I need to do now is divide my full level of accuracy number by 3, and that gives me 73.2 degrees. So now, using the diagram, we have 2 answers. So we solve the equation to get one answer, and then we use a symmetry of the graph to get our second answer, with each graph having a slightly different symmetry. Now there's a third step. Now the trick here is the range of possible answers. Now for these questions, we're going to have a range in between 0 degrees and 360 degrees. Now, if we're dividing by 3, you can see our 2 answers are quite close together. And if you divide by 3, you can make quite large numbers fit into the 0 to 360 range. So what we want to do really is we want to look at a 0 to a 3 times higher range just in case. So 360 times 3 gives us 1080. So when we find answers in that range, after we divide by 3, they're guaranteed to be in between 0 and 360. And our graph only covers in between 0 and 360. So how do we get the rest of the answers? Well, another part of the symmetry of these graphs is that they repeat every 360 degrees. That means that if you add 360 degrees onto your answer, it's going to correspond to the answer on the next section of the graph if we continue drawing it further out, perhaps up to 720 for another 360, and up to 1080 for another 360 on top of that. So the graph repeats every 360 degrees. So if we are dividing by 3, 360 divided by 3 is 120. So this pattern is going to repeat every 120 degrees. So going from a 360 repeat to a 120 repeat because we're dividing by 3. That means we can add 120 onto our answer for another set of answers. So we can take 46.8 and add 120 to it, and we get 166.8. We can take 73.2 and add 120 to that. And that's going to give us 193.2 degrees. Notice how these answers are still within the 0 to 360 range. Now, we can divide it by 3, so rather than repeating once within 360, the 120 is going to repeat 3 times. Let's add on another 120. So 166.8 plus 120 gives us 286.8 degrees. And 193.2 plus 120 gives us 313.2 degrees. Again, the answer is still under 360. Now, if we added another 120 to that, we're going to get 433.2, and that is outside of our range. So when you have a question like this, where you are dividing, you also need to multiply out your range by what you're dividing by, because that division is going to fit more numbers within that range. Remember that these graphs repeat every 360 degrees. So if you divide it, it's going to repeat by whatever you divided by. In this case, repeat every 120 degrees. It's also worth noting, this was a 3 theta question. You can also have fractions in there. So, rather than multiplying by 3, you might have one where it's a half theta, which means that you're dividing it by 2. That means that to solve the equation, you'll be multiplying rather than dividing. And that will have the opposite effect. And that will mean you might have less answers. And some of your answers might end up falling outside your range after you multiply them. So always make sure that any numbers that aren't in your range, you would delete, you don't use. Now, the last thing we'll look at is something like this, where we have 5 tan theta equals 2. So in this case, what we're doing is we're multiplying the entire thing by 5, not just theta. All of tan theta has been multiplied by 5. Now, to rearrange this, the first step is divide both sides by 5, and that will give you tan theta is equal to 2 divided by 5, 2/5, which is equal to 0.4. So it's actually not too hard to get rid of any numbers at the start. You just divide 3 by it, and then you've got something that looks like a normal question. So all we need to do now is do inverse tan to both sides, and that will give us that theta is equal to the inverse tan of 0.4. Or inside your brackets, you could write 2 divided by 5. That would work as well. And that gives you 21.8 degrees to 1 decimal place. Now, again, like all of these questions, this is going to give you something that's one of multiple answers. So let's look at tan 0.4. So we see we're coming in and we're getting 21.8 out of it. However, if we extend this line, we can see that there is going to be a second answer. So how do we get the second answer? Well, you're surprised how with tan it's really easy. Now, the symmetry with sin, you can see, we just look at the 180 degrees of sin, the first 180, and we put the symmetry line through the peak, and we do 180 takeaway. With cos, we can put the line of symmetry through the middle of the entire thing, and we do 360 takeaway. Now, with tan actually doesn't repeat every 360 degrees. Well, it does in a way, but it also repeats every 180 degrees. Now, that's a factor of 360, so it will repeat every 360 as well, but it's also got a shorter repeat like this. That means we can just add 180 onto our answer. So we take a 21.8, we can add 180 onto it, and that will give us that second answer. So we're doing 180 plus the 21.8, and that gives us 201.8 degrees, which is our second answer. Now, as an extra, what if the range of this isn't the 0 degrees to 180 degrees that the previous 2 questions have been? What if this one is negative 180 degrees between x and positive 180 degrees? Well, in this situation, our answer we just got is outside of the range. We can't use the answer. It's bigger than 180. And our graph doesn't show the negative part of tan. So do we need to extend the graph? Well, we don't, because we know it repeats every 180. So as well as adding 180 to get larger answers, we could actually take away 180 as well. And the 21.8 take away 180 is going to give us negative 158.2 degrees. And that does fit within the range. So once you've got your final answers, always go back, look at the range of answers you're allowed, and see if your answers fit within it. If any are outside, cross them out. And if the range goes into negatives you didn't expect, then just check to see if there are any in the other direction, again using the symmetry you've been using all along. We are going to have a look at trigonometric identities. Now with trigonometric equations, we've always had one of sin, cos or tan. We'll look at here what happens if we have more than one of them. And then identity means we've got a kind of formula that will help us reduce the multiple copies into one copy so we can solve it as normal. So for our first one, we're going to have a look at the equation 6 sine squared theta plus 5 sine theta plus 1 is equal to 0. So with this, what's happening is we have got two lots of sine. And hopefully you notice that it looks like a quadratic equation. So we're going to treat it like a quadratic equation. So we need to open up some double brackets and we need to factorize this. Now we're not using x like we normally would, we're using sine squared. So we need sine on both sides because sine theta times sine theta will give us sine squared theta. Just like x times x will give us x squared. It works the same way. And for factorizing a quadratic, we want to find two numbers which multiply together to make 1. And add together to make 5. Which numbers multiply to make 1? Well, it's got to be 1. And then how do we make those make 5? Well, 1 and 1 can't make 5. But remember with this, because we have these 6 on the sine squared, then we can use those to multiply our coefficients. So let's say 6 is made of 3 times 2. When you multiply these brackets, you get 3 times 1 is going to be 3 sine theta. And you're going to get a 2 sine theta times 1 is 2 sine theta, and 3 sine theta and 2 sine theta will add together to make 5 sine theta. So I've rushed through how to factorize a quadratic. Again, always the same way. So go and look at the revision for factorizing quadratics for a bit more information. But anyway, we've factorized it, and now we need to make the brackets equal to 0. Now, if we want to make the first bracket equal to 0, then sine theta would have to be a third, or rather a negative third, because 3 times negative third will give us negative 1, and negative 1 plus 1 will give us 0. So our first answer is going to be that sine theta could be a negative third. To make the second bracket be equal to 0, then that sine theta would have to be equal to negative a half, because two lots of negative half will give us negative 1, and negative 1 plus 1 will give us the 0. So now we've got two answers, and we've now got two equations. And let's actually carry on like we've done with trigonometric equations. So we want to get theta on its own. So we need to do the inverse of theta to both sides, the inverse of sine to both sides. We take inverse sine and negative a third. That will give us negative 19.5 degrees. And if we take the inverse sine to get theta on its own of negative a half, that will give us negative 30 degrees. So we've got two answers. We need to check the graph for the rest of the answers. It's also worth noting the range we're looking for. Now, what if the range was only in between 0 degrees and 360 degrees? We are allowed either of the two answers we've been given. So what do we do? Well, firstly, you would sketch your sine curve. And you just need to sketch the positive one between 0 and 360. And we'd look where negative 30 is first. Negative 30 is going to be starting, and we can extend this slightly into the negative with a little sketch. So negative 30 is going to be roughly around about here. And we can see there's going to be another answer after 180. And there's going to be another answer before 360. Now, because the negative 30 that we've got is 30 away from 0, we know there's going to be symmetry involving 30s here. And what's going to happen with our other two answers, let's just do these in another colour actually, is that we're going to have one that's 30 above 180, which is going to be 210. And we're going to have one that's 30 below 360, which is 330. So while we're not allowed to have negative 30, using the symmetry of the graph, we can see it's going to correspond to 210 and 330 degrees. That's our first one done. Now, for the next one, it's very close to negative 30. It's at negative 19.5. Now, that means we're going to follow the same method. We're 19.5 away from 0. We're going to be 19.5 away from 180 and 360. So we take 180 and add 19.5, and that will give us our second answer, which is 199.5. Then we're going to take 360 and take away 19.5, and that'll give us our fourth answer, which is 340.5. So again, while our range of answers doesn't allow negative 19.5, we can use the symmetry of a sine curve to work out where the positive versions would be. and it's 199.5, and it's 340.5 degrees. And so there we have our 4 answers for theta. So that's how you get rid of having 2 sins or 2 cos or 2 tan. And it worked the same way for cos and tan as well, if it was a cos or tan squared. Now, what if we had a mix of sin and cos? So for our next question, we are going to have cos theta multiplied by cos 2 theta plus sine theta multiplied by sine 2 theta. And that's going to equal negative 0.43. So that looks like a mess. How can we solve that? Well, this is where we're going to look at our trigonometric identities. Now, there's 3 we need to look at, and these are called the compound angle formulas. So we have sine angle A plus or minus angle B is equal to sine A times sine B, or rather sine A times cos B, plus or minus cos A times sine B. So if you've got a really long thing with lots of sines and coses in, you can compress it down into just a sine. The second formula, which is the one we're going to use for this question, is that cos A plus B is equal to cos A times cos B. Now, in our original, it's plus or minus. It's going to be minus or plus. So it means that if this is a minus, then we're just going to simplify it to a plus. And if this is a plus, we're going to simplify it to a minus. And on the other side, we've got sine A multiplied by sine B. There's also one for tan. So tan plus or minus B is equal to, and it's tan A plus or minus tan B all over, so we're dividing this, 1 plus or minus tan A tan B. And while these formulas look really complicated, that means it's going to be obvious that you've got to use one of them. So, we've got cos theta, cos 2 theta, plus sine theta, sine 2 theta. That looks really complicated. Obviously, we need one of these formulas. So we're going to use the cos formula. And with the cos formula, we've got to say what A and B are. A is the first angle we're mentioning, and the first angle is theta. And B is the second angle we're mentioning, which is 2 theta. You can see we've got the cos theta, cos 2 theta, and the sine theta, sine 2 theta. So we've got those 2 angles being used. And we'll really carefully look at the plus or minus. Now, we've got a plus in our original. In the equation, it's minus plus and minus. It means we switch the sign. So this is going to be a minus. And cos theta minus 2 theta is going to be equal to 0.43. And we can actually do that sum. Cos theta take away 2 theta is going to give us negative theta. So it's 1 take away 2. So now we can do inverse cos to both sides to get negative theta. And the inverse cos of negative 0.43 gives us 115.5 degrees. So if that's negative theta, then positive theta is going to give us the opposite of that, which is negative 115.5 degrees. And so that is our first answer. Now, again, it's a negative, and it's not going to fit on our graph. Now, you can sketch between 0 and 360, and then you can maybe extend the graph backwards, and that'd be one method of doing this. Another method is, why don't we do it with negative theta and then swap the signs on our final answers? So negative theta is 115.5. So let's find 115.5. So we had 0.43, so it's a negative 0.43, and then that corresponded to 115.5. So the second answer, we can look at the symmetry of the cos graph, is going to be here. We know the symmetry of a cos graph is going to be through the middle. So if we are going to be 115.5 away from the left-hand side, which is 0, we're also going to be 115.5 away from the right-hand side, which is 360. So 360 take away 115.5 will give us 244.5 as a second answer. However, these are negative answers, and the range is likely going to be between 0 and 360. So how do we get the positive versions of the answers? Well, remember, these graphs repeat every 360 degrees. All we need to do is add 360 onto the negative versions. So I'm just going to, for space, just adjust this. So negative theta is going to become positive theta. But if we do that, then we're going to have a negative 115.5 and a negative 244.5. So to get positive numbers out of these, all we need to do is add 360 to both of them. So we take the negative now, 115.5, and plus 360, and that gives us a positive 244.5. And if we take the negative 244.5 and we add on 360, that's going to give us a positive 155.5. So now I can adjust the answers again and get rid of those negative symbols. And a quirk of the cos graph is that positive and negative values, if you add on 360, when you've got two values like this, are going to correspond to each other. Now, the last question we'll look at is another way where we can mix together cos and sin. I'm going to look at cos theta is equal to 2.5 sine theta. And for this, we need to introduce another trigonometric identity. And for this one, it's going to be that sin divided by cos is equal to tan. So what we want to do is get the sin and cos to the same side. Let's divide both sides by sin. That will give us cos theta over sin theta is equal to 2.5. Now that is the opposite way around to the identity. Sin over cos is tan. We've got cos over sin. So to flip those around, what we're going to do is find the reciprocal of both sides. So to find the reciprocal of a fraction, you flip them upside down, which is what we've done, what we want for our identity. But then to do the same thing on the other side with the 2.5, you can't flip a whole number around or, something written as a mixed number. So what you need to do is 1 divided by 2.5. So again, we're taking the reciprocal of both sides. If it's a fraction, flip it over. If it's not a fraction, it's going to be 1 over the number. And we can do 1 over 2.5 is 0.4. And we can do sine theta divided by cos theta. It's tan theta. So tan theta is equal to 0.4. So once we have tan theta equals 0.4, we do inverse tan to both sides is equal to 21.8 degrees. All we need to do now is find the other answer. So we can see where 21.8 is, and then we can see that there's going to be another answer further on. And again, remember with tan graphs actually repeat every 180 degrees. So all we need to do is add on 180 for the other answer. So 21.8 plus 180 is going to give us 201.8 degrees. Now, there are more trigonometric identities in this, and we come into a lot more of these as you move on to a full A level. There's one more famous one that's going to be important to mention, and that is, we'll squeeze it in at the top, that's sine squared theta plus cos squared theta is equal to 1. And you might see various rearrangements of that you've got to use to answer questions like this. But the gist of all three of these is there's different ways to have multiple trigonometric words, sin, cos, and tan. And there are things you can do to reduce them down to 1. Then you can use the appropriate graph to solve. Differentiation is a mathematical function. So the way it works is you take a function, f of x, and you're going to have something, for example, you might have a coefficient on the start of an x, and you might have a power. And the way that you differentiate, which will give you f dash x, is that you bring down the power to the coefficient. So you're going to multiply the a by the power. So the coefficient being multiplied by the power. And then with the x, the power, because we've kind of used the power to multiply it by the a, we reduce the power by 1. Let's have a look at a few different scenarios of what this would actually look like in use. So let's say we have a function which is 2x to the power of 7. If we were to differentiate this, we would bring down the power. 2 times 7 is 14, and then reduce the power by 1. So then it would be a6. So going through that another time, we multiplied the coefficient and the power together. 2 times 7 is 14, and then we reduce the power by 1. Let's have a look at another example. So let's say we had a function, and this function is going to be 2/3 x to the power of 3. So now we can start to introduce fractions. So when we differentiate this, we follow the same process, and we're going to bring down the power and multiply it by the fraction. So 2/3 multiplied by 3 would give us 6/3. And 6/3 is 6 divided by 3, which is 2. Then we have the x, and we reduce the power by 1. So let's go through that one more time. We multiply the fraction by 3, which will give us 6/3, and reduce the power by 1. And then we can simplify the fraction. 6/3 is 2. The final answer is 2x squared. Remember, when multiplying a fraction, if you want to find an equivalent fraction, which is the same size, you multiply the numerator and the denominator, which would give us 6/9, which is the same fraction as 2/3. If you want to actually make it 3 times bigger, you only multiply the numerator. Let's have a look at another example. So we have a function, and this function is 4x plus 8. So we're going to differentiate it. Now, the key to differentiating this is to think, well, what are the powers on the x? And there are no powers on the x, so we can add them in. On 4x, the power is 1, and on 8, the power is a 0. That's why there's no x there. So we bring down the power on the 4x, 4 times 1 is 4, and we reduce the power on the x, because x to the power is 0. Now, as we can see in the question, if something's x to the power of 0, anything to the power of 0 is 1. So in the question, that's 8 times 1, which is 8. So here we've got 4 times 1, which is 4. So if you end up with a power 0, then you do not write an x in there. Here you have a power 1, as you saw, then we don't write the power, we do write the x. Now, what about the 8? Well, we do 8 times the power, 8 times 0, and that gives us 0. Then we reduce the power by 1 on the x, which gives x to the power negative 1. But the thing here is the coefficient is 0. We're multiplying it through by 0, so it doesn't matter what the x term is. If you multiply by 0, you get 0. And so when we differentiate this, we end up with 4 as our answer. So what you can see here is, if you have an x to the power of 1, or just an x, it's going to reduce down into just a number. 4x has become 4. If you have something that's just a number, and you differentiate it, it disappears. It cancels itself out. And you can see here we had 2 different terms, and we differentiated them separately. So now we're going to look at an example with lots of terms. So we'll look at a function, which is 6x cubed minus 5x squared plus 7x minus 3. So when we differentiate this, we look at each term one at a time. 6x cubed. So we multiply the coefficient and the power. 6 times 3 is 18. And then we reduce the power by 1 down to a 2. Then we look at 5 times 2 is 10, and reduce the power down by 1. So a x to the power of 2 reduces down to x to the power of 1. But as we've seen previously, if it's power 1, we don't bother writing the power. We just write the x. Then we've got 7x to the power of 1. 7 times 1 is 7. Then we get x to the power of 0, which has a value of 1. You multiply by 1, it stays the same. The last one is a negative 3. And as we saw in the previous example, normal numbers just end up cancelling out to be 0, because we're multiplying it by the power, and there is no x there, so the power must be 0. And that gives 0. So we don't bother writing 0 down. So these are kind of the key set of differentiations that you're going to see. Now, there are some more complicated differentiations to look at. So the first kind of set of complicated differentiations are fractions. So you could have something like f of x equals 9 divided by x. Now, this isn't in the form that we've got the generalized form pink up at the top. It doesn't look like that. So our first step is to make it look like that. I need to know that if you're dividing by an x to the power of something, you can make it come up to the numerator, get rid of the denominator, but you've got to make the power be negative. So 9 over x is 9 over x to the power of 1. So we bring the x to the power of 1 up to the top, it becomes a negative 1. And notice in the form we can use. So when we differentiate it, we follow our method. We're going to multiply 9 by the negative 1, which gives us negative 9. And we reduce the power by 1. And 1 below negative 1 is actually negative 2. So we get negative 9x to the power of negative 2. So make sure when you do the negative numbers, when you make them smaller, the actual digits get bigger as you get further away from 0. Now, there are a few examples like this where you have to kind of rearrange the equation to be in the form that you want. So we could have a function that's 2 over x to the power of 7. So we can rewrite that as 2x to the power of negative 7. So all we did is we got the denominator, we multiplied it onto the numerator, but if you do that, it's going to end up being a negative on top. When we differentiate this, you do 2 times negative 7, which is negative 14, and we reduce the power by 1. Negative 7 becomes negative 8. Sometimes you might have one that's already negative, so you could have 6 over x to the power of negative 5, and we rewrite that as 6x to the power of 5. So if you bring in a negative power up to the top, it's rather than making the powers negative, kind of just reversing the sign. So positives become negatives, and negatives become positive. Once we've done that, it's fairly easy to differentiate. 6 times 5 is 30, and then reduce the power from 5 to 4. The last one we're going to look at is a power. So we could have f of x could be the square root of 4x cubed. And when we rewrite this, and we can rewrite square roots as a power. Yeah, we need to square root 4 to get 2. When we square root the x cubed, we're going to get x to the power of 3 over 2. So just remember that fractional indices can be rewritten as roots and vice versa. So when we differentiate this, we'll bring down the power. 2 times 3 halves will give us 6 halves. And then the x, the power's going to go down by 1. So 3 halves will go down by 1. So that 3 halves is 1.5. So it goes down by 1. It's going to be 1 half. And then we can simplify the fraction at 6 over 2 is 3. So that gives us 3x to the power of a half. So really what we're doing here is we're using the laws of indices to rewrite our equation into the format that we're used to then properly differentiate it. The next complication is using trigonometry. So you might have a function, trigonometry in it. So we could have 8 sine x. When you differentiate sine, it becomes cos. Everything else stays the same. When we differentiate cos, so we have 8 cos x. Now, it's not an inverse operation, this. We don't go to then 8 sine. It's going to be a negative 8 sine x. So don't think that differentiating sin and cos are opposites of each other. They're not. The last thing to look at is a number called e. Now, when you differentiate e, so let's say a function is 2e to the power of x. When you differentiate it, we get 2e to the power of x. So e is quite an odd number. It's like pi, it's an irrational number. When you differentiate, it's got a very odd behavior, and essentially you can think that e is immune to being differentiated. Now, there is a situation where it being differentiated can make a change. So let's say we have f of x, and we have 8e to the power of 2x. Now, when you differentiate this, you're going to get 16e to the power of 2x. So while the power is not going to change, if the coefficient on the x in the power is present, in this case it's a 2, then we will multiply the coefficient on the e by 2. But again, the power is not going to change. So e is quite an odd number, and it has some very odd rules when you're differentiating it and integrating it. When looking at the second derivative, you'll notice that I've kept all the working out from differentiation. Differentiation is the first derivative. So what's the second derivative? Well, the second derivative is simply when you differentiate a second time. The first derivative with 1 dash in our function, the second derivative has 2 dashes on your function. Now, all we do is just follow the exact same rules we followed for the first derivative. So we get the coefficient on the x, we get the power, and we multiply them together. So for our first question, 14 times 6 will give us 84. Then we reduce the power by 1, so x to the power of 6 becomes x to the power of 5. And there we have our second derivative. Moving on to the next question, second derivative. So we've got 2 dashes. We have 2x squared. So we multiply the 2 by the 2 to get 4. And then we reduce the power by 1. So our second derivative will be 4x. Second derivative, the next one. Now, the first derivative was 4. And we've said before that essentially this is 4x to the power of 0. So we do 4 times 0, which will give us 0. Then reduce the power on the x, which will be x to the power of -1. But because we're multiplying by that by 0, it's going to end up being 0 anyway, so that doesn't matter. So the second derivative of that is going to give us 0. So the second derivative, or even the first derivative of any number, will give you 0. Let's have a look at the next one. Now we've got multiple terms, and again, we'll just follow the same thing and do the derivative for each term. 18x squared, that will give us 36x. Negative 10x will give us negative 10. And the 7 is going to cancel out to 0, so we don't write it. So we just find the derivative every single term like we did for the first derivative. And you'll notice that if you start off with a kind of polynomial like this, where you have an x cubed, an x squared, an x to the power of 1, and you've got a normal number at the end, practically an x to the power of 0. So you've got one of each. What's happened is we've got 4 terms in our original question, we've got 3 terms in our first derivative, and 2 terms in our second derivative. Each time we differentiate, we lose our whole number term. So the total number of terms goes down by 1. Now, with the next set, all of these have, well, some of them have got negative numbers, so be very careful with those. So the second derivative of our next question, we've got a -9 for a coefficient and -2 for the power. So -9 times -2 gives a positive 18. Then we reduce the power on the x, so it's going to go to -3. So you can see we start with -1 in the original question, -2 for the first derivative, and -3 for the second derivative, reducing by 1 each time. We've also got a double negative for the next one. Coefficient is -14, and our power is -8. So 14 times 8 is going to give us 112. Then reduce the power by 1 to -9. Now, for our next one, we didn't have any negative numbers. This will be a little bit easier. So we've got 3 times 4 is 12, and the 0, so 320, and reduce the power by 1, 120x cubed. This stays consistent as well when you have functions that have a fraction as your power. So we're going to do 3 times a half, which will be 1.5, and then reduce the power by 1. A half, take away 1, will give you a -half. So I can show you how fractions can make this tricky, but just be patient and follow the rules. You should be okay. 3 times a half is 1.5, 1.5, and then a half take away 1 is -1/2. Moving on to trigonometry. So we want the second derivative of 8 cos x. Now that's actually the question afterwards, wasn't it, that we did before? So the answer will be -8 sine x. Differentiating cos into sine will give you a negative number. Differentiating sine into cos, we just swap the sine with cos. And then second derivative of an e, well, if the first derivative doesn't change it, the second derivative isn't going to change it either. Then looking at the last one, we've got 16e to the 2x. That'll end up being 32e to the 2x. So if you differentiate e multiple times and it's just power to x, you can have no changes. But if you differentiate e and it does have a coefficient on the x in the power, then you will be bringing down the coefficient. But the coefficient on the power itself won't be changing. Integration is the inverse operation to differentiation. And so it can have a similar general rule. Now we have this kind of curvy S symbol, and this is what we use to show that we're integrating. So let's say we have a coefficient on an x and we have a power. Then at the end, we have another bit of notation, the dx. Now, the relevant part of this is just the middle part. This is the bit that we're interested in. The rest is, technical notation. It just tells you what kind of maths you're doing. So we're only looking at the pink highlighted area. So what do we do with this? Well, with differentiation, you multiply the coefficient and the power and increase the power. So here we do the opposite. We are going to divide our coefficient by the power, and then we're going to increase the power. Now, when I say we divide by the power, we actually divide by the new power. So the power is b, we divide by b plus 1, and our new power is b plus 1. So let's look at some examples. So let's say that we are differentiating 5x to the power 6. Again, we're only going to focus on the maths in the middle. The curly S symbol, the integral symbol, and the dx, just part of the notation that shows the kind of maths we're doing. So we're going to take the 5 and we're going to divide it by the new power. Now, what's the new power? Well, it's power 6. We're increasing the power to a 7. So we divide by the new power, which is a 7. So we get 5/7 x to the power of 7. We've increased the power and we divide the coefficient by the new power. Just like with differentiation, you can do this with multiple terms. So we could have 7x plus 8. So again, we focus on the middle part and we just integrate both terms. So with the 7x, the power on the x is a power 1. There's no power, it's power 1. So we need to increase that to a power 2. That means a 7 is going to be divided by a 2. Then we look at the 8. Now, with the 8, if there is no x, that's practically x to the power of 0. So if we increase the power, we get to the power of 1. So we're adding 8x to the 1. Now, there's one extra thing here you might notice, which is that when you differentiate, you lose a term. So let's say if we differentiated 7x plus 8, we would reduce the power to get 7x to the power of 0. And then with the plus 8, that's 8x to the 0. We'd multiply the coefficient by the power and get 0x to the -1. And so you multiply something by 0, you get 0. So we don't write the 0x to the -1. We lose a term. And then the 7x to the power of 0, we just write 7, because x to the power of 0 is 1. So we lose terms. And in integration, we gain terms, but with no way of knowing what that number was that we've gotten rid of. There's no way to work backwards to it. So what we do in integration as well is we write plus c on our answer, plus a constant. And that says we could be adding on to this a whole number. But given the information we've got, there's no way to kind of work backwards and work out what that number was. Let's look at another example. So let's say we differentiate 9x to the power of a half. So we've got a fractional power here. And as usual, we focus just on the numbers in the middle. So what do we do here? So again, we take the x and we increase the power. So power half plus 1 will give us a power of 1.5. Or you could write 3/2. Now we need to divide 9 by 1.5. So how many 1.5s go into 9? Well, actually, this is something you can do. You can actually count up how many 1.5s go into 9. So you say, we've got 1.5, 3, 4.5, 6, 7.5, and 9. That was 6 that went in. So we say we've got 6x to the power of 1.5. Alternatively, it might be easier to write. You could just write 3/2 for this instead. Takes up a little less space. Now, just like with differentiation, we can write out questions that initially don't seem like we can do them. So we could have 2 over x to the power of 5. And just like differentiation, what we need to do here is change this into something in the format we're expecting. A coefficient, an x, and then a power. So we can write 2 over x to the power of 5 as 2 times x to the power of -5, just using our laws of indices. And now we have something we can handle. We take the x, when it increases the power, now -5 increases, not -6, it's -4. If you increase the power, it's going closer to 0. That means that the 2 will be divided by -4. That gives us -2/4. Now 2/4 is a half if you simplify it. So we'll have a -half x to the power of -4. There are other situations where you would have to rearrange this. So, for example, one situation would be having roots. So let's say we had the cube root of x squared. So again, we're focusing on that middle section. We've got to rewrite it into the form we need to actually integrate it. So that's the same as x to the power of 2/3. So any roots are just the denominator on your power. So then we're going to increase the power. Now 2/3, if we increase it by 1, that'll be 1 2/3. You write that as a fraction. We could write it as 5/3. And then we've got no coefficient at the start. Now if you don't have a coefficient at the start, it's 1x to the power of 2/3. So then we're dividing 1 by our power, which is 5/3. Now if you divide a fraction by another fraction like this, and you've got 1 over a fraction, you're essentially find the reciprocal of it. So that's going to be 3/5. So that gives 3/5 x to the power of 5/3. And what I've done is I forgot to put the plus c's on my last 3 answers. And this is really easy to forget. So always remember to put those on. That's just saying again that there's another bit to this that maybe we don't have. There's no way of working backwards with integration to get this number. Now, we also have some special cases. So we have trigonometry, for example. So if you are differentiating sine of x, then we differentiate it, you get a negative cos. And of course, it's plus c. If you're differentiating cos of x, then you get sine x. So notice they're not inverses of each other because you integrate sine, you get a negative version. With integrate cos, you don't get a negative version. There's also a version of this for tan. Now, we call this sec squared. And if you see that, it's just a kind of version of tan. And it will integrate to give you tan. Another thing to think about with this is we can have kind of coefficients that come to the front like in the other examples. So let's say we are differentiating and we've got 3 sine 2x dx. Now, the number on the x actually comes out like the powers do in the other examples. So this will give us 3/2. Sine goes to cos, and it'll be a negative cos. And then the number in the bracket is going to stay the same. So it'll still be 2x. And then that also will be plus c. E works in a similar way to differentiation, where if you're integrating e to the x, your answer is just e to the x. If you're integrating something like 4e to the power of 4x, then what would happen is that 4 would come down and divide your coefficient at the start. And use 4 divided by 4, e to the 4x. And so then that would just give you e to the 4x. And with both of these, as usual, we have the plus c, even if it's e. So here are most of the cases of integration that you should encounter. Definite integrals are a practical use of integration. So let's say we've got a line, y equals 8x minus 3. So let's just do a little sketch of this. It's not going to be very accurate. So it's going to be quite a steep gradient, and it's going to be going through -3. So something like this. Now, what we're going to do here is we're going to find a question involving integration. Now, it's going to look like this. we're going to have the integral symbol and two numbers next to it. We're going to have 4 and 3. We're going to have the 8x minus 3 and the rest of the integration notation. So you can see we've got the kind of the y equals pair here. So we've got the equation of our line. Now, what do the 4 and the 3 mean? So the 4 and the 3 mean that we're going to find the area in between 4 and 3 on the x-axis. So we're going to be finding this part of the graph here. Because when you integrate, what it does is it finds the area underneath the graph. And so we need to find that area. So how does integration help? Well, the first thing to do is actually to integrate. We're going to take the x, we're going to increase the power and divide the coefficient of that x by the new power. Then we move on to the next term. Now, again, with that, we're going to take the x. There isn't one, so there isn't an x. We're going to pop one in. Because that -3, that's -3 to the x to the power 0. So now it'll be x to the power 1. And we divide the 3 by the new power, which is 1. 3 divided by 1 is 3. And now it's integrated. So how do we find the area under the curve using this? Well, we substitute in the 4 and the 3. And you might see some square bracket notation for this. So when we integrate with 8/2, which is 4, so we've got 4 lots of 4 squared, take away 3 lots of 4. And remember, I forgot to write it in again, it's plus c when you integrate. So we've got to put in that plus c. There might be something else there. Once we find the answer for 4, we take away from it the answer for 3. So now we substitute in 3. So we've got 4x squared, so that'll be 4 times 3 squared. Then we've got the -3x, that'll be 3 times 3. And then we've got the plus c. And so what we need to do now is do the substitution and get some answers out of this. So working through this, 4 squared is 16. Multiply it by 4, you get 64. We're taking away from that 3 times 4. And we're adding on c. 64 take away 12 is going to give us 52. So we have 52 plus c from our first bracket. The second bracket, we're going to have 3 squared is 9. Multiplied by 4 gives us 36. Then we're taking away 3 times 3, which is 9. And we're adding on the c. Now, a really critical thing here is we are taking away the second bracket. So we've got 36 take away 9 is 27. But on our final answer line, we're not going to be adding on 27. We're taking away the 27. And then we're not adding c, we're going to be taking away c. So remember, all the answers from the second bracket have to become negative. Or they're already negative, they need to become positive. Now let's have a look at this answer line. So we've got 52 take away 27, which is 25. And then we've got the plus c and a takeaway c. So those c's have cancelled out, they've gone away, so we don't need to worry about them. And so now with this answer, 25, we know that the area under the curve in our little diagram here was 25. So definite integrals can find the areas under curves. Let's have a look at one more example. I'll look at a slightly more complicated example. So we're going to have y equals 5x squared plus 2x plus 9. And so when we integrate this, we want to get the area between 0 and -3. So let's write the integration notation. And we can see the equation of our line in the middle of that. So the first thing to do is going to be to actually integrate. So with the x squared, that will become x cubed, meaning that the coefficient 5 will be divided by 3. Then the next x will become x squared. So the coefficient 2 will be divided by the 2. Then move on to the next term, the 9. So that will go up to 9x. And we'll have the plus c at the end. So now we're going to write out our square brackets. And when we do our square brackets, we're going to think about the first bracket. We are going to be substituting in 0. So our first 3 terms all have x. And if x becomes 0, then we're multiplying by 0. So those terms just going to become 0. So the only thing we'll have left in the first bracket is the c, which doesn't have an x connected to it. So it won't be multiplied by a 0. So if you've got a 0 involved, that bracket is going to be 0. And we only need to look at the second bracket. Now that second bracket is going to have our 5/3 x cubed. And so we're going to substitute in -3 and cube that. Over the next one, with the x squared, 2/2 is 1. So it'll be 1x squared. So that'll be -3 squared. Then we're adding on the 9x, which would be 9 lots of -3. And then we've got the plus c at the end. So working through this step by step. So -3 to the power of 3 will give us -27. I'm going to multiply that by 5/3. So multiply by 5 and divide through by 3. That will give us negative 45. Then we have negative 3 squared, which is going to be 9. Then we have 9 times negative 3, which would be negative 27. And we'll have the plus c. So when we get to our final answer line, we've got the positive values from the larger bracket, which was 0, so we have a c in there. And the second bracket we're taking away, all of these are going to become negative. If they're not already negative, then they'll become positive. So we have the negative 45, we added 9, and we took away 27. And altogether, that's negative 63. We'd have to add 63 instead, since a double negative is a positive, and we're taking away the c. The c's cancel out, so our answer is going to be 63. That means that the area under the curve, 5x squared, plus 2x plus 9, the area is 63 in between 0 and negative 3. And one last thing, let's say underneath the curve. The area underneath the curve can go on forever. So the limit to underneath the curve is the x-axis. So really, it's the area between the line and the x-axis in between those two values. With logarithms, there's a list of rules you need to follow, and you might need to kind of use these rules to change logarithms from one form to another for use in various different equations. So let's have a look at the rules. So the first rule is that if you have a log with a number and you add to it a log with another number, then just like surds, if you're adding these together, you multiply them in the simplified version. And following on from the kind of comment that this is similar to surds, if you have two logs, log A, and you take away log B, then you need to divide A and B. Or perhaps you could write them as a fraction. So we have an addition law, a subtraction law, and just like with indices, we have a multiplication law. So if we have b log a, would the b mean that you're multiplying everything by b, and a is what the log's been applied to, then your answer is going to be a power. You can have log a to the power of b. And you might think, well, what about division? Is there one for that as well? And there is. So if you have log, and it's 1 over a, so it could be written as a fraction division, then the 1 over just means it's going to be negative. So it's going to be negative log a. Now, it's worth pointing out with all of these that there should be a base to the logs. So when we say something like log a, what that really means is that's a log to the base 10a. So you don't write the power, it's to the power of 10. And there's another one we don't write the power, is when you write ln. Let's say you've got ln a. ln is a log, that's the base e. Now, what is e? Well, e is an irrational number. It's very similar to pi in kind of how it's set up. So that would be log, and then e is 2.7. And then how many decimal places? Well, let's do 2.72. However, do be aware that's a rational number, and it will be continuing on. And there'll be an infinite number of decimal places without a pattern. Now, in all of the cases, you are going to write the power of the log. So let's have a look at some things where that's relevant. Additional set of rules here. You could have log of base b, so this could be any number, and it'll be a log of 1. And that's going to give you 0. So no matter what that base b is, it could be 10, it's just log. It could be ln, it could be 3, 4, it could be any number. If it's a log of 1, it's always going to give you 0. If you have a log of base b, and then you're also taking a log of the same number, so the base and the number you're logging are both the same, then that's going to equal 1. And then if you have a log of base b, you're taking a log of b to the power of a, then rather than that being equal 1, like the previous one, it's going to be equal to a. It's going to be equal to the power. Now, there's one more rule you need to know where the base is relevant, and that is if you have log to the base of b, and it's of a, you can do something to change the base. And what you can do is you can call it 1 over log a to the b. So by taking the reciprocal of it, by putting it as 1 over, you can swap the position of the number you're taking log of and the base of the log. Matrices are useful ways to show information such as coordinates. And it's a vertical bracket in effect. And you have a square bracket to show a matrix. So for example, we have the matrix -3, 9, and you can add another matrix to it. For example, 4 and -5. So these could be two coordinates that we're adding together. How do you add matrices? It's really easy. You add the tops, you add the bottoms. -3 plus 4 is 1, and 9 plus -5 is 4. So there shouldn't be any issues with that. You can also take away using the same method. Let's say we have 2 over 5, and we are taking away from that negative 3 over 9. So again, these could be two coordinates that we're taking away, with the top number being the x-coordinate and the bottom number being the y-coordinate. All you do is take away the tops. So 2, take away a negative 3, double negative, gives us 5, and 5 take away 9 is negative 4. Now, as well as having single matrices like this, you can have a double matrix. So we've just had a look at 2 by 1 matrices. A 2 by 2 matrix is going to have 4 numbers in. So we can have negative 6, 5, 4, and 2. Now, we can also add together 2 by 2 matrices with another 2 by 2 matrix. So let's say we're adding to this 0, 1, 3, and 2. Then it's simpler matter of adding the top left corners. Negative 6 plus 0 is negative 6. Adding together the top right corners, 5 plus 1 is positive 6. The bottom left, 4 plus 3 is 7. And the bottom right, 2 plus 2 is 4. So as you can see, adding and subtracting matrices is really easy. Where matrices become difficult is when we have a look at multiplication. So let's take a 2 by 2 matrix, and we could have negative 6, 2, 4, and negative 5. And let's multiply that by a 2 by 1 matrix. Let's say 3 and 2. We multiply these together, we are going to get a 2 by 2 matrix. The question is, how do we multiply this together? And it's not as simple as multiplying the tops and multiplying the bottoms. So the way we do it is we multiply the top row of the 2 by 2 matrix by the 2 by 1 matrix, the entire thing. And we get the following calculations. So we get negative 6 times 3 and 2 times 2. So what we're doing is we're multiplying the first number by the first number and the second number by the second number. And you add together those results. So negative 6 times 3 is negative 18. 2 times 2 is 4. Negative 18 plus 4 is negative 14. And that's what's going to go in the top of our answer matrix. Then we do the same thing with the bottom row. We're going to multiply the bottom row by the entire 2 by 1 matrix. That gives us 4 times 3 and negative 5 times 2. So again, the first number multiplied by the second number. We add those results together. So 4 times 3 is 12. Negative 5 times 2 is negative 10, which gives us 2. That goes in the bottom row of our answer matrix. So the answer is negative 14 and 2. Something that's even more complicated is multiplying a 2 by 2 matrix by another 2 by 2 matrix. And this time the answer is not going to be a 1 by 2 matrix, it's going to be another 2 by 2 matrix. So for numbers, let's say we have negative 8, 6, 7, and negative 1, and negative 6, 8, negative 7, and 4. So how do we multiply these together? So again, we're going to multiply the top row of the first matrix by the first column of the second matrix. We're going to multiply together the first numbers. So negative 8 times negative 6. And then we're going to add onto that answer the second numbers multiplied together. 6 times negative 7. That's going to give us 48 plus a negative, so it's going to be a takeaway altogether, 42. And 48 take away 42 is 6. So 6 goes in the top left corner. Then we take the same thing, negative 8 and 6 in the first matrix, and we multiply it by the second row in the second matrix. That gives us negative 8 times 8, and we add on to that the second numbers multiplied together, 6 times 4. That gives us negative 64 plus 6 times 4 is 24, which altogether is going to give us negative 40. So negative 40 is the next number, and that goes in the top right corner. So we've multiplied the top row of the first matrix by both columns of the second matrix, and that gives the top row of our answer matrix. Now I'm going to do the bottom row. So we take the bottom row of the first matrix, and we're going to multiply that by both rows of the second matrix. That's going to give us 7 times negative 6 for the first column, plus negative 1 times negative 7 for the second column. And it's going to give us, for the second column, 7 times 8. Take away the second numbers, negative 1 times 4. So we work these out. 7 times 6 gives 42, so negative 42. Negative 1 times negative 7 is going to be a positive 7. So 42 plus 7 is going to give us 35, or negative 35 actually. So negative 35 goes in the bottom left. It's the bottom of the first matrix, and it's on the left because we multiply the left of the second matrix. For the bottom right, which is now missing, this last one, we've multiplied the bottom of the first matrix by the right of the second matrix. So 7 times 8 gives us 56. Negative 1 times 4 gives us negative 4. And so we combine those, we're going to get 52. If you ever forget what to multiply together, then when you look at the matrix, the first one is going to be up or down, and the second one represents left or right. So if you wanted the top right, which we said was negative 40, the top right would be multiplying the top part, the upper part of the first vector, and the right part of the second vector. The same thing with the previous example as well. The first vector was giving you up or down, and the second vector didn't matter because there wasn't a left or right, there's only one option. Matrix transformations are a faster way to do complicated transformations. Rather than previous methods where you look at the shapes on a graph, maybe use tracing paper. Now, as an example for this, let's say we've got a triangle. And the triangle has got 3 points, obviously. And these will be the coordinates 1, 2, 3, 5, and 4, 4. And let's also join up this triangle. Now, you can represent the coordinates with a matrix. And the way you do that is by using a 2x1 matrix. So let's say you've got the coordinate 4, 4. We could say that is the matrix 4, 4. And if you want to do a transformation to that coordinate, we want to know where that top coordinate of the pyramid, the triangle, is going to be, after, say, rotating it or enlarging it. Then we can multiply it by what we call a transformation matrix. Now, transformation matrices are all derived from an initial matrix that we call the identity matrix. The identity matrix is a matrix 1, 0, 0, 1. And if we were to multiply that by our matrix 4, 4, then the answer would be 4, 4. So that's a matrix where multiplication by it doesn't change anything. And it's useful because we can change it to do all the different transformations that we would want to do. So the identity matrix is initially no change. Now, let's say we want to do some reflections. What we would do is we'd make a change to the identity matrix. So let's say we wanted to reflect in the x-axis. We'd multiply by the matrix 0, 1, 0, 0, negative 1. And you can see from the identity matrix, we've only changed one of the numbers and made it negative. And that's enough to do an x-axis reflection. We can also do a y-axis reflection, and that's by making the other one be a negative. So negative 1, 0, 0, 1. We can also do diagonal reflections. For example, we could reflect in y equals x. And then that would be the matrix 0, 1, 1, 0. So you can see that we've kind of reflected the positions of the zeros and the ones. We also change one of the negative numbers. We do the same thing with the other diagonal, which is y is equal to negative x. And that would be 0, negative 1, and 0. So let's say we want to reflect our triangle in the y-axis. Then we would take each coordinate. So for example, 4, 4 for our first coordinate. We would multiply it by the matrix for that. So for the y-axis, it'd be negative 1, 0, 0, 1. We would do a matrix multiplication, which we already revised. So we would do the 4 times negative 1 added on to 4 times 0. So we've multiplied by the top row. And that's going to give us 4 times negative 1 is negative 4. 4 times 0 is 0. So that gives us negative 4 altogether. We multiplied by the top row. So we get negative 4 as our coordinate. Then we would do the bottom row. So we do 4 times 0 and add that on to 4 times the 1. That would give us 0 plus 4, which is 4. That would be the answer for the bottom row. And so if we reflected that triangle in the y-axis, then the coordinate 4, 4 would be transformed to the coordinate negative 4, 4. So 4, 4 is our original matrix, and negative 4, 4 is from our answer matrix. You'll see that when you reflect on the y-axis, what happens is the x-coordinate has its sign flipped, but the y-coordinate stays the same. So here's an example of it working. Now, there's not just reflections, there's also rotations and enlargements. So let's have a look at those. So first, we'll look at 180-degree rotation. You would multiply it by the matrix -1, 0, 0, and -1. What about 90 degrees? Now we can have 90 degrees anti-clockwise, and we can have 90 degrees clockwise. Let's look at both. So 90 degrees clockwise would be multiplying by 0, 1, -1, 0. And 90 degrees anti-clockwise is multiplying by 0, -1, 1, and 0. Now, there is an alternative to this, and it lies here. What if you don't want to multiply by kind of multiples of 90 degrees? What if you wanted to do 30 degrees or 43 degrees? So an alternative to this is that you can rotate by any angle by using the vector cos theta, negative sine theta, and cos theta. And this is rotating by theta degrees. So you can just remember that one rather than the others. Because of the reflections, maybe you can kind of derive this from thinking about it and thinking, well, I want to change one of the things into a negative, so I've got to have one negative in there. But for rotation, it's going to be a little bit more abstract. So remembering the sine and cos, if you plug in 90, cos 90 or sine 90, it's going to give you the zeros and the ones. So you'll need to remember one for rotation. The last one to look at is enlargement. Now, there's only one really to look at with enlargement. So let's put it in the gap we've got here. So with enlargement, it's going to be A, 0, 0, and A. Now, what's the A stand for? The A is the scale factor. So it's scale factor A. Then you can multiply it by whatever number the scale factor is in those two positions. So let's look at a full example. So let's say we want to rotate 90 degrees clockwise around the center of rotation, which would be 0, 0. And all of these, the rotations and the enlargements, assume that the center of rotation is 0, 0. So you want something else to be the center of rotation. You're going to need to translate your shape to make the center of rotation be 0, 0. Do your transformation and then translate it back. So let's say center of rotation is going to be 1, 1. You would translate your shape -1, -1. Do what you need to do. And at the end, add 1 to the x and y coordinates. So to do that, what we would do is we'd take the 3 coordinates of the triangle. So we've got 4, 4, we've got 1, 2, and we've got 3, 5. And what we would do for all 3 of these is multiply them by the matrix for 90 degrees clockwise. So we look at our list, and it's 0, 1, -1, 0. And it's going to be the same matrix for all 3. Now, I don't have enough room for all the working out, so I'm going to do the working out and only write down the answers. The answers are all going to be 1 by 2 matrices for the coordinates. And so now you can see that I've popped the answers in. And if you drew both triangles accurately on a graph, now I've just got a sketch at the top, it wouldn't actually look like that, but if you drew both accurately on a graph, you would see that will be a 90-degree clockwise rotation around the center, 0, 0. So let's look at the determinant first. So if you have a matrix, we can give the values of the numbers some letters. We call it A, B, C, and D. So if you wanted the determinant, what you would do is you would do A multiplied by D, take away C multiplied by B. And that would give you a number. And that number will be a kind of measure about kind of how big the matrix is, let's say. To find the inverse, again, let's take a matrix and add letters. Now, there are 2 things you need to do to find the inverse of a matrix. The first thing is you need to find the determinant. And you're going to have 1 over the determinant, which would be AD take away CB. You then multiply that by a matrix. And the matrix you're going to multiply it by is a transformation of our original matrix. The transformation you do is that you swap the positions of A and D, and then you make C and D negative. And that gives you the inverse of a matrix. And we can use this to solve simultaneous equations. So let's have a look at a simultaneous equation. So let's say that we have 6x plus 10y is equal to 46, and 3x plus 8y is equal to 35. So we can set this up as a matrix. The way we do that is we have a 2 by 2 matrix for our numbers, a 1 by 1 matrix for the letters, and a 1 by 1 matrix for the answers. So we say that 6 and 10, 3 and 8 are our variables in that order, or rather there are coefficients because our variables are x and y, and the answer is going to be 46 and 35. So we can set it up like this, and this would be a matrix multiplication. Now, if you actually multiplied that matrix using the multiplication rules that we've learned, you would actually derive the original equation. So 6x plus 10y equals 46 is what you would get out of multiplying that together. So what we need to do is find the inverse of that, so we get something that we can solve. So for the inverse of our matrix, we are going to swap the positions of the 6 and the 8. We're going to make the 3 and the 10 negative. We also need the determinant. So the determinant is going to be with AD, so that's going to be 8. That's going to be 6 times 8. I'm going to take away from that C times B, which is going to be 3 times 10. That gives us 48, take away 30, which is 18. So the determinant is 18. So then what we do to solve this is that we write out that x and y is going to be equal to 1 over the determinant multiplied by the inverse matrix. So we're just find the inverse of the matrix basically, and then we multiply that by the old answer, which was 46 and 35. So this is a way of kind of rearranging equations using matrices. And if we did this multiplication, we would get an answer for x and for y. So we've got kind of 3 stages. We start off with our original simultaneous equation, then we change it into the same thing in matrix notation, and then we rearrange it to make x and y be the subject by finding the inverse. So now we have to do the multiplication to solve it. So to find x, we have to multiply an 18 by the top row, because x is the top row, and then by the answers. That's going to give us, so it's going to be an 18th of, so we're going to have 8 times 46 plus negative 10 times 35. So again, it's the first number multiplied by the second number. For y is going to be the bottom row. So we multiply an 18th by the bottom row and the answers. That gives us that y is going to be equal to an 18th of the first numbers, which is negative 3 times 46, plus the second numbers, which is 6 times 35. So now we can work these out. So for x, 8 times 46 is 368. Negative 10 times 35 is negative 350. And that answer, we want an 18th of it, so we divide it by 18. That altogether should give you 1. So we've got some quite complicated calculations there, especially divide by 18. To get a whole number answer out tells us this question has been designed to give us a whole number answer. Do the same thing for y. So negative 3 times 46 is negative 138. We're going to add on to that 6 times 35, which is 210. And whatever that answer is, we need to divide by 18. Notice that I'm not too concerned about the order in which the divide by 18 is in. So I'm just doing it at the end because it's easier for me to do it there. So negative 138 plus 210 divide by 18 gives us 4. So again, to get a nice answer like 4 tells us this question has been designed to give us a nice answer by 4. Last thing to do, it would be useful to write down the answers separately. So we want x is equal to 1 and y is equal to 4. And so now we've got a kind of fourth version of our equation, which has the answers. So to sum up the method, you take simultaneous equation, you convert it into matrices. Then you find the inverse of the coefficient matrix so you can rearrange it. To do that, you need to know how to find the inverse by swapping A and D and making C and B negative. I need to know how to find the determinant. We do AD, take away CB, assuming you label the letters in the way that I do. Once you've found the inverse, you can do the multiplication. Remember to divide by the determinant at the end, and you're going to get your answers. We have 2 graphs. One graph is measuring distance against time. The other graph is measuring speed against time. Another word for speed is velocity. Now, there's a number of things we can read from these graphs. So, for example, from the first graph, we see a journey starting at 0 seconds, and after 1 second, then this object has moved 25 meters, because we can see the kind of height here is 25. Then it moves again for another 2 seconds, and then it ends up here, which corresponds to 45 meters. So we can read off distances from this. We started at 0, we moved up to 25, then we moved up to 45. We can also read off times. So we started at 0 seconds, the object moves, then it becomes stationary at 1 second until 2 seconds. Then it starts to move again, then it's stationary at 4 seconds and continues being stationary until the end. So it looks like there's only 2 different kinds of measurements we can read off these graphs, but it's not true. There's a third measurement. And what we can do is we can read off this speed. And so first, we're going to find the speed of the first journey. Now, you think about the units of speed. If distance is in meters and time is in seconds, speed is going to be in meters per second. And the way we write the measurement actually shows what maths to do. Meters per second, meters divided by second. So with the kind of journey I've highlighted in pink here, it ends at 25 meters and it took 1 second. So we can say that it's 25 meters per second. Now let's look at the units when we do this actually. So 25 meters, we have 1 second. So we divide the numbers, 25 divided by 1 is 25. And we divide the units, meters divided by seconds is meters per second. I've literally written meters divided by seconds. Let's do the same thing for the second journey. And actually, let's highlight this in a different colour. So we need to take the distance. We're going from 25 meters to 45 meters. We're traveling 20 meters. The distance is 20 meters, but the time is going from 2 seconds to 4 seconds. So that's traveling for 2 seconds. So 20 divided by 2 is 10, and meters divided by seconds is meters per second. Now we can also read multiple things from our second graph. So we can see again there's a journey. We're starting at 0 speed, so 0 meters per second, and it goes up to 7.5 meters per second, which we can see at the top here. Then it drops back down to 0 meters per second. We also have the time, so we're starting at 0 seconds. The first journey ends at 5 seconds, then it restarts at 6 seconds, ending at 10 seconds. Now, when I say journey, that's not strictly true, because on the first graph, every time you saw the line not be straight, so the diagonal lines show movement, whereas the bits highlighted in blue, that means that this object is stationary, it's not moving, because the distance is increasing or decreasing. Now, with this one, it's not measuring distance, it's measuring speed. So the diagonal line showing the speed changing, and the bit highlighted in blue is when the speed is stationary. So actually the object is moving for the entire time it's on here, for the entire 10 seconds of movement. It's just showing the changes in speed. Now, how do we show changes in speed? Well, changes in speed is meters per second squared. Now, you might notice another way of writing these things. So, for example, the meters per second can be written as meters per second to the negative 1. So meters per second squared can be written as meters per second to the negative 2. I'm just using the laws of indices here to rearrange this. A power that's being divided can be written as a negative power instead of divide. So let's find the meters per second squared, which is acceleration. So we should also label this as well. Acceleration is the rate at which the speed is changing. And for speed, let's write velocity for this, which is kind of the technical term for speed. So look at the units for acceleration, meters per second squared, meters divided by seconds twice. So what we need to do is get our velocity we've already divided by seconds and divide by seconds for a second time. So let's have a look at the first change in velocity. What is the acceleration of this line? So the speed goes up to 7.5 meters per second, and we divide it by the number of seconds it takes, and it goes up to 5 seconds. So we do the numbers. 7.5 divided by 5 gives us 1.5. And then we do the units. We've got meters divided by seconds on the numerator, but then we're divided by seconds again. So meters per second squared. We're divided by the speed twice. Once is already baked into the velocity. And we saw how to do that on the first graph. And then the second is divided by speed for a second time to get the acceleration. So every second, the speed is getting 1.5 meters per second faster. We can do the same thing for the second part as well. So we're starting at 7.5 meters per second and we're ending at 0. Now what I should do really here is rewrite the first question. Going with the 7.5 meters per second, because we started at 0, I didn't actually bother to mention the 0. What we could have done is written our end speed, 7.5, take away our starting speed, 0, and write it like this. And this is how we get the 7.5 meters per second. So when we go in on the next one, we're starting at 7.5 and we're finishing at 0. So you're writing finishing point first and your starting point last. Then you divide that by the time, which is going from 6 seconds to 10 seconds. So that altogether is 4 seconds. Now, why am I bothering to go through this with 0 take away 7.5 gives us negative 7.5. And dividing that by 4 gives us negative 1.875 meters per second squared. So this does two things for us. The first thing is it gives us a negative number for the 7.5. That means that our second change in velocity, the second acceleration, is negative. That shows it's slowing down. So the first journey is speeding up 1.5 meters every second. And the second part of the journey is decreasing in speed. It's going slower by 1.875 meters per second every second. The other thing it does for us is these graphs start at 0 and ending somewhere else. You could always have these graphs that don't start at 0. So the object's already in motion. Then you look at the change of velocity, you say you could be between, say, 3 meters per second up to 7.5 instead. So if we just do a dotted line here, we could have started here. And if we did that, then we need to be taking away the 3 from our original calculation, because the acceleration will be slower if we're already moving at a speed. Now, there's actually one more thing we can do with this graph. So we've read off it time, we've read off velocity, we've calculated acceleration. Well, what about distance? Because we've got meters per second, on the velocity. So can we find meters? And again, it's all about looking at the units. If velocity is meters per second, meters divided by seconds, then if we multiply by seconds, we're going to be undoing that and getting just the meters. So we can find the distance travelled as well. So for the first part, if we have 7.5 meters per second, and then that's lasting for 5 seconds, we can multiply by 5 seconds. So you see you've got divide by s, and now we're doing a times by s. And so that's going to give us just meters. And so that'll be 7.5 times 5, which is 37.5. Now, if the answer is 37.5, we're assuming here that our speed was 7.5 meters per second for the entire amount of time. And if you think about it here, we've done a base times height, where the base is 5 seconds and the height goes all the way up to 7.5 seconds. So what we found is this highlighted pink area here. Now you'll notice the line's going through the middle of it. And the reason for that is because it's not a constant speed. We're not starting at 7.5 meters per second. We're starting at 0 meters per second. But look at this area that we've found, 37.5. Look at the line through the middle. It's splitting it up into 2 triangles. Now we know how to find the area of a triangle. We can divide by 2. All we need to do is take our answer and divide it by 2. So 37.5 divided by 2 will give us 18.75 meters. We can do the same thing with the deceleration as well. Now again, we see it starts at 7.5, but it's going down to 0. So we can do base times height, but we need to divide by 2 at the end because this is still going to be a triangle shape. So we take the maximum speed, 7.5 meters per second. It's going down to 0. So to average it out, we need to divide by 2. I'm going to multiply by the time, which was 4 seconds for this one. So 7.5 times 4 divided by 2 is going to give us 15. So we're traveling 18.75 meters speeding up, and we're traveling 15 meters slowing down. Now, what about the middle section? We haven't highlighted the middle. Now, if we colour this in blue, we can see this isn't a triangle shape. This is a full shape. And at the top, it's actually a constant speed. So for that 1 second in the middle, our 7.5 meters per second for 1 second is a constant speed. So we don't need to kind of divide it and do any calculations to adjust for the speed going slower. It's just going to be 7.5 meters. There's going to be no adjustment to it. And now we've got all 3 of these numbers. We can add them all together and we can get a final answer for the amount of distance travelled. So we do 18.75 plus 7.5 plus 15. And altogether, that's going to give us 41.25 meters. let's label that as going to be the distance travelled. So in total, we could read 4 things from this graph. We could read the velocity directly from the graph. We could read the time directly from the graph. We could do some calculations and divide velocity by time to get acceleration. And we could do some calculations and multiply velocity by time to get distance. SUVAT is a system of equations that help you find different variables considering other variables being missing. And the first thing to talk about is what SUVAT means. S stands for space. U stands for initial velocity. Now you might think, well, why is that? There's no U there. But when you look at V, which is final velocity, clearly V is named after velocity. And U is also named after velocity, so you can't have 2 V's. So what's happened here is they just use a letter before V because the initial velocity is before the final velocity. So they use 2 letters next to each other for velocity. A is acceleration and T is time. Now, the odd one out here is that people don't usually use the word space. They use the word distance or displacement. So let's use distance. So if you ever wonder why distance or displacement isn't D, it's because it's named after S for space, or rather the word for space in Latin when these equations were first used. Now, what are the equations? So the final velocity is equal to the initial velocity plus the acceleration multiplied by time. The square of the final velocity is equal to the square of the initial velocity multiplied by 2 lots of the acceleration multiplied by distance. The distance is equal to the initial velocity multiplied by time plus half of the acceleration multiplied by time squared. Distance is also equal to the final velocity multiplied by time, take away half of the acceleration multiplied by time squared. And the distance is also the half of the initial velocity plus the final velocity plus time. So these are the SUVAT equations. And to make it more complicated, we have 2 follow-up equations, which will make this more difficult. So for the velocity, or for the final velocity, we can say that's equal to ds over dt. That means if you differentiate distance and time, you're going to get the final velocity. And then if you differentiate it for a second time, you actually get the acceleration, which we write d2s by dt squared. So that's just a differentiation notation for the first and second differential. So let's look at some examples. So let's say we have the distance, which is 14 meters. We have the final velocity, which is 6 meters per second. And we have the acceleration, which is 0.9 meters per second squared. So what you need to do is look through each one of these equations and think which one has got these 3 variables. So going through them, let's have a look for S's. So we've got a S here, and then we've got our 3 equations that are looking for S. Then let's look for V, final velocity. So we've got the 2 that look for final velocity, and then we've got 1 here and 1 here. Then let's have a look for acceleration. So we've got acceleration in most of these, but not the last one. So looking through these, we've got to think which one has got all of the variables we have. Now we've got 2 that have all the variables, so we need to know what we're looking for. And our objective here is going to be to find the initial velocity. So I'm going to go through, I'm going to highlight U for initial velocity. And now we're looking for an equation that has every single variable highlighted. So most of these are missing time, but the second one doesn't include time. So that's the one we're going to use. So that's going to be V squared is equal to U squared plus 2AS. So when we substitute, that's going to be 6 squared is equal to whatever U is squared plus 2 lots of 0.9 times 14. So now we need to solve the equation. So 2 times 0.9 times 14 gives us 25.2. 6 squared will give us 36. So we're going to have 36 is equal to x squared plus 25.2. So we take 25.2 away from both sides, we're going to get that x squared is equal to 10.8, and therefore x is going to be the square root of 10.8, which is going to give us 3.3 to 1 decimal place. And the units for the velocity is going to be meters per second squared. For our second example, we're going to have that the distance is equal to 2t cubed plus 2t plus 5t plus 5, and t is equal to 6 seconds. So we've got an equation for the distance. Now this is telling us that we're going to be using one of the ones where we have to differentiate. So from this, we could be asked to find either the final velocity or the acceleration. So let's say we're going to find the velocity. We're going to differentiate once. So we bring down the power and multiply it by the coefficient at the start. So 3 times 2 is 6, and reduce the power by 1. For the next term, the power 2 times the coefficient 2 will give us 4, then reduce the power by 1. So power 2 becomes power 1. The next one, we've got 5 to the power of t to the power 1. So 5 times 1 is 5. And reduce the power from 1 to 0. When you do that, the letter is going to disappear, because that'll be t to the power of 0, which is 1. So we get 5 times 1, which is 1. And we differentiate, any kind of whole numbers are going to disappear, because that's going to be 5t to the power of 0. And so we do 5 times 0, which is 0. You multiply by 0, you don't need to write that down. Then we can differentiate another time for the acceleration. So multiply the power by the coefficient. 2 times 6 is 12. Reduce the power by 1. And 4 times 1 is 4. Reduce the power by 1. And now we have an expression for the acceleration. Now we still have equations, so don't we want a solid value out of this? Well, we're told we want this when time is equal to 6 seconds. So all we do is substitute in 6. So for the velocity, we're going to have 6 squared times 6. We're going to add to that 4 times 6, and we're going to add 5 to that. And that gives us 245. And it's a velocity, so that's going to be meters per second. For the acceleration, we've got 12 times t, so 12 times 6, and add on 4. That gives us 76, and that's going to be meters per second squared. One last detail with this is that you can also do this in reverse. So you can differentiate the distance to find the final velocity and the acceleration, as long as your equation is in time. But you can also integrate. So if you were given an equation for the acceleration, you could integrate that to find an equation for the velocity, and integrate that for a second time to find an equation for the distance. And then again, you'll be substituting in the numbers you're given for time. So if you're only given 1, it'll be 6 and 0. So have a definite integral, substitute in 6 and take them away from each other. If you have 2 different times, then substitute in both and take them away. So let's have a little hour to show this. So we can go from distance, and here we are differentiating. But we can also go in the other direction, and that's going to be integrating. With vector diagrams, you can describe any coordinate on the grid using vectors. Now we've got 2 vectors labelled for each one. So for our first diagram, we have the vector A and we have the vector B. And every description you make needs to be in reference to A and B. So let's say you wanted to describe the position between A and C. You'd write A to C is equal to, and you can see from A to C, it's the length of 2 A vectors. So we'd write 2 lots of A. Because with these diagrams, typically all the lines are parallel and the same length. So you can say that if AB is A, then BC is also A. Now, let's say you wanted something to use a combination. So let's rub out our working out so far. Let's say you wanted to go from A to K. So we can go on a journey, go down A, and another A. So we've gone to A, and then considering what vector B is, we can do a vector B and another vector B. And you can see those 2 green lines are parallel and the same length as the vector B line. So we'd say that AK is equal to 2 lots of A and 2 lots of B. Now, for our last example, we'll do something a little tiny bit more complicated. So let's say you want to go from L to O. And the direction with the arrows is very important here. You have to start at L. So we've got 2 options. We could go backwards down vector A. Now, if you're going the opposite direction to vector A, then we don't call it A, we call it negative A. And then we're going to go the same direction as vector B. And we can see they look like they're going to be parallel and the same length. So what do we write down for this one? So you've got a few options. You could write negative A and then plus B, and that is a perfectly valid answer. Or what you could do is, if you write them the other way around, you don't write the positive sign at the start of a sentence. So we could write B, take away A, and by swapping the positions, we don't need to write the plus, and so use less characters to write it out. Now, you might think there's more than one way to do this. We could go from L, we could go downwards to P, and then across to O. Now, L to P is parallel to B, and P to O is parallel to negative A. So even if we went the other way around, it would still be the same vectors and the same answer. Now let's look at our second example. So again, we've got a vector A labelled and a vector B labelled. So we can say things like, if we want to go from A to B, then that's a vector A. If we want to go from A to D, that's going to be 2 lots of vector B. And if we want to go from, say, C to E, let's look at that one in more detail. We'll start at C, we're going to end at E. It doesn't matter which way we go, we'd have to go backwards down vector A, and then we'd have to go forwards down vector B, and then backwards down vector A again. Let's talk about this in a bit more detail. Let's just look at that journey. So we've got the reverse of vector A twice, because we're going in the wrong direction, going backwards down vector A, and we're going forwards down vector B. So we could write that as B, take away 2A. Now, you might have thought, well, why can't we go down this diagonal route? Wouldn't that be faster? We go down 2 lines rather than 3 lines. Now, the answer is that we cannot go down that line because we do not have a vector to reference it. We've not been told what vector that is. We've been told what A and B are, and we can go in those directions or in the opposite direction to those, but we can't go in this other direction that's not labelled A or B. We can't use it. Now, we can define that direction. That's from C to D. And if you wanted to go from C to D down that line, you'd have to go around. So you'd have to do the negative A and then the plus B. And so we can label that pink line. It would be B, take away A. And then if you did want to use that line in future, you'd have to label it as B, take away A. So from C to E, we do B, take away A, and then we do another minus A. And it will just give us the same answer, so it wouldn't make a difference. Now, the last thing we'll look at are midpoints. So let's say in our third diagram, we want to go from N to the midpoint of O and P. So let's label that with M for midpoint. So how would we do that? So you could think, well, we could go down vector X, but then we don't have a value for going down M, halfway to M. We could go down vector Y, but again, we don't have a value for going halfway down M. So how can we do it? Now, the trick here is not to think about going directly to M. What we could do is we could go from vector P, from point P to point O. Now, M is halfway down that line, but there is a route between O and P. Let's say we're going to start at O and go to P. We can't go direct because we don't have a value for it. So we would have to go backwards down vector X. So that'll be negative X. And then forwards down vector Y. So we'd call that Y minus X. Now we know what OP is. It's Y minus X. We can now find OM. OM is halfway down that line. So the vector OM is going to be half of Y minus X. So it's going to be half of Y, and we're going to take away half of X. And so now we've got a value for that. So we want to go from N to M. We would do N to O, which is X, and then we do O to M, which is half of Y minus half of X. So we can actually write it out as NO plus OM. So we're going to do some working out up at the top here. So we've got NO, which we already said was X. We've got OM, which is negative half of x and positive half of y. And so we can do the maths with that. We've got x plus half of y minus half of x. So we've got two x terms. X take away half of x will be half of x. And then we only have one y term, which is half of y. And so that is going to be what n to m is. Now, if you look at that on the diagram, you can see that half of x plus half of y is actually in between x and y. So there's some relation between the maths and what you see in the diagram as well. You can see it's physically in between those two lines. With magnitude and direction of a vector, we've got a few vector diagrams here. Now in each one, when you see the numbers that's on the end of the arrows, these are the magnitudes of each vector. And so when we say magnitude, what we're saying is the length of the vector. Then we've also got the directions. So when we've got an angle with degrees, these are all the direction of the vector, which is the angle. Now, there's different ways to define the direction. So in our first diagram, the direction is from the x-axis anti-clockwise. You can also have things like bearings, which are from the y-axis clockwise. So it depends what you're looking at. This is kind of what we call a polar coordinate, where you might use the x-axis anti-clockwise. You'll see that not all the angles here follow that. Now, there's other things we can find out. So when we know the direction, we might want to know how long this line goes in the x and y axes, because the length doesn't reference the x or y axes. The direction kind of tells you kind of where it is in between the x and y axis, but not how far in either direction. Now, the way we can do this is we can turn this line into a triangle. The triangle is going to have a right angle in it, so we can use trigonometry. The y direction and the x direction are on this triangle, and you might need to adjust the angle. So, for example, this angle here isn't going to be 71 degrees if we do the triangle this way around. We're going to add together to make 90, and this will give us actually 29 degrees. But we could make an alternative triangle that has a 71 in it and have the triangle going downwards instead. But that'll overlap what I've written already. So I'll do it this way. Now, in this particular triangle, we can see that y is the adjacent and x is the opposite. And we know what the hypotenuse is. The hypotenuse is going to be the magnitude, which is our 4.2. And so using trigonometry, we can figure out what x and y are going to be. The x difference, the horizontal difference, is going to be the magnitude multiplied by cos theta. Now, what do we mean by r? Well, r is the letter we can use to describe the magnitude. What do we mean by theta? Theta is a letter we can use to describe the angle. The y distance, the vertical distance of the line, is going to be y sine theta. So the magnitude multiplied by the sine of the angle. So these are the basic things that we need to know. So now looking at our second example underneath, let's actually do a calculation as an example. So you want x is going to be equal to r cos theta. That'll be 13.9 for the magnitude. Then cos, and theta is going to be the angle. Now we want the angle from the x-axis, so 70 degrees is going to do just fine for us there. We work that out in my calculator. 13.9 multiplied by cos, open some brackets, type in 70, close the brackets, and I get a value which is 4.75. So that's the distance in the x direction. We also want the direction in the y direction. So y is going to be r, which is still 13.9. This time it's going to be sine theta, but theta is still going to be 70. So just changing the trigonometry word we use it from cos to sine. And that gives me a value of 13.06. So now we know how far up the line goes, how far across it goes, and we know the length of the line, which is 13.9. Now the length is kind of the hypotenuse of this, so the length should always be longer than the x and the y lengths. Now, what if we have something like a third diagram, and we can see for this one, we've got a much, much larger angle. Now, we're going to follow the same principles. X is going to be this time it's 12.9, multiplied by cos theta. But for the theta, what we want a measurement from the x-axis. So theta is going to be from the x-axis, and it's going to be the closest angle, because technically the 144 also comes from the x-axis, but it's on the opposite side. So if we have 144 for the kind of full angle, it's going to make 180 degrees with a full half turn. So to get up to 180, it's going to be another 36 degrees. So we're going to use 36. So we can type that into our calculator, 12.9 multiplied by cos 36. And I get a value of 10.44 to 2 decimal places. Then we can look at y, do the same thing. So it's going to be the same magnitude. It's going to be the same direction. We're changing cos into sine. You can literally just press the back button on your calculator, highlight cos, and change the sin, press equals. And I'm getting 7.58 to 2 decimal places. The magnitude is larger than either of those two measurements, which it should be because it's a hypotenuse. Now, there's one more detail that I haven't gone through here, and it's the direction. Now, in this example, you see the x distance is actually on the negative side. And so with x, we don't write 10.44. We're going to write negative 10.44. It's the same thing with the previous example as well. It shouldn't be 4.75 at all. It should be negative 4.75 because it's going towards the negative side of the x-axis. And in both cases, the y values are going upwards, so they will stay positive. So we take an angle from a reference point on the x-axis. You're not really telling the trigonometry on which point of the circle it is. It could be the top left corner, the bottom left corner, top right, bottom right. So what you need to do is look yourself at the graph and decide if it's going to be positive or negative. Now we can do a little key for this. So let's put the key at the top. A lot of room, so let's just see what we can do. So we're going to have an x-axis and a y-axis. We should label them. So if you've got a coordinate in the top right, then you're going to have a positive x and a positive y. If it's on the left-hand side, it's going to be a negative x and a positive y, just like we've been doing. Below that, you have a negative x and a negative y. And in our next example, we're going to look at a positive x and a negative y. So let's look at that example. Now, again, we've got an angle 306 degrees, but we want an angle from the x-axis, from the closest point on the x-axis. So obviously, going clockwise to it is going to be shorter than the anti-clockwise route we've got here. Now, this makes a full circle. So we do 360, take away 306, and that'll give us 54 degrees. Now, it's worth pointing out in our first question, the two angles add up to 90 degrees. And I kind of did the triangle the other way around with that. But if you actually sketch it out, values might be the other way around perhaps, but you can sketch it out and work it out. For a second and third examples, they added up to 280. In fact, the second example is given to us already, but the third one, they add up to 180. And our final one, it adds up to 360. So it's not always going to be the same number you're taking away from. You've got to draw the diagram. You've got to kind of figure it out from the diagram. But it's going to be on our x-axis. It's going to be the magnitude, 11.3, multiplied by cos, and multiplied by the angle, which is 54. 11.3 times cos, 54, and we get 6.64 to 2 decimal places. Same thing with y values, going to be 11.3. This time it'll be sin, but it's still 54. So now if we press the back button on our calculator, change the cos into a sin, or write it out from scratch if you prefer, and get the value 9.14. But you see that this arrow is going downwards from the center. So it's going to be a negative 9.14. So you've always got to look at what direction the numbers are going in from the center. Left or down will give you a negative answer. Vectors can be written out in different kind of formats. They can be written as a diagram, but you can also write them as vectors. So for example, we could have the vector negative 28, 21. And we could write that as an equation. And we write that as negative 28i plus 21j. And so you can use what you normally say, the x and y coordinates. You'd also might see them as I and j coordinates as well. So we call these I and j vectors. Now, what we don't know from this is the magnitude or the direction. So that'll be the first thing to find. So with the magnitude, you might remember that these kind of form part of Pythagoras' theorem. If you've got the x and the y coordinates, then you kind of want the distance in between, which will be a hypotenuse. So we need to use Pythagoras' theorem. I'm going to take 28 squared, add on to it 21 squared, and we're going to square root the answer. You might be wondering that I made a mistake here. I didn't put the negative symbol into the 28, but it doesn't matter. because if you square negative 28, you get the same answer as squaring positive 28. So there isn't really much point writing in the negative symbols when you're squaring them anyway. And that's giving me an answer 35. That's the length of this vector. And it might be useful drawing a diagram for this. So we drew a diagram. Let's draw an x and y axis. We know the x-axis is going to be negative, and then the magnitude is going to come out in this direction. So let's label this, and what we're going to get is a kind of triangle like this. The x distance is going to be a negative 28. The y distance is going to be a 21. And then the length of the arrow is going to be 35. And what we're looking for now is going to be the angle of this. So let's find that next. So the direction. Now, the previous revision slide, when we were doing this, and we did cos theta and sine theta to find the x and y coordinates, when we're working backwards, what you're going to get is you're going to get tan to the -1, and it's going to be y over x. And that's going to give us our angle theta. So what values do we put into this? So y and x are going to be corresponding to the I and the j. We've already drawn it on the diagram, actually. So it's going to be tan -1. Our vertical value is 21. Our horizontal is the negative 28. We can type that into our calculator, inverse tan, 21 divided by the negative 28. And I'm getting, for the angle, negative 36.9 degrees. Now, I'm not too concerned about that being negative. I'm just concerned about the 36.9. And what we found here with the 36.9 is the angle was shaded in blue. Now, what we actually want for the direction is going to be from the positive x-axis, and we want the angle all the way around. Now, you see the two angles make 180 degrees. So 180 take away our answer is going to give us 143.1 degrees. And let's just highlight that in another colour. Let's highlight it in purple. Now, which one you give depends on how you're arranging the directions. So if using polar coordinates, you might want to say it's from the x-axis in the anti-clockwise direction, which is the 143.1. If it's bearings, then you want it from the x-axis, from the y-axis going clockwise. So you'd add on 270 degrees onto this. So then you'd have your 36.9 plus 270, because we're going through kind of 3/4 of the graph to get there, and that'd be 306.9. So you're going to frame the angle you're given in terms of what the question is asking you for. It's asking for bearings. Is it going to be asking for from the x-axis anti-clockwise? Read through the question carefully. Now, there are a few bits of vocabulary we need to know. The first bit of vocabulary we need to know is going to be parallel. Now, let's say we're looking for a parallel vector to the one that we've just used. And so we want a vector parallel to negative 28i plus 21j, but it's going to have a magnitude of 175. So r is going to be equal to 175. So how can we do that? Well, for a parallel line, all you have to do is find the magnitude of the actual vector you've been given, which we know is going to be 35. And so to get from an r value of 35 to an r value of 175, if you divide them, you get 5. So you need to multiply by 5 to get from the original r value to the new r value. That means we multiply the vector by 5. So you negative 28 times 5, which is going to be negative 140i, and we multiply 21j by 5, which gives us 105j. And then I'm just going to colour code this. Let's swap those colours around. So if you want our new magnitude to be 175 and our old magnitude is 35, then what we need to do is to multiply our magnitude by 5 to get there. So then we multiply the vector by 5 as well. And that will get us our new parallel vector. The next piece of vocabulary we need to know is collinear. So let's say we've got 3 vectors. We've got vector A, which is I plus j. We've got vector B, which is 3i minus j. And we've got vector C, which is 6i take away 4j. So how can we prove these are collinear? Well, collinear means they're all going to be on a straight line. I'm going to check the difference between these. So firstly, we're going to check AB. AB is the distance between A and B. A to B, the i's is from 1i to 3i, which is 2i. And the j's is from 1j to negative 1j, which is taking away 2j's. Then we could look at B to C. So from B to C, 3i to 6i is going to give us 3i. And negative 1j to negative 4j is going to be negative 3j. And what we can do with these is we can factorise. Now we can take a 2 out of both in AB, which gives us 2 lots of I minus j. We can take the 3's out of BC, which gives us 3 lots of I minus j. And you can see they've both got a multiple of the same I and j vector. And so we can say that therefore I minus j is a factor, therefore it's collinear. A, B, and C are collinear. The last thing we've looked at is making vectors larger. We're finding parallel vectors which are larger. So we had a vector that's 5 times bigger. What about making vectors smaller? Now we have something called a unit vector, and a unit vector is a vector with a magnitude of 1. So in a unit vector, R is going to be equal to 1. So let's say vector P is equal to negative 28i plus 21j. So this is the vector we looked at before, our previous example. If we want P with a little triangular hat on, that is the unit vector, and it has a magnitude of 1. How do we make a vector have a magnitude of 1? Well, all we need to do is divide by it. So to go from a magnitude of 35 to a magnitude of 1, we need to divide by 35. So we take the 28, the negative 28, and divide that by 35. And we take the 21 and divide that by 35. We can simplify the fractions. These are all in the 7 times table. So that'll be negative 4/5 I plus 3/5 j. And that's our unit vector with a magnitude of 1. So you see, it's a similar method to finding a parallel vector with a larger magnitude. So rather than multiplying by 5, we divided by 35. But otherwise, it was the same method. And that was going to give us answers smaller than 1. So I kept the answers as fractions. We could change decimals if that'd be relevant and have negative 0.8i plus 0.6j. But I think the answers look better as fractions. The first force we'll look at is in equilibrium. And what equilibrium means is that the kind of state of this object and the forces on it are not going to be changing. So for example, at the top, we can see that it says it's moving at 2 meters per second in that direction. So that's not going to change. Now, if there's no change, that means we can work out some of the missing forces on this diagram. So let's look at R. R is going to be equal to the 2 forces opposing it. Let's highlight force R. Against it, we've got 20 newtons pushing down and another force of 20 newtons pushing down. Altogether, that's 40 newtons. So R has to be the same strength as the 20 newtons and the other 20 newtons, which means that R has to be 40 newtons. Now you might be thinking, well, that means that R is equal to the forces against it. Now, if it's accelerated upwards at 2 meters per second, shouldn't the force of R be larger? Now, it's true that in the past, that force would have been larger to make the object accelerate in that direction. However, now that we're in equilibrium and there's no change, now the forces are equal. And so if the up and down forces are the same, whatever speed the object's at will stay. If it's stationary, it'll stay stationary. If it's moving, it'll stay moving at the same speed. If R set to get larger, then it would accelerate and then reach equilibrium again. If R was smaller, then it will start to decelerate until equilibrium was reached again. We can do the same thing with F. So with F, we've got 50 newtons on one side, on the left, and 50 newtons on the other side, on the right. So that means with F, it's already balanced. We already have 50 on both sides, so F must be 0. So the force on F side, and we're taking away the force on the opposite side, then we get 0 newtons. So whatever force F was, it's no longer active. Nothing's happening with force F. We can write equations to show that it's in equilibrium. So we can write that R, take away 20 is equal to 0. And we can write that F plus 50, take away 50, is equal to 0. So this shows that the forces are in equilibrium. It's just another way to write the equation. And again, you can see that R must be 40 to make it be true that it's all equal to 0. And F must be 0 to make the expression true be true and make it all equal to 0. Now, where things get more complicated is when an object isn't in equilibrium, which is our second diagram. Now, what we can do with our second diagram is I'm going to draw a new diagram for this. I'm just going to try to find the overall forces for this. So let's look at the horizontal forces first. We've got 90 newtons to the left, and we've got 40 newtons to the right. So altogether, that's going to resolve as being a 50 newton force to the left. So I simply took the 90 and I took away the 40. Then let's have a look at the vertical forces. So we've got 70 downwards and 40 upwards. So 70 take away 40 is going to give us 30, and it's going to be going downwards. So this gives us an idea of the forces acting on the object. They're not in equilibrium, so this object is going to move. Now look at those two arrows. That means the object is going to be moving in this kind of direction. It's not going to move, to the left and then move down. It's going to move to the left and down at the same time, following the path that I've shown in purple. So what we might want to know is what's the force in that direction? Or we might also want to know what's the angle of that force. So the first thing is going to be for the kind of force of this. Now, for this, we want something called magnitude. Magnitude is how powerful the force is. And what we can do for the magnitude is we can kind of draw a diagram of what's happening here. So we've got a force going 30 newtons down and a force going 50 newtons to the left. And we want to find the force that I've highlighted in purple. Now, we have a triangle here. And so, because we have a triangle and the horizontal and vertical forces are at a right angle to each other, because that's a definition of horizontal and vertical, they're at right angles, we can use Pythagoras' theorem. So we can do 30 squared plus 50 squared and square root the answer. So a squared plus b squared equals c squared. And when you find c squared, you want to square root it to get what c is. So if we do that calculation, the answer you're going to get is going to be a 58.3 Newton force to 1 decimal place. The next thing we want is going to be the angle of this. Now, again, we look at our little triangle here. The angle that we want, I'm just going to highlight in this kind of purple colour. We want to find this angle. And we're going to find our answer as a bearing. So with a bearing, we find our angle from north. And so actually the angle we want is going to be going all the way around like this. That's quite a large angle. So to start with, we only focus on the part of the angle that's inside the triangle. And for this, we can use trigonometry. Now, what do we have here? Well, we've got the adjacent is going to be the 30. The opposite is going to be the 50. And the hypotenuse is the magnitude. Now, while we've worked out what the magnitude is, we could use it in this equation. It's easier just to use the two numbers that we've got. Now, you think about SOHCAHTOA. The one with A and O in it is TOA. So what we want to do for the angle, let's call it bearing. We'll call it angle first, and then we'll call it bearing later on. For the angle, we want the inverse tan of the opposite over the adjacent, because it's TOA, O over A. And if you type that into your calculator, you're going to get 59 degrees. So then we want the bearing for this. The bearing we have to start measuring at north. And we can see that in the top right and in the bottom right quadrant, that makes a 180 degree angle. And then we add on the angle that we've just found. So the bearing is going to be 180 plus 59, which will give us a bearing of 239 degrees. So from our initial diagram, we've worked out the direction of the forces overall, which is a 239 degree angle from north. And we've worked out the force, which is 58.3 newtons along that angle. So basically, we combine together all the forces to get a single force to work out which direction the object is going to move and with which force. But we can only do that if there is no equilibrium. We know there's no equilibrium because the forces to the left and right and the forces up and down are not equal to each other. A really important equation is that force is equal to mass times acceleration. So let's write down what all these letters mean. So F is force, M equals mass, and A is acceleration. So looking at our first question, we've got an acceleration labelled. We know it's acceleration because it's meters per second squared, and we have a mass, which is 40 kilograms. So we can use the equation. Force is going to be equal to the mass, 40, multiplied by the acceleration, 1, which gives us altogether a force of 40 newtons. Now, if we draw a little diagram here, 40 newtons is the overall force of the object. It's going to be going in the same direction as the acceleration. Now, we haven't been asked for the overall force of the object. We've been asked for x's. Because there's two forces acting on the object, x and 10. So if the overall force is 40 newtons, that's made out of the x pulling in the same direction as the 40 and the 10 newtons pushing in the opposite direction. So we take it away, it's going in the wrong direction. So if we solve this equation, x must be equal to 50 newtons for the overall force to be 40. Because if x is 50 newtons, 10 newtons is cancelling it out by going in the opposite direction. And so the overall force is going to be the 40. Now that important equation, force equals mass times acceleration, can be rearranged. So one rearrangement is that you can get acceleration on its own by dividing both sides by mass. So that would be that the acceleration is equal to the force divided by the mass. And so we're going to find the acceleration of the object I've just written that next to with the 20 kilograms. So 20 kilograms is going to be our mass. But what about the force? We have 4 forces. So what we're going to do is try and combine these forces. So we'll draw a little diagram. First, let's look at the horizontal force. We've got 40 in one direction and 10 in the other. So that's going to cancel out to be 30 newtons. Then let's look at the vertical forces. We've got 80 up and 40 down. That'll cancel out to be 40 upwards. And what we might want here is we might want the force that's in between. We might want a single force for this. So to find that single force, we could write this as a triangle. So we have a force going 40 newtons upwards. We have a force going 30 newtons to the left. So as a triangle, the thing we're looking for would be the hypotenuse. And the vertical and horizontal forces are going to be at a right angle to each other. So we can use Pythagoras' theorem here. So the force is going to be equal to the two sides squared, a squared plus c squared, and then square root c squared. So if we work that out, 30 squared plus 40 squared is 2,500, and square root it, we'll get the overall force, which is 50 newtons. So now we can find the acceleration. The acceleration is equal to force divided by mass, which would be 50, divided by the mass 20, and 50 divided by 20 is going to give us 2.5. Its acceleration to be meters per second squared. Another thing we could do here is we could find the individual accelerations, vertical and horizontal, because what we've got here is a combined acceleration. So for the vertical acceleration, that's 40 newtons. So let's call these I and j vectors. So j vector would be vertical. So that would be force 40 over mass 20, which will be 2 meters per second squared. And then I, which we'll say is the horizontal, that was 30 newtons altogether. So we divide that by 20, and that's going to give us 1.5. So now we can write this as I and j vectors as well. So we could say the acceleration is 2.5 meters per second squared, or we could say that the acceleration is equal to our I vector, which is going to be negative because it's going to the left, negative 1.5 I plus 2j. It's going upwards, that'll be positive, and then that'll be meters per second squared. And you might be asked for either. You might be asked for an overall acceleration, 2.5 meters per second squared, or you might be asked for individual horizontal and vertical accelerations. Horizontal acceleration 2, going upwards. So always be aware of which one you're being asked for. You're being asked for a combined acceleration or for separate horizontal and vertical accelerations. The last rearrangement is that we can make mass the subject by dividing both sides by the acceleration. So mass is equal to force divided by acceleration. Now we do have an acceleration here. It's 1.05 meters per second squared, but we've not been told which direction it goes in. And the forces, again, we've got lots of different forces on this, so we're going to have to try and resolve them into a single force. So I'm going to draw a little diagram again. If we look at the horizontal forces, we've got 20 and 80. So 80 is the biggest one, so it's going to be at 60 to the right. Then looking at the vertical ones, we've got 50 up and 30 down. So altogether, that'll be 20 upwards. So we're going to want the force that goes in between. So again, we can visualize this with a triangle. So our triangle is going 60 to the right and 20 upwards. And we want the hypotenuse. Horizontal and vertical forces are at a right angle, so we can use Pythagoras' theorem. So the force is going to be equal to the square root of 20 squared plus 60 squared. And so that force gives 20 squared plus 60 squared, we get 4,000. And with square root 4,000, the force is going to be 63 point, let's do 0.2 to one decimal place. So where mass is equal to force times acceleration, then mass is going to be equal to our 63.2. Now that was rounded, so I'm just keeping the full value of my calculator, so it's going to be more accurate. Divided by the acceleration, 1.05. And working with full accuracy for the force, and divided by 1.05, I'm going to get a mass of 60 kilograms. It's the nearest whole number. I'm actually getting at 60.2 if you're going to do one decimal place. So we've looked at the equation, force is equal to mass times acceleration, and we've looked in the ways it can be rearranged so you can find any one of the three variables. Looking at forces on inclined planes, firstly, there's information on the diagram. So we know that our first inclined plane is at 36 degrees. We know that our object is 40 kilograms, and we have a coefficient of friction. Now, for our first example, the friction is going to be 0, so we're not going to actually look at the friction for this one. We'll look at friction for our second example. Now, if the object is 40 kilograms, that means that the downward force due to gravity is going to be 40 multiplied by gravity, which is 9.8. So gravitational constant, it's always going to be 9.8 on Earth. Now, using trigonometry, we can work out the force on the object going downwards. This is the resistance of the slope against the kind of the weight, the mass of the object. So this is going to be cos of the angle multiplied by the force of the object downwards, which is 40g. And when we work this out, we should get 317.1 newtons. So that's the force the object is exerting on the slope. Now you might be thinking, well, why are you looking at a force that's kind of perpendicular to the slope like this? Because this force is at a right angle to the slope. Well, the force going downwards, the 40g equal to 392 newtons. So what's happening here is the force downwards due to gravity is 392, but the force of the object against the slope is only 317.1. So the missing force, that's the force that's going to be going downwards. So the object's going to slide down the slope. Now, using trigonometry, we can do a very similar equation to work out that force. So that's going to be, rather than cos, this one's going to be sin, 36 times 40g. So we're just separating out the kind of 40g into the two directions. 40 kilograms multiplied by gravity gives you a force of 392 newtons. That'll split up into a force against the slope of 317.1 newtons. And then if you work out the force going down the slope, sine 36 multiplied by 40 multiplied by gravity, 9.8, that gives us 230.4 newtons. So you can see splitting up that 392, the two forces it splits up into do not necessarily add together to make that force. So now we've got the force going down the slope. So now we can use force equals mass times acceleration to work out the acceleration. Our force going down the slope is 230.4 newtons, and that's equal to the mass 40 multiplied by the acceleration. So we find the acceleration, 230.4, and divide it by 40. That gives us 5.76 meters per second squared for the acceleration. Now, our next example works the same way. So we have the angle of the slope, we have the object, and we have a friction coefficient. So for this, it's going to be 0.1. So we are going to include friction in this example. The first thing to look at is the force of gravity on our object, and that's going to be 30G. And so 30G is going to be 30 multiplied by 9.8, the force of gravity. So gravity is always going to be 9.8, and that gives us 294 newtons. Now, that force is not going to go straight down. It's going to be split into two things. We're going to have the force acting on the slope, which we label R, and we're going to have the force going down the slope, which we're going to label F, and we're going to find both. Now, in our previous example, we didn't actually need R. We didn't do anything with a number for R, but for this one, R is going to be equal to cos 58 times 30G, and when we work this out, that's going to give us 155.8 newtons. Now, the reason we're looking at this is now we can work out the friction. Friction is equal to that force, the force acting against the slope. So it's a force that's going to be rubbing against the slope and creating the friction, multiplied by the coefficient of friction, which is 0.1. That means that friction is going to be 15.6 to one decimal place. Then we carry on as before. So we're going to find the force going down the slope, which will be sine 58 times 30G. And if you type that into your calculator, again with G being multiplying by 9.8, that should give you 249.3 newtons. So now we use our force is equal to mass times acceleration. Now our force is 249.3 newtons, but we're taking away the 15.6 newtons that we've got from friction. The mass is 30, and we're multiplying by the acceleration. So we take 249.3, and we take away the 15.6, and we get 233.7. It's equal to 30A. You know what A is, we'll just divide that through by 30. That gives us 7.79 meters per second squared. So now we know the acceleration. Now, why would we do something like this? Well, let's say, we're working out the acceleration. You might know that certain rates of acceleration will be dangerous. Perhaps if an object's going too fast down the slope, it's going to cause a lot of damage. So looking at the force of the object going down the slope and the acceleration might help you work out certain parameters for safety. And if you work out that maybe this is too fast, it needs to be a lower acceleration, then perhaps you'd lower either the mass of the object potentially, or definitely the angle of the slope would slow it down, or perhaps even increasing the coefficient of friction. In a system of forces, you have multiple objects, each with different forces acting on them and acting on each other. So let's say we have a lift that is 499 kilograms. There is a person in the lift who is 86 kilograms. We have a wire connecting the lift to the building, which has a tension in it. So that's the force keeping the lift kind of suspended, not falling. And we have the acceleration of the lift. So let's say for this, it's going to be an acceleration of 7.5 meters per second squared. So what can we say about this lift? The first thing we might want to do is work at the force of the tension in the cable attached to the lift. Because if this force is too strong, then it might end up, snapping or not being safe. So we need to figure out what this force is. Now, from the purposes of this cable, it doesn't really care what's in the lift. So I'm going to draw another little diagram here. This is just a diagram from the point of view of the cable. Now, the cable doesn't see a 499 kilogram lift and a 86 kilogram person. It sees them combined. So it sees a 585 kilogram object that it's attached to. To work out the force, we're going to do force is equal to mass times acceleration. So what's the force? Well, we have the downward force of gravity acting on the lift. So that's going to be 585 kilograms multiplied by gravity. And that's going to be offset by the cable pulling the lift up against gravity. That's going to be equal to the mass times acceleration. So the mass is 585 and the acceleration is 7.5. So if we solve this equation, we can figure out what t is. So 585 times gravity, and gravity is always going to be 9.8, will give us 5,733. That's going to be equal to the mass, 585 multiplied by acceleration, 7.5, and that gives us 4,387.5. So to get what the tension is, we are going to take the force to the left, 5,733, and take away from it the mass times acceleration. That gives us 1,345.5 newtons for the tension in the cable. And then we can think, well, is that going to be a safe value for this lift? Or is it going to be a case that this tension is going to snap the cable? It's too much. Another safety consideration is going to be the forces acting on the person inside the lift. Because there's too much force, they might get crushed by the speed of the lift going up, or they might end up flying around from the force of the lift going down. So we're going to draw another new diagram, this time just looking at the person inside the lift. So they have a weight of 86 kilograms, and we've got a force acting on them going up, and a force going down. So what we're going to do, we're going to have a look at the forces acting on the person. So we have the downward force, which is going to be 86 times gravity, because again, we're doing force equals mass times acceleration. The mass is 86, and multiplied by the acceleration, that's going to be 7.5. What I've missed out here actually is the force going upwards, which is let's add that in. So 86 times gravity, 9.8, will give us 842.8. And that's going to be equal to 86 times 7.5, which gives us 645. So if we rearrange the equation and solve it, we are going to get that the force acting upwards on the person is going to be 197.8 newtons. Now, given that the downwards force on the person is 842.8 newtons, and that'd be true anywhere, that'd be true, stood outside, then the force acting in the opposite direction, that's kind of accounted for when you're in a lift and it moves. You have like a funny feeling, maybe you feel a little bit lighter than usual. That's that feeling where you're not exerting as much force downwards because you've got this upward force acting on you in the lift. But you still overall have a force acting downwards, so you don't go flying up into the air. But if this number ended up being more than 842.8, then the lift would be going so fast that the person would end up kind of floating upwards and hitting the roof of the lift, which you want to avoid. So again, things like this are really used for kind of safety issues. The next thing to look at are the forces acting on a car towing a trailer. So we'll have a weight for the car. Let's say this one is 1,910 kilograms. And a weight of the trailer, let's say 231 kilograms. There's going to be a force in the wire in between the car and the trailer. We'll call this the tension again. There's going to be a forwards driving force of the car's engine pulling it all forwards. And we're going to have air resistance. The trailer is going to have some air resistance. Let's say 138 newtons. And the car is going to have some air resistance. Let's say 326 newtons. It'll have a greater air resistance, the car, because it's a larger object, so there's more air pushing against it. If we look at the driving force of the car, then the kind of engine doesn't really care that this is broken up into two objects. So again, we're going to combine these into one object. Now the weight is going to be the combined weight, so the 1,910 plus 2,031, and altogether that's going to be 2,141 kilograms. Just adding together both of the weights in kilograms. It's going to be the same thing for the air resistance. So we're going to add together the two air resistances to get the total air resistance, which is going to be 464 newtons. And what we're looking for is the driving force. The first thing to do is resolve the forces, because as usual, what we want to do is we want to do force is equal to mass times acceleration. So the forward driving force, we don't know. Let's call that D. And acting against it, we have the air resistance, 464. That's going to be equal to the mass, 2,141, multiplied by the acceleration. Now, I forgot to write that down. For the acceleration, let's have 3.7 meters per second. So we'll multiply by 3.7, which will give us 7,921.7. So all we need to do now is rearrange the equation. To find the driving force, we're going to have to add on the 464 to both sides. That's going to give us a total driving force of 8,385.7 newtons. Next, we'll find the tension in the cable between the trailer and the car. Now we can focus on the trailer or the car and get the same answer. I'm going to focus on the trailer. So I'm going to draw a little diagram just for the trailer. So we know its weight is 231 kilograms. We know that we have the air resistance, 138 newtons, and we've got the tension in the cable dragging it along. Again, we want to do force equals mass times acceleration. So the force, we've got the tension in the cable, and acting against it is our 138 newtons of air resistance. The mass is 231 kilograms. We're going to multiply it by the acceleration, 3.7. That's going to give us 854.7. And now we just need to rearrange the equation. So we're going to have to add the 138 to both sides. That gives us, for the tension in the cable, 992.7 newtons. And again, this will be a safety thing, so it might be that the cable can only handle so much force. And like I say, if the cable can only handle 1,000 newtons of force, then this would be dangerously close to breaking. So you want to either make the cable a lot tougher, or you want to say that this kind of acceleration wouldn't be allowed with this sort of cable. There are a lot of different things that you can find from grouped data. Now, the easiest thing to find is the mode, which is the most common group. So when we have a look at our table, look at the frequencies, we find the highest frequency, which in this case is 60, and we look at the group next to it. And that group is the 120 to 130 group. And so that is how we find the mode. Another relatively easy thing to find is the range. With a range, you find the lowest possible value, which is 110, and the highest possible value, which is 150, and you subtract them from each other. And 150 take away 110 is 40. So the range will be 40 centimeters. All of the values will be somewhere in between 110 and 150 centimeters. The mean tends to be what people think is the most difficult one to find. Now, for the mean, what you need is a new row on the table for the midpoint. And the midpoint is the middle point of the group. So if our first group is 110 to 120, our midpoint is 115, because that's right in the middle. And so we write down a list of midpoints. Then we need to multiply the midpoint by the frequency. What we're doing is we're just trying to add up all of the lengths. So for example, if your frequency for the first group is 53, we're going to multiply 53 by the lengths in the first group, but we don't know what all those lengths are. So we just assume that all of them are in the middle, 115, and any extreme values will cancel each other out. So we multiply through. So 53 multiplied by 115 gives us 6,095. 125 multiplied by 60 will give us 7,500. 135 multiplied by 46 gives us 6,210. And 145 multiplied by 29 gives us 4,205. Now, once we've done that, we need to add up all of these numbers. So we add up our 4,205 to our 6,210 to our 7,500 to the 6,095. And so altogether, we have 24,010. So that's an estimate of if you took all the people in the table, all the lengths in the table, whatever it is, and you add them all together, it should be somewhere around 24,000. So that's the first part of finding the mean. Now, another thing we need to find here is something called the cumulative frequency. Now, this is also the starting point for the median. Now, the cumulative frequency, what you do is you take the first frequency, which is 53, and for the next column, you add it on to the next one, which is 60. And 53 plus 60 is going to give us 113. Then we add that on to the 46. And so what we're doing here is just kind of keeping a running total of the frequencies as we go through the table. Add on 46, we should get 159. And you add on 29, and you get 188. That's how many items of data we have in the table. So for the mean, once we've found what everything adds up to, which is 24,000, we'll then divide it by how many items of data we have, which is 188. That's the last value in the list of cumulative frequencies. Alternatively, you could add up the frequencies, and this is the common method as well. If you add them up that way, you get 188. But if you do it with cumulative frequency, then you can overlap your working out with your working out for the median. You need to find that as well. So 24,010 divided by 188 should give 127.7 centimeters. Last thing to do is just make sure that number is within the range, so it's within 150 and 110, and it is. And then is it roughly in the middle of all the values? Now we can see the 120 to 130 group where this is in has the highest frequency, and the groups on either side have the next highest frequencies. So it kind of makes sense that the mean will be roughly around about there. Next, we're going to find the median, and we're going to be careful. We're going to find the median group. So with the mode, we should make that clear as well. With a mode, we find a modal group. So make it clear if it's kind of a particular length we're looking for. So we have the centimeters for the range of the mean, or if it's a range of values to group. So modal is just the same word as mode, but use modal when you're talking about a group. So how do we find the median group? So you get your cumulative frequency, and we know we've got 188 items of data in the table. So you take the 188, you add 1 to it, and you divide by 2. Now, why divide by 2 should be pretty clear. If you've got 188 people, then you divide by 2, you get 94, which should be the middle person. But a little quirk of finding data from lists is that we want values that are in between. They're possible as well. So adding 1 just makes a little correction that should get you the correct answer. So actually the median is going to be the 904.5th person in the group or item of data. So we need to find that. Now, which group is that going to be in? Well, it's not going to be in the first group. The first 53 items of data are in the first group, so it won't be in that. So it must be in the second group, because the second group goes up to 113. And that's smaller than 94.5, but then we know that 94.5 won't go in the group before. So say the first 53 values go in the first group, then the next 60 go in the second group. And so the 94th value is going to be the next 60 after the 53. All we need to do, just like the mode, is look to the group that that's part of. And it's actually the same one as the modal group. It's 120 to 130. Next, there are 2 things you need to know that go beyond GCSE. The first thing is the standard deviation. The standard deviation is roughly how far away from the mean you're going to find most of the items of data in the table. And there's a symbol for it, which is the kind of sigma symbol. Now, how do we find it? So we have a formula. So it's going to be the square root of the sum of the frequencies multiplied by the midpoint, take away the mean, squared, all over n minus 1. So it looks really complicated. Now, since I said midpoint, we have 4 of those, we're going to have to do some calculations here. So when we have the sum of the frequencies, our frequencies are 53, 60, 46, and 29. And they're being multiplied by something. They're being multiplied by the midpoint. So our first midpoint was 115. Take away the mean, which was 127.7, and then we're squaring that. So let's do that for all of them. Taking away the mean is always going to be the same number, and then we can work these values out on a calculator. So the first row gives us 8,548.37. Our second value will be 437.4. Our third value will be 2,451.34. And our fourth value will be 8,679.41. Now it says the sum of those. So we add up all 4 numbers and we get altogether 20,116.52. Now we still haven't finished because we have to divide that by n minus 1. Now n is a number of things in the table. That's 188 for this. So we're going to divide it by 187. And then we have to square root that answer. And that gives me a final value of 10.37. Now, it's just important just to clarify what all the bits of the formula mean. So, for example, the mean is x bar, it's x for the line over the top of it. M was for the midpoints. So we can actually see the midpoints from the working out there. And then n, so we should do some working out for that. So n was the 188 take away 1. And that was n minus 1. Now, what does a 10.37 mean? Well, it means that if the mean is 127.7, then it means that around about 60% of all the data should be within 10.37 of it on either side. So anything between, somewhere around 117 and 138, you're going to find most of the data in that range, with a little bit on the outside at the bottom and top end. The last thing to look at is to find the median. Now, we haven't already found the median, we found the median group, but now we want the actual median. Now, we know the median is going to be in between 120 and 130, and we know it's going to be around about the 94.5th value. Now, the first thing we need to know is how many values are in the median group. And we know there's 60 values in the median group, but which of those 60 are the one we're looking for? Because the 94.5th refers to all of the values in the table. So you take the 94.5, we're going to take away the group before it, which is 53. And that means the median is going to be the 41.5th value out of these 60 values in the group. So let's make it clear how we got that. We took away the previous group from the 94.5 to get to the next part of the median. Now, when we do 41.5 and divide it by 60, we get 0.69. That's near 70%. And what we're saying is that our median is about 70% of the way through the group. Now, if it's about 70% of the way through the group, if we multiply it by the width of the group, which is 10, and we'll just make a note on here that there's a width of 10 from the top to the bottom of that group. Then we've got how many numbers through the group it is, and we're getting 6.9. So then all we need to do with that 6.9 is add it to kind of at the bottom part of the group. Now the group starts at 120, so we take 120 and we add on the 6.9, and we're going to get the value in the group, and it's 126.9. That's going to be the median. And then the answer is going to be in centimetres. And while I'm talking about centimetres, actually the standard deviation should be in centimetres again. Find the median group and the median value in terms of all the data. If you take away the cumulative frequency group before it, so in this case it's 53, but let's say our median was in the 188 group, then we take away the 159, the group before it. So you take away all the previous groups basically, and the cumulative frequency has already added all the previous groups up for you. So now we know the median is in the 41.5th part of its group out of the 60 items in its group. Multiply by the width of the group, and you'll get how far the group we're looking. We're looking around about 7 items of data through the group. So add on the base of the group, which is 120, the bottom number of the group, and you get the median, or rather an estimate of the median. And you'll find most of these are estimates because we didn't actually know the actual items of data. Whenever we've used a midpoint, that means it's an estimate. Moving averages are used with seasonal data. That's data that has a kind of repeating pattern through the seasons. So, for example, on our graph, we've got the 2014 values, and we can see that with the 2014 values, that there's a kind of a peak in the middle. Now, this is the graph of temperature. So, of course, there'll be a peak in the middle where we have the summer and the temperatures are higher. Now, we look at the 2015 value. Again, we see the same pattern, and there is a peak in the middle corresponding to summer. Then we can look at the 2016 values, and again, we have that same peak in the middle corresponding to warmer temperatures in the summer. The reason it's important to spot this is because if you find the average of these items of data, because they kind of have these kind of peaks and dips in the summer and the winter, any average you'll find in this data will be completely meaningless. It's not going to really tell you much about what's going on. So another thing is you're trying to find a trend here. What's happening with the data? Are the years getting warmer? Are they getting cooler? It's really hard to tell with the data going up and down like this. So we use something called moving averages to smooth out the data. So rather than find the average of all 12 items of data, what we do for our first average is that we just find the average of the first 4 items of data. So reading the graph, we've got a point of data at 6, a point of data at 11.5, a point of data a little bit higher than that actually. So I'll keep it 11.5. This will be an estimate. Then we've got a point of data that's at about 3.5. And we've got 4 items of data. We divide that by 4. And that will give us an estimate of the average of the first year. I'm going to type all that into my calculator, divide it by 4, and I'm getting 8.125. And now what we can do with that is that we can plot this on the graph. I'm going to plot it in the middle of the 4 items of data. So if this is summer 14, spring 14, summer 14, autumn 14, and winter 14, in the middle will be in between the summer and autumn. So we're going to plot it around about here. So that's our first average. And that kind of stands for the average of the first year. Now, what we do next is, for the second average, we're not just going to find the average of the next year. You could find the average of the years separately, and that'll give you a trend for just the years. But what we're going to do with moving averages, average number 2 is going to move along one position. So we're not going to use a 6 anymore. We'll use the 11.5s, and we'll use a 3.5. And what we're going to do now is, now we've done the first 3 items of data, we're going to move on to the 5th item of data, which is summer 2015. And that one looks to be around about 8. So now we add those numbers up, we divide those numbers by 4, and we get 8.625. So we can see the temperature's kind of creeping up a little bit here. And we can plot that. Now it's going to be in the middle of the next 4 items of data. Now we're including spring 15. So now it's going to be in between autumn and winter 14. And it's going to be a little bit higher. So now move on to average 3. And now we're getting rid of the summer 14 temperature, the first at 11.5. But we're going to keep the next 3 temperatures, the 11.5, the 3.5, and the 8. And we add on the next value. So we've moved on to the 4th value, which is spring 15, and that is about 13.5. So now we add up those values, divide that by 4, and we get 9.125. And now we can move on 1 square, and we can plot that value. Then we move on to average number 4. So the next one we're adding on is autumn 15. So we drop off the first number, keep the rest of the numbers, and add on our new value, which looks like it's just over 8, just over 10 actually. Let's call it 10.5. So now we add up our new set of numbers. We divide those by 4, and we're getting 8.875. And again, we can plot that on the graph. Now, altogether, we're going to need 9 of these. So what I'm going to do now is I'm going to work out the rest of these, and I get the idea of how they work, and I'll jump ahead to when we have all the answers. And so this is what the full calculation looks like. Now, with the dotted line, what we can now do with that is we can draw a line of best fit, and we can try and figure out some kind of trend. So with line of best fit, we're going to try and draw a line which has roughly half the points above and below it. And so this line of best fit has roughly 2 points below it and 2 above it. And then that shows a trend. And the trend is that the temperature is decreasing over time. Now, initially you might think it was increasing, because look at the peaks in the summer. The peaks in the summer are getting higher. However, the troughs in the winter, they're actually getting lower, especially the last value in winter 16. So with colder kind of springs, autumns and winters, that kind of balances out the hotter summers, and actually over time things are getting cooler for this temperatures. Now, what if we wanted an estimate for the average temperature in 2017? So if we wanted the average for 2017, now you can see the average of each one's going to be the middle of the year. So for example, the middle of 2014 is going to be in the middle of the spring and autumn on this. So you can see you've got 2 months, 2 seasons before it and 2 after. So in between spring and autumn for 2015 and 2016. And we can see the kind of pattern we're going along here. So we can see there's 3 full squares in the middle. So where I'm marking now, that'll be the average of 2017. Now, to find this estimate, you just do what you do with a normal scatter diagram or line graph. Draw a line up from where that's going to be, and then draw a line across. Now, you would do this with a ruler. I'm doing it freehand just to show you kind of step by step where you're going to look, but you would do this with a ruler and get a nice straight line. And we can see roughly where our answer is going to be. It's going to be roughly around about, just under 7, so let's say 6.75. The units for that, that'll be degrees Celsius. So with the current trend, that should be the average temperature of the year afterwards. Incidentally, you want to find the average temperature of any one year. You just find the 4 values for just that year, add them together, divide by 4, and get your answer. With probability tables, the first thing to know is that all the probabilities should add up to 1. So for our first table, we have a biased die. It can roll a 1, 2, 3, 4, 5, or 6. But unlike a third die, where every single side would have the same probability, these are all different. So we see that there is a much less chance of getting a 1 than a 5. Now, all the probabilities add up to 1, and we can see that there are 2 probabilities labelled with algebra letter. So what we do in this situation is get all the numbers that we do have. We have a 0.06, we have 0.23, 0.26, and 0.13. And so we add together all the probabilities that we do have, and we see what we get. And altogether, that's going to give us 68, so 0.68. Now we know that all the probabilities have to add up to 1. So what we do here is think, well, they're adding up to 1. Let's take 1, and let's take what we have away from it, which is 0.68. You can add in some numbers if you like. 1.00 is the same as 1, but now it's all lined up nicely for us for the takeaway. And the answer that you should get is going to be 0.32. So we know that x is equal to 0.32. Or rather than be x, it's going to be 2x is equal to 0.32 because we have 2 x's in the table. So if you want what 1x is, we're going to divide that through by 2, which will be 0.16. And now we have the missing probability. So the probability of getting a 4 is 0.16, and the probability of getting a 2 is 0.16. So let's write that down. Probability of 4, 0.16. Now that's the probability of getting 1 4. Now what we could also say here is what's the probability, or rather how many 4s would we expect if we rolled 100 of these? So 100 rolls. Let's make it clear that the table is about dice rolls. So 100 rolls would give us, we take our probability of a 4, which is 0.16. We'd multiply it by the number of rolls, and that would give us 16. We'd expect to get 16 4s if we rolled 100 die. So if you want to know how many you'd expect to get, just multiply the probability by the number of events there's going to be, the number of trials there's going to be. And of course, this is an estimate. So you'd expect to get around about 16. You'd be lucky if you got exactly 16, or you might get 15 or 17. You might even get 14 or 18 on either side. What would be really unlikely is getting something wildly different from the 16. For example, getting a 50 is most likely not going to happen. It should be close to 16. The next type of probability table could be something like having 2 events that we find the outcomes of. For example, rolling 2 fair dice. I've got a table here that shows all the possible outcomes. So let's say we want the probability of rolling a 1 if we roll 2 dice and we multiply the results together. Now, if you look at the table, where do we have a 1? Well, we only have 1 1 in the table. That means there's going to be a 1 chance of rolling a 1. And out of how many? Well, it's a 6 by 6 table, so there are 36 outcomes in the table. We could take another value. So let's say the probability of getting a 2. So you find all the times you find a 2 in the table, and there are 2 of them. So that would be a probability of 2 out of 36. Then we can find the probability of getting a 4. So how many 4s are in the table? We have 1, 2, 3 4s in the table. We'd say that's a 3 out of 36 chance. We could also say things like what's the probability of not getting a 4 with a dash showing not. Now, all these probabilities are going to add up to 36 out of 36 outcomes. The probability of not getting a 4 is the other 33 outcomes that add to 4. And see that 3 out of 36 and 33 out of 36 will add up to 36 out of 36. One other thing you can do here is to say things like, what's the probability of getting, for example, more than 16? So you highlight everything that's more than 16. And note that 16 itself is not more than 16, it's equal to 16. We've got 4, 5, 6, 7, 8, 9. 9 are more than 16. So we'd say that's 9 out of 36 chance. You could have something like the probability of getting less than or equal to 6. And so you go through the table and you find everything that's less than or equal to 6. That's 1, 2, 3, 4, and 5. And of course, 6 itself is more than or less than or equal to 6. It's equal to 6. So if we have the equal symbol, we can include the number itself. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14 different numbers highlighted. So that's 14 out of 36. You can also have questions. Now, I'm going to free up a bit of space at the start. You could have the probability of getting a, let's say, 13. So what's the probability of getting 13 in the table? Well, there aren't any 13s in the table. So the probability of getting 13 will be 0 out of 36, which is better written as just a 0. Because 0 over 36 implies you 0 divided by 36, which won't be possible. So you just write 0. And with this, we're not limited to individual values or more thans or less thans. You can also have things like what's the probability of getting an even number, the probability of a prime number. So there's all kinds of different things you could be asked. The last sort of probability table to look at is one such as this one, where it records outcomes. And you'll typically have missing values in the table. So how do we work out missing values? Well, what you want to do is find a row or a column that only has one piece of information missing. Now, you're missing the total, so add everything together. If you have the total, then take the total, in this case it's 157, and take away the numbers that you do have. And the answer to that is going to be the missing number. So 157, just quickly do it on a calculator, we're going to take away 76, and then we're going to take away 69, and that gives us 12. So we know that 12 is going to go in the missing position. And then once you do that, you can find another row or column. So for example, the totals, we have 126, and we have 157. So we add those together, we're going to get 283. And you'll see as soon as I fit that number in, now the total column at the bottom only has one missing. So as you start filling in numbers, you increase the amount of numbers you can use, and you increase the number of rows and columns that only have one missing piece of data. So for the totals, we've got 283. Let's take away the 140 and take away the 103, and that's going to give us 40. That's now give us a second value in column A3. The total's 40. We can take away the 12 that we worked out previously, and now we've got 28. We've got row A2, the total's 140. We can take away the 69, and that gives us 71. Finally, you could do something that you could add up row B1 and see if we do get the total. So 27 plus the 71 plus the 28 should all add up to 126. And if it does, you know you've got the table correct. If it doesn't, you need to look back at it. So you can use logic using rows and columns with one missing value to work out that missing value, and you gradually build up a list of skills, a list of numbers. Now we can find probabilities from this. We say, what's the probability of choosing A1 and B1? And the number there is 27 in the column of A1 and B1, and the total is 283. So that's the chance of probability of choosing something at random where it's getting A1 and then B1. You can also do things like saying what's the probability of getting something from A3. Now the total for A3 was 40, so that would be a 40 out of 283 chance. And finally, we can have the probability of getting something from B2, given that A3 has happened. So if A3 has happened, that means we've got 40 different outcomes to look at from A3. And you want to get the value for B2. So that in the A3 column is 12. So given that A3 has happened, and we have one of the 40 outcomes for A3, what's the probability of choosing something from B2? Well, there's only 12 in B2 that also corresponds to A3. With tree diagrams, there are two main types to think about: tree diagrams with replacement and tree diagrams without replacement. Now, each tree diagram needs an event. So for this event, what we're going to do, let's say we had a bag, and inside the bag were some counters. And what we're going to do is we're going to reach into the bag and pick out a random counter. So what should we have in the bag? Well, let's have some blue counters and let's have some green counters. So we are going to choose two counters. I'm going to take them out of the bag. Now, with replacement, what would happen is we'd have a first choice, and we could either choose a green counter or we could choose a blue counter. The probability of choosing a green counter is 2 out of 5. There are 2 green counters and 5 counters altogether. The chance of choosing a blue counter will be 3 out of 5. There are 5 counters and 3 of them are blue. So that's the first event, the first choice of a counter. Now, with replacement, what will happen is that you then put that counter you chose back in the bag. So we'll make your second choice. Again, you can choose green or blue. Green is still going to be a 2 out of 5 chance, and blue is still going to be a 3 out of 5 chance because the number of counters in the bag hasn't changed. Now, with the tree diagram, I've listed this choice as after green. So if you choose green, then we could have green or blue. You can also choose blue first and then have that second choice of green or blue. But again, the probabilities are going to remain the same because all the counters are returned to the bag. And the first choice does not affect the second choice. Now, why are we recording it like this? Well, the tree diagram shows all of the possible things that can happen. So we could choose a green counter and then a second green counter. And if we did that, we have a 2/5 chance followed by another 2/5 chance. And if you want both to happen, what you need to do is you need to multiply them together. And so that's going to give us a 4 out of 25 chance of choosing green then green. Alternatively, we could choose green and then blue. If we choose green then blue, we just write down the fractions on that path. So we've got 2/5 on the green part and 3/5 on the blue part of the path. So altogether, that will be a 6 out of 25 chance. A third alternative is we could choose blue first, and after blue, choose another blue. And if we choose blue then blue, it's going to be a 3/5 chance, multiplied by a second 3/5 chance, and that's going to be a 9 out of 25 chance. The last possibility is we could choose blue and then green. So the blue path is 3/5, the green path is 2/5, and we multiply them together, we're going to get 6 out of 25. Interestingly, if you add all 4 events up, what you would get is 25 out of 25. So it's going to add up to a whole one. And that's the same for each branch as well. You won't always be given the probability of both parts. I mean, we can see the little diagram I drew here with the bag. We can see there's 3 blue and 2 green. But sometimes you might only be given one of the probabilities. Each part of this tree adds up to a whole one as well. 2/5 plus 3/5 is 5/5. It's a whole one. And that's true of each set of branches. You can also be asked follow-up questions. So, for example, the probability of green then green is 4 out of 25. We can follow the work we've already done. But what if we wanted the probability of at least one green? So probability of green being more than or equal to 1. So if we chose green and green, then we'd have more than or equal to 1 green. We have 2 green. And so that would be a 4 out of 25 chance. But then if we had green and blue, that's also more than or equal to 1. It's 1, it's equal to 1. So we could have that outcome as well, 6 out of 25. And we could have blue then green, which is also 6 out of 25. The only one we're not going to look at is blue then blue, because with blue then blue, we have 0 green, and that's not more than or equal to 1. Now, if we have multiple potential paths that satisfy what we're looking for, we can add those fractions together. So altogether, this will be a 16 out of 25 chance to get more than or equal to 1 green. The big thing to remember here is when you multiply and when you add. When you're calculating the final probabilities for each tree, the probability of one thing happening and then another thing happening, then we use multiplication. So anytime you use and, that means we are going to multiply. Now, when we're saying probability of green is more than or equal to 1, we could have green and green, or green and blue, or blue and green. So if you say or in regards to probability, you're going to be adding them together. And when you check your answers and add together all 4, effectively that's say the first outcome, or the second outcome, or the third outcome, or the fourth outcome. And it all adds together to 25 out of 25, which is a whole. That's how tree diagrams with replacement work. Now, what if there was no replacement? Well, it will start off the same way. The probability of green would be 2/5, and the probability of blue would be 3/5. But this time, we're not going to put the counter back into the bag. We're going to leave it out. And this is going to change the probabilities. So let's say you want to choose a second green. What would the probability be? Well, one of the greens would be removed from the bag. So you've only got 1 green left in there. In addition to the numerator changing, the denominator is going to change because now you have 4 counters in the bag. So both the numerator and the denominator have both gone down by 1 for your second green choice. The probability of green then green would be 2/5 multiplied by a quarter, which will give 2 out of 20. Now, what if we wanted green and then blue? Now, with blue, because we took a green out of the bag, the number of blue counters has not changed. We still have got 3 blue counters. So the numerator stays the same. However, the denominator changes to a 4 because we only have 4 counters in the bag. Now, look at the probabilities on the trees. For the first choice, we've got 2/5 and 3/5. That adds up to 5/5, which is a whole one. Now let's look at the second choice. We have 1 quarter plus 3 quarters, which adds up to 4 quarters. That's a whole one. So you can check your work once you've written down your probabilities. Now, what about if we chose blue first, and then we want to choose a second blue? We had 3 blue counters in the bag. We've taken 1 out. There's only 2 blue counters left. And there's only 4 counters in total left in the bag. So that's a 2 out of 4 chance. What if we wanted green? Well, without even thinking about it, I know that green is also going to be 2 out of 4, because 2 out of 4 plus 2 out of 4 is 4 out of 4, which is a whole one. Let's just check the logic of it. So we haven't taken the greens out. We still have 2 green in the back, so that's where the 2 comes from, and there's 4 counters altogether. So that does actually check out as being true. So now we go through the list and multiply together all the probabilities and calculate the probability for each outcome and multiply the fractions together. And so we can see each outcome coincidentally is at 6 out of 20, except for the one at the top, which is 2 out of 20. Additionally, if you wanted to, you could simplify these, and that might make the working out later on a little bit easier. So 2 out of 20 is the same as a tenth, and 6 out of 20 is the same as 3 tenths. We can even visualize these as percentages. You've got a 10% chance of green then green, and a 30% chance of the other 3 options. Now, again, we could be asked follow-up questions. So we can have the probability of 1 green and 1 blue. So which paths would satisfy that condition? Well, the top path is green then green. That's 2 green and 0 blue. So that's not going to be true. The second path is green then blue. Well, that's 1 green and 1 blue. That was a 3 out of 10 chance. The third path is blue then green. Well, that's 1 green and 1 blue. In the other order, but you still have 1 of each. That's a 3/10 chance. And then the final one is blue then blue, which is going to be 2 blues and 0 green, which doesn't satisfy our condition. So 3/10 plus 3/10 is going to give us a 6/10 chance, or we could say a 60% chance of choosing one of each counter. And so now we can see the difference between replacement and no replacement. If you have replacement, then the probabilities are going to stay as a probability given in the question. Now, with replacement, you could have 2 different events. This is the same event twice, but you could have a different bag of counters for your second event. And so you could have different probabilities for the first choice and the second choice. But the point is, it's still going to be the probabilities you've been given in the question. With no replacement, the first event is going to have the probability you're given, but then you have to calculate the second event, because the outcome of the first event has changed the outcome of the second event. And with these kind of tree diagrams, you can't have 2 different bag of counters for first and second choice. That's essentially the same as a replacement tree diagram. For no replacement, it has to be the same event twice, with the second event being changed by the first event. For example, by not returning a counter to the bag. With Venn diagrams, you can see 2 examples on the page, and it's about sets of numbers inside of geometric objects, usually circles, but you can also see a rectangle around the circles, which is also a set. So what do we mean by set? Well, the first thing we have is the universal set, and that's this odd symbol you can see in the upper right corner. The universal set is all of the numbers. So for our first diagram, the first 10 numbers are in the diagram. And we've got 2 other sets. We have set A. Set A is the circle next to A, and inside that circle, we've got 3, 4, and 9. The other set is set B. Inside set B, we've got 1, 5, 6, 7, 9, and 10. And you'll notice that 9 is in both set A and set B. And so you can see it's in an overlap section in between the 2 circles, but it is in both circles. You'll also see that 2 and 8 are not in either set A or set B, but they are in the universal set. Now, there are a few ways to describe getting different numbers out of these sets. So, for example, we could look for the probability of set A, then this kind of N symbol, and then set B. Now, what that means is, with the N symbol, is it's the intersection. And the intersection is where the 2 circles cross over. So I'm just going to highlight that in green. And we can see that there is 1 number inside there, and it's the 9. So 1 out of the 10 numbers are in the intersection. So we say the probability of A and B is 1 over 10. If we're just listing the set A and B, then we would write 9. Then there's something called a union. It's the probability of the union of A and B. Now, by the union, we mean both circles together. The union of the 2 sets. The 2 sets joined together. So that includes all of A. It includes the overlap between A and B, and it includes B. So we wanted the probability of choosing a number at random from that. We can see we've got 1, 2, 3, 4, 5, 6, 7, 8 numbers. There's an 8 out of 10 chance of choosing one of those at random. If we're just describing the set, A, U, B, then we'd have to write in all the numbers. So we have 1, 3, 4, 5, 6, 7, 9, and 10. So So it's all the numbers except the 2 and the 8, which are not in the highlighted section. Now, how can we describe things like the 2 and the 8? So we also have a symbol for something called not. So let's say we had not A, that'd be A with a dash. And that's all the numbers that are not in set A. So for example, 1 isn't in set A, it's in set B. 2 isn't in set A, it's outside A and B. 3 and 4 are in set A, but 5, 6, and 7 are in set B. 8 is outside of both sets. 9 is in set A, so we don't include that. But 10 is in set B, so we can include that. So we've got a list of all the numbers that are not in set A. Why don't we look at not set B as well? So what's not in set B? Well, we've got the 2, that's outside of both sets, the 3 and the 4, which are in set A, and then the 8, which is also outside of both sets. So it's a shorter list for not B. Now, for our first diagram, each one of these numbers appears once. So we're talking about probabilities, like going back to the probability of A and B, then we'd say that's a 1 out of 10 chance, because we've got one number in the intersection of A and B, and we've got 10 numbers altogether. So each of these numbers is counting for 1. And you can tell it's like that because you've got multiple numbers in each set. Now for our second diagram, for this one we've got 3 sets, A, B, and C, and the universal set. But you can see there's only one number in each set, and we have some numbers repeated, like the 6s and the 7s. Now what this means isn't that we've got the number 6, and that's the only one in there, like for example, for the intersection of all of them with a 2 in the middle, we can't say that that's a 1 in 7 chance because there's 7 numbers and one of them's a 2. Because this time the 2 is representing 2 items, the 7 is representing 7 items. So it works very subtly different. And so for a diagram like this, we can't list the members of the sets because we're not being given the members of the sets. We only know how many members are in each set. So let's have a look at some questions. So we could have the probability of having something in set A. Now, what is inside set A? So let's highlight it and have a look. Inside set A, we've got the 6. That's the one that's only in set A. We also have the 7 and the 2 in the overlapping sections. And so how many numbers are there in set A altogether? Well, it's 6 plus 7 plus 2, which is 15. So there are 15 numbers in set A, not 3 like you'd say with the previous diagram. We also need to know how many numbers there are altogether. So we're going to add the 6, and the 5 that are only in A, B, and C. We're going to add together the 7, the 2, and the 3 in the intersections. And we need to add the 7 on the outside. And there are 36 numbers altogether. So it's a 36 chance as choosing something from set A at random. So we can do the same thing with set B. What's the probability of choosing something from set B? So we've got the 6, the 3, and the 2 in set B. That's 11 out of 36. And we could do the probability of choosing something from set C. We've got the 5, the 7, the 2, and the 3. That's 17 altogether. Also note that these probabilities do not add up to 36 out of 36 because these probabilities overlap with each other, so some of them share values. If you chose something that's in set A or set C, then there's 7 numbers that are in both that would overlap. Now, on that theme, if you said we wanted the probability of something in the intersection of set A and C, there are 7 numbers in the intersection out of 36 total. If you wanted something in the union of A and C, then that's all the numbers in both added together. That's the 6 plus the 7 plus the 5 and plus the 2. Let's highlight it actually so we can see really clearly. So the union of the 2 sets, or the intersection of the 2 sets, and actually now I'm drawing the diagram, actually I've made a mistake because if we look at the intersection of A and C, it also includes a 2 in the middle. So actually I shouldn't have written 7 out of 36. I should have written 9 out of 36. And I've left that mistake in because I wanted to show you how easy it is to make mistakes with these diagrams and how useful highlighting intersections can be. Now, in the union, we'd have that 9. We'd also have the 6 that's in set A. So 9 plus 6 is 15. And we'd also have the 5 that's only in set B. That's 20. I nearly made another mistake there because we've got the 3 here as well. That's also in set C. So that's 23 altogether, which is 23 out of 36 chance. Now, we can also do things like we can have a combination of all 3. So we have the probability of something being the intersection of A and B and C. And the intersection of all 3 is a 2 in the middle. That'll be a 2 out of 36 chance. We could also do things like, we could say the probability of B, a line, and an A. And that's a probability of choosing something in set B, given that set A has happened. Another alternative is you could have C/A, which is the probability of something happening from set A, given that set C has happened. So how do we resolve questions like this? Well, again, let's go back to the highlighting. So let's go back to what we've done already. So we're saying that C has happened. So whatever the first letter is, this has happened. So we've chosen something from set C. Now, given that we've chosen something from just set C, what's the probability that what we choose is also going to be in set A? And we can see there are 9, the value of 9, that's in set A and it's in set C. So what we say about the probability here is, I've got 9 different choices there to choose something that's in both. But then it's not going to be out of 36 because we've already chosen set C to start with. So it's going to be out of the total for set C. And there are 17 numbers in set C. So that'll be a 9 out of 17 chance. We could do it the other way around. We get a different answer. We have the probability of choosing something in set C, given that set A has happened. And so now we need to say about which way around these go. So the way it's written is P, C, line A, as a probability of C, given, that's a given symbol, given that A has happened and given that C has happened. Now, I've actually done this wrong myself because the 9 out of 17 should be the answer to A, line C, because it's not the first one that's guaranteed to have happened, it's the second one. You just read it out in English as you see it. Probability of A happening given that C's happened. C's after given, so in a sentence, that means that C's happened. If it was the other way around, so the probability of something from C happening, given that A has happened, there's still 9 in the overlap between them, but it's got to be over the total for A, which was 15. So you can see there's quite a subtle difference in between those two letters being the other way around. And it can be a little bit confusing. The last thing to look at is another way of a mix. You could do something like the probability of A and want the union of A and not B. So you can stick nots in wherever you want. And again, this is going to be a situation where highlighting is going to be really, really useful to find this. So let's read through what it says. What the union of A, so let's highlight A first. And then it's the overlap with not B. So for not B, I'm going to highlight everything that isn't in circle B. So that's going to be the kind of outside set. Notice I'm not going inside the circle for B. Now, parts of set C are going to be inside this. But notice the 3 that's in set C, but also set B, that's not been highlighted. Colouring the rest of the outside. So there's a 7 on the outside, so that will be included. We haven't used that yet in any of the questions. And then, what's not B? Well, most of set A is also not B. So what I'm going to do is, I'm just going to kind of cross-hatch this bit, because it's going to be both colours. And notice that the 2, that's in set B, but is also in set A, that's not being highlighted. So let's think about our answer. It's a union of A and B. So it's the ones that have been coloured in twice. So it's the ones that are in green for set A and in blue for not B. And that's only the 6 and the 7. So we add those together, we get 13. And what's it going to be out of? Well, it's the same as before, it's out of the entire set. So we 13 at a 36 chance of choosing something that's in set A and it's also not in set B. Binomial distribution is used when you see this kind of terminology. So you're going to have X follows a binomial distribution. You're going to have the number of trials you're doing and the probability of getting the outcome that you want. So let's think about a practical example of this that we could use. So let's say we're looking at coin flips. So we can say that coin flips follow a binomial distribution because anything can follow a binomial distribution if the thing you're looking for is either going to be a kind of a true or a false outcome. So for coin flips, you're going to get a head, and you flip the coin, it's going to be true or false. Either you got the head or you didn't. Now, we need to know how many coin flips are doing, so let's do 6 coin flips. And we need to know the probability. Well, if it's a fair coin, it's going to be 0.5. And then we need something that we're going to find. So let's say you want the probability of getting the thing we're looking for, X. So let's say getting a head on a coin. Let's say what the probability of getting 3 of them. So what you would do is you look at your probability distribution tables, or use your calculator to look these up, and you look for when n is 6. I've only got 3 tables, but you can have, quite a lot of these. You could have up, 20 tables, for example. So we want to find when n is 6. Then we want to find our probability. Our probability is 0.5. Then we'll look for the thing we're looking for, x being equal to 3. And we look at the intersection of those things. And here we have a value. Now, that value is not actually our answer. It's not the probability of getting exactly 3 heads on our coin flips. What this is a probability of is getting less than or equal to 3 with our coin flips. And it's a 0.6563 chance. So all these probabilities are cumulative. So if you look at x equals 3, it also includes the 2, the 1, and the 0. So what if we want the probability of getting exactly, and let's just make a little note here actually what this is. So all of this is about the probability of getting a head on a coin. So what we would do is we would take our value, this is 3 and everything before it, and we take away from it 2 and everything below it. And the value for 2 is 0.3438. Now, we don't need to take away the value before that. We don't need to take away the x equals 0, the x equals 1, the x equals 2, because, again, this is cumulative. So each value includes all of the values before it. So when we take away a 0.34, that has baked into it a 0.1 and a 0.01. So you would do that subtraction, perhaps use a calculator to do it. And I'm getting 0.3125. So this is how you find probabilities from the table. One thing you might have noticed is getting, well, what about 6 heads? Now, you've got the probability of 6 heads. You'll notice that x equals 6 is missing from the table. That's because it's cumulative, the last value is always going to be 1. So when you look up the value for getting 6 heads and the value is 1, well, it can't be a 1 chance. Well, it's cumulative, so that includes all the ones before it. So actually, to get the probability of it being equal to 6, we do 1 take away the probability of 5. So 1 take away the 0.9844. And then you get a much, much smaller answer. That would make no sense. There's lots of other things to mention. You know, the probabilities are cut off after 0.5. So what about 0.55 or 0.60? Well, what you would do is these are symmetrical, so you just take them away from 1. So, for example, if you wanted the probability 0.95, that would be 1 take away 0.05. And you could work it out that way. So for a 0.95 question, you do all the calculations with 0.05 and take your answer away from 1 right at the very end. Similar to that, you'll see other things that are missing. For example, we don't have the values in between. So your question will be limited to the values that are in the table. So, for example, going up by 5 in the 10th column. Another thing that's missing is all of these cumulative to less than or equal to. What if you wanted more than? What if you wanted the probability of x being more than 3? And so what we would do for that is think all the probabilities add up to 1. And less than or equal to 3 is what we don't want. We want more than 3. We want 4, 5, and 6. We don't want less than or equal to 3. So 3, 2, 1, and 0. So less than or equal to 3, which we've already found is 0.6563. If we take that away, the other side of it is going to be the greater than. So 1 take away 0.6563 should give you 0.3437. Another kind of question might ask you for what the average answer is going to be. So if you want the mean, which might be represented with the mu symbol, then you do n multiplied by p. So for our coin flips, we do 6 multiplied by 0.5, and we get 3. That means on average, we'd expect to get 3 heads out of 6 possible. You can also find the variance and standard deviation. The variance, which has a symbol sigma squared, would be np multiplied by 1 minus p. And what that does is it kind of gives you, well, if the mean of coin flips is 3, so actually let's write this down for this question. So what the variance would do would give you the spread around the 3 we'd expect answers. So we do n times p, which is 3, and we'd multiply that by 1 minus p. Now, if p is 0.5, 1 minus p is also 0.5, and that gives us 1.5. So that will tell us that while the mean is 3, we can expect values around about 1.5 in each side, and that would do about kind of 2/3 of the possible outcomes. So most likely would be getting 2, 3, and 4, and you might get a 5 and a 1 sometimes as well if you're really lucky, but you're not going to get a 6. That's going to be almost impossible. It would be very, very small probability. So the mean tells you where you'd expect the answers to fall, and the variance tells you how far on each side those answers will go. The last thing is standard deviation. This is another measure of how far answers can go at either side of the mean. And I'm not going to write down the formula for standard deviation, because standard deviation is equal to sigma. Now, we have the formula for sigma squared, the variance. So for standard deviation, you just take the variance and you square root it. The normal distribution is a pattern which a surprising number of things in nature follows. Now, it's a curve that's very close to the bottom at one end, raises to a peak in the middle, and it comes down symmetrical on the other side and gets very close to the bottom at the end. What kind of things can follow distribution? Well, for example, people's heights. A small number of people are very short, a small number are very tall, but most people are clustered around the middle. And what we have directly in the middle of the curve at the highest point is the mean, where the average person goes. A question for this will be in a certain format, and it'll look like this. X follows a normal distribution, and then you're going to have two numbers. You're going to have the mean, and you're going to have the variance. So the mean being where the average person is, and the variance being kind of how far either side the kind of curve goes. So where the majority of people are. So let's look at an example. So let's say that X follows a normal distribution. The mean is 7.67 and the variance is 0.24 squared. So how could we figure things out from this? Well, let's say we want the probability of X being less than or equal to 8. So what's this going to mean for us? Well, firstly, let's have a look at the diagram. This is going to be important. So on the diagram, we've got the 7.67 at the mean. So if we want less than or equal to 8, 8 is going to be at some point after 7.67. And if we want less than or equal, then we want everything to the left-hand side, so everything to the left-hand side. And so we want a kind of percentage. What percentage of people are less than or equal to 8 with this value? Now, what could this mean? Let's say it's something like shoe size. So the average shoe size could be 7 and a bit, and we want to know how many people have shoe sizes that are less than 8. Now, unfortunately, we don't have a table of values that has 0.67 as the mean. And you can think that there's going to be an infinite number of tables with all kinds of different values of the mean. So what is the table that we've got? Well, the table that we have here is a table where the mean is equal to 0. And so what we're going to do is convert the values that we have to be equivalent to a mean of 0 so we can use the table. So how do we do that? Well, we have a formula, and the formula is something called Z values. And we say that Z is equal to X, take away the mean, over the standard deviation. And this is how we do our conversion. So when we convert in the 7.67, what we would need to do to find it is find our value of X. So that's 8. We take away the mean, which is 7.67, and divide it by sigma, which was 0.24. Now this value is not for the mean, because the mean is going to be converted into 0. This value is for the 8. So 8 is going to be converted into our Z value. And what is our Z value going to be? So we take the 8, take away the mean, 7.67, divide it by the standard deviation, 0.24, and that gives us, for our Z value, 1.375. So now we have values for the table. Our mean is going to be converted to 0, so we can use the mean as 0 table. And our Z value is 1.375. And so we have to look through the table and find 1.375. And while we don't have 1.375, we do have 1.38. So I've had to round it to 2 decimal places to find it in the table. And that's got a corresponding value. And that value is our answer. So the probability of getting less than or equal to 8 is 0.9162. So it's nearly a 92% chance. Now, does this make sense? Well, 8 is above the mean. So that's more than half the values already. And if you look at the variance, 0.24, that means that we can only really expect to go 0.2 at either side. And 8 is actually just outside that range. So that tells the majority of the values are going to be within that range, or we're outside it. So having a kind of extreme value like nearly 92% would make sense. Now, there's a related one to this. We could also find the probability of getting something that's greater than or equal to 8. And how we do that? Well, we get less than or equal to 8, and we get 1, and we take it away from 1. So what's important to understand is this table is only for less than or equal values. So you want more than or equal, we don't get another table because that'd be a waste of space. We'll just take our answer away from 1. Now, I just want to colour code this. So the less than or equal to 8 on the diagram I've highlighted in green. To help you visualize this, the more than or equal I'm going to highlight in purple. And so we're looking for the other side of the line. And so 1 take away 0.9162 will give us 0.0838. And keep in mind, this is an estimate. Firstly, this kind of distribution in itself is a kind of estimate, but we had to round our Z value. So actually, this value is probably going to be slightly smaller because we had to round up. Another thing to mention is that you can find probabilities in between two values. So let's say you want the probability of X being in between 7 and 8. How will we work that out? Well, we would find the probability of X being less than or equal to 8, which we already have actually, and we take away from it the probability of X being less than or equal to 7. And what we're left over is the in-between values of those two. So we know being less than or equal to 8 is going to be our 0.9162. And we take away from that being less than or equal to 7. We only need a Z value for this. So we do 7, take away 7.67, and then divide by 0.24. And we get a Z value of negative 2.8. Now we can find 2.8 in the table, but you'll notice this is positive 2.8. It's not negative 2.8. Now, if we go back to the graph, let's say that 7 is going to be somewhere around about here. As a Z value, that's our negative 2.8. Now, on the other side of this is where we're going to have the positive 2.8. And what you'll notice is that the less than or equal bit below 7 will be symmetrical as the greater than part from the 2.8. So when we look at the 2.8 and we have 0.9974, that is actually the probability of being less than or equal to the Z value of positive 2.8. So if we want more than that, we have to do 1, take away it, and we get a decimal value for that. I'm getting 2.6 times 10 to the negative 3. And because the graph is symmetrical, the more than 2.8 is the same as the less than negative 2.8. We take that value away. So as a decimal, it is 0.0026. Take the two numbers away from each other, and we get 0.9136. So we can see that by finding the values in between 7 and 8, we had to take away the values that were less than 7, but that was actually very few values. It didn't actually adjust the final percentage by that much. We just went from maybe being close to 92% to being closer to 91% of the values. So to recap, there's a range of things you can find. The values from the table can only be found if you convert the values that you have into Z values, where the mean is always 0, and you use the Z value formula to convert anything that you're looking for into something that's in the table. You look at your values in the table, and that will give you probabilities that are less than something. If you want more than, you have to take it away from 1. And if you want negative values from the table, then they're going to be symmetrical to the positive values. And you do a little sketch in your graph to kind of work that out for yourself. You can also find more complicated things like in-between values by getting a larger value and taking the smaller value away from it. For Spearman's rank correlation, on the screen you see some data. You can see a scatter diagram and a line of best fit. Now, Spearman's rank correlation is a way to find how close the line of best fit is, how strong the correlation is. Now, the way you do this is we're going to have a look at the X and the Y coordinates of our data first. Now, going through our data, we're just going to do it in order. So the X coordinate was 1.25 for the first item of data. Y coordinate was 35. And we can cross that off after we've done it. The next one was 1 and 42.5. Then we have 1 and 37.5. We have 2.25 and 35, 1.75 and 32.5, 2 and 15, 3.25 and 22.5, 3.75, and 22.5, 4.5, and 7.5, and then 4.25 and 10. So we separated the X and Y coordinates on kind of lists. Now, what we want to do next is to rank them. We want the rank of X and the rank of Y. So by rank, we mean what is the largest number in the X list? And the largest number in the X list is 4.5. So we call that rank 1. We can cross it out so we know that we've done it. The next one, rank 2, will be the next smallest number, 4.25. The next largest will be rank 3. Then we have rank 4, rank 5, rank 6, rank 7. We have rank 8. And then with rank 9 and 10, we've got a 1 for both. We've got a tie break. So which one's going to be 9 and which one's going to be 10? Now, what you do is, if there is a tie break situation and they're both the same value, they're going to take up rank 9 and rank 10. So rather than give them 9 and 10, you give them the average of 9 and 10. And in between 9 and 10, you've got 9.5. So rather than writing rank 9 and rank 10, we have two rank 9.5s. We do the same thing with Y. So the highest number in Y is the 42.5. That's rank 1. The next number is 37.5. That's rank 2. And then the number after that is going to be the 35, which is going to be rank 3. But we have two 35s, which will take up rank 3 and rank 4. So to get the average of those ranks, which will be 3.5. If for some reason you had three numbers that were a tie break, you'd add up all three and divide by 3. And then that'll be the middle number. So add up the tie break numbers and divide the ranks available by 2 to get the averages. What's next? So next we're going to have the 32.5. So we have 3 and 4. This will be rank 5. Then we've got two 22.5s. That'll be rank 6 and 7. So they both get rank 6.5. After rank 7, rank 8 is going to be 15. Then we've got rank 9 and rank 10. So we've finished our list. So what do we do next? Well, next we want the difference of the ranks, and we are going to square the difference in the ranks. So for example, with our first coordinate, we've got 8 and 3.5 for the rank of the X and Y coordinates. We take them away from each other. That's going to give us 4.5. And then we square it. That's going to give us 20.25. For our next one, we've got 9.5 and 1. That'll give us 8.5. We square that. That's going to give us 72.25. Now, I'm going to find it hard to fit all these in because these are longer than previous numbers. So I'm just going to write them one row below in alternate columns, just so everything can fit in. Next, we have 9.5 and 2. That'll give us 7.5. And don't worry about which way you take them away, because if you do 2 take away 9.5, you get negative 7.5. But when you square it, it's going to end up being positive anyway. And squaring it gives us 56.25. Then we've got 5 take away 3.5, which is 1.5. And we can square it to get 2.25. Then we have 7 take away 5 is 2, and square it to get 4. 6 take away 8 is negative 2, and then square that will give us 4 as well. 4 take away 6.5 is going to give us a negative 2.5. And if we square 2.5, that's going to give us 6.25. Notice I'm not bothering to write a negative number for the difference because it's going to get removed anyway when you square it. 6.5 take away 3 gives us 3.5. And 3.5 squared will be 12.25. 1 take away 10 will give us negative 9. Square it will give us 81. And 9 take away 2, it will give us 7. And square it will give us 49. Now, what we can do next is we can use the formula. So here's the formula. Spearman's rank coefficient is going to be equal to 1 take away 6 multiplied the sum of all those d squared we just worked out, divided by the number multiplied by the number squared minus 1. And by number, n, which means the number of items of data. So how many items of data do we have? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items of data. So now we need to substitute into the formula. So R is going to be 1 minus. Now we need the sum of our d squared. So we can work that out at the bottom with the kind of E symbol, the capital Greek sigma being sum. So we're going to add together the 20.25, the 72.25, the 56.25, the 2.25, the 4, the second 4, the 6.25, the 12.25, the 81, and the 49. And altogether we get 307.5. So then when we substitute into our formula, we can have 6 multiplied by 307.5, and it's all going to be divided by 10 multiplied by 10 squared minus 1. So let's work out the top row of that. So 6 times 307.5 will give us 1,845. And we're dividing that by 100 take away 1 is 99. And 99 times 10 is going to give us 990. And now finally we have something that we should be able to fit onto our calculator. So we're going to do 1,845, divide it by 990, then we get a 1 and take that answer away from 1. And I'm going to get my answer, which is negative 0.8. And we'll just say 86 to 2 decimal places. So what can we say about that number? Well, if it's positive, you have a positive correlation, and if it's negative, you'll have a negative correlation. So we can see that this is going to be a negative correlation, and obviously looking at the line of best fit, it's a negative correlation. Now, the closer to -1 it is, the better, the stronger the correlation is. So 0.86, that's actually pretty close to 1, isn't it? So we know this is a fairly strong correlation. And actually looking at the line of best fit, there's only really one point of data that's a little bit far away from the line. So it kind of makes sense that this would be a strong correlation. Let's just make some notes on that. So +1 is strong positive, and -1 will be strong negative. And these are our correlations. So again, negative 0.86, that's pretty strong. Linear programming is the same as another topic. It's the same as solving inequalities on a graph. The one difference is going to be that you're going to be given questions, rather than being straight algebra, they're going to be kind of phrased in some kind of way. So your first step, it could be taking whatever words you've been given and turning them into equations. And you'll be given equations such as y is less than 5x minus 6, y is less than negative 2x plus 8, and x is greater than 0. But again, it'll be in a practical context usually for these questions. And a useful thing to do is to rearrange them so in the form y equals mx plus c, so then you can plot them. So they might not necessarily be laid out like this, so you've got to rearrange them. So let's plot these graphs. So for the first graph, y is less than 5x minus 6. So the -6 tells us that it's going to have a y-intercept at 6. And the 5 tells us that every time we move 1 to the right, we're going to go 5 upwards. And so we keep going up by 5. We can plot the outline of the graph. And going to the left, the same thing. We'll just go down by 5 each time. You can put a straight line through. Make sure the straight line goes all the way to the end in both directions. And label it. Now let's have a look at our second line. Y is less than negative 2x plus 8. The plus 8 tells us that our y-intercept is at 8. And the negative 2x tells us that each time we go 1 to the right, we're going 2 down. And again, we can lay the course of the line by going down by 2 each time, and in the other direction, going the opposite way and going up by 2 each time. So again, we can draw a line, and we want to draw the line all the way through. And then we look at our last one. X is greater than 0. There's no y in this. This means it's going to be a straight line. There's only one variable. And x is greater than 0. It's going to go through the x-axis. And actually what I wanted for this is greater than or equal to 0. Now what's the difference if it's got an equal sign in? So first let's clean up the lines a little bit, get rid of the dots. So normally you have a dotted line if it's less than or more than. I'm just going to have a thin line for those. And if it's more than or equal to, you're going to have a thicker line. Now what this means is that we are allowed values on the line if it's equal to. But if it's just greater than or less than, you're not allowed values that are actually directly on the line. Now, what is the point of this? Well, we're going to highlight an area on the graph. So with y is less than 5x minus 6, we're going to highlight the area underneath that line. So this area is going to be highlighted. And we could colour in the whole thing. Then for the y is less than negative 2x plus 8, that's also a less than, so we're going to colour in below the line. And the x is greater than or equal to 0. It's greater than, we're going to colour in above the line. Now, there's multiple areas on this graph. So we've got at the top here, I'm going to label with 1. We've got the sides 2 and 3. The bottom 4, we've got 5 and 6 at the other side. Now, we've got 7 in the middle as well. Now, what you'll find is only 1 of these 7 sections is shaded in by all 3 lines. So, for example, area number 1, you can see the shading for the 2 lines either side is pointing away from it. The one that's pointing towards it is the x is greater than or 0. So we're not looking at 1. For 2, while it's shaded in by the line next, the 2 lines in between it, the other line over the side at negative 2x plus 8, the opposite side shaded. So we're not looking at 2. 3, 4, and 5 are all below x, we want greater than x. And we're talking about the x-axis there. So actually the equation for that is going to be y is greater than or equal to 0. If we want our line along the x-axis, because it's actually the y values that are more than 0. Now, with 6, again, the 2 lines at either side of it are pointing towards it, but y is less than 5x minus 6 is pointing away. Well, what about the centre? Well, with the centre, all 3 parts are pointing towards it. So it's above the x-axis, so that part's shading it in. It's below the y is less than 5x minus 6, and it's below the y is negative 2x plus 8. So you find the part of the graph that everything kind of points towards. Let's rub off the rest of the shading to make that really, really clear. So the shaded section is our answer. If you're only allowed integer values, so you're only allowed whole number values, what are the possible answers that we're allowed? What are the possible coordinates that we're allowed to have? And so I'm just going to try and pick them out in pink here. So we can have coordinates that are on the x-axis. We can't have coordinates that are on any of the 2 lines. We can have any kind of whole number coordinates that are inside. So I'm just looking for kind of grid lines that cross over. And it looks like we've got 5 positions that are whole numbers and are inside the green shaded area that are allowed on y is more than or equal to 0, but they're not allowed on the other 2 because they're not equal to. So what are those coordinates? So we can have the bottom left coordinate, that's 2 across and 0 up. The one next to it is 3 across. Then we've got the 2 above it, so that's going to increase the y coordinate by 1. So 2, 1, and 3, 1. And then we've got the one on the left-hand side that's 1 above that. So that would be 2, 2. Would it be 2, 2? Yes, it would be 2, 2. So then we can find whole number values in the middle. And then at the end, you're going to have to bring this back to your practical context. So x and y are going to have kind of practical values, and you'll only be allowed x and y to be in the combination shown in the brackets. So x could be 2 and y could be 2, or x could be 3 and y could be 1. But you can't have any values that are outside those 5 options. With truth tables, you get combinations of different events, and if they happen or if they don't happen. So in our first table, we have event P and event Q. We have every combination of them happening or not happening. Now, the way we do this is we write the true versions of the first activity, so the probabilities of P being true. And then for Q, we kind of alternate between true and false. And so what this does, it gives this kind of pattern where you have the first event has all the trues and all the falses, and the second event, it alternates. Now, there's a few things we can do with this. So we can say we can have P not happening, which would be P dash, and that's really the opposite of column P. So if P is true, P dash will be false, and if P is false, P dash will be true. We do the same thing with Q and have Q dash. So if Q is true, Q dash will be false, and if P is false, Q dash will be true. We can also make logic statements like P and Q. And what this does is it tells us if both of them are true. Both have to be true for an AND. So for the first row, we've got true and true, so that's true. The next row, we've got true and false, they're not both true, so that's false. The third row is false and true, they're not both true, so it's false. And the final row is false and false, so that'll be false. So we make an AND statement. Again, it's really important that you need all of them to be true. And there's only one row where they're both true. It's the top row. We can also do an OR statement, so P or Q. Now where AND, all of them has to be true. For P or Q, one has to be true. So the top row, true and true. Well, at least one has to be true, so we can write true. Second row, true and false. We have a true, so we write true. Third row, false and true. We have true because we have one true. And the last row is false and false. We don't have at least one true, so we write false. So this is the kind of logic we can start to build. And you can even join these together. So you could say P dash and Q. And what you want for P dash and Q is P dash being true and Q being true. Now we look at P dash, it's the last two that are true. And we look at Q, the third one from the bottom is true. So it's going to give us false, false, true, and false. Because it's only the third row where P dash is true and also Q is true. Now, as you can see with our second truth table, we can also have 3 variables. Now, the pattern with 3 variables, you take your first variable and you say, okay, that's going to be true. But once you've got all your true values, then you have your false values. For your second variable, you have a pattern of 2 true, 2 false, 2 true, 2 false. And then for your third variable, you alternate between true and false. True, false, true, false, true, false, true, and then false. Now, just like the previous one, we can have not P and not Q and not R, which are just going to be the opposites. And I'm not going to write that out because it's going to be fairly simple. We can also do things like having P and Q and R, and so we can have variables that take all 3 into account. So let's try that. Now, which one do we have all 3 being true? Well, we can see with the blue highlighting, the one at the top is the only one where all 3 are true. And again, if it's an and, all of them have to be true. So the top one will be true, and the rest are going to be false. We can also have the or statement. We can have P or Q or R. And you can see for all of these, every single row has got at least one being true. So we can write true all the way down, except the last row doesn't have a true, so we have to write false for that. Now, you can have more complicated combinations of statements, but the 3 we're looking at here are the main ones to think about. So you got the not with a dash, which means the opposite. So you just flip true and false around. You have and, which means that every variable has to be true. You've got or, where only one variable has to be true. Any other combination, you can figure it out from those kind of base logic facts. With critical path analysis, you'll first start off with a table. And a table is going to have a column for your task, and then a column for what the task depends on. Now, these tasks can be any kind of number of industrial processes. And if you think about perhaps making a car, you can't just do all the tasks in making a car in a random order. For example, when you want to fit the windshield in, you already need the body of the car done. So there's somewhere to put the windshield, to put the window. If you want to fit on the tyres, then you need the rubber of the tyres done, you need the hubcaps done, you need the actual structure of the tyre, you need the axles the tyres fit onto. So there's an order in which tasks have to happen. Tasks can be given letters, so let's call them A, B, C, D, E, F, G, H, I, J, and K. So there's going to be quite a few tasks in this diagram. Now, how do we construct this? So some tasks are not going to depend on anything. So we're going to have A, B, and C don't depend on anything. They're going to be the kind of tasks that we do first. So in your diagram, you're going to have a starting point, and from the start, we can have A, B, and C come out. Then we have what we call a node. So it's just a kind of point where we've finished that task. Task D depends on task A. And so it's going to come out from the node after task A. You can't start task D before you're done to task A. Task E and F are both going to depend on task B. We're going to put 2 arrows coming out of task B. Task G depends on task C. Task H depends on task E. Task I depends on task D and task H. So what I'm going to have to do here, let's redraw task H and have H and D pointing to the same place. Task J depends on task E, and task K depends on task F and G. Now, what I want to do at the end is have all the arrows pointing into the same place. So we can put task I and task K joining into a node at the end, which we'll call the end node. And so we build up the diagram like this. And it can be quite tricky to draw, to be honest, but with a bit of trial and error, especially because you don't know where the arrows need to point at the start. So that I kind of changed the direction of a few of them as I went through the diagram. Now let's have a look at an accurate version of this diagram. Now we have spaces on this to write values, and we also have some distances for each task, or lengths for each task. So we could say that all these numbers perhaps are the number of hours or days to solve each task. What we're going to do is find the critical path. We're going to find how long it's going to take to finish all of these tasks. Now, we always start with 0, and we just go down each path in the diagram. So let's say we go down path A. Path A takes, we'll go with hours for this. So path A takes 2 hours. Then we can go down path D. Path D takes 8 hours. So 8 hours on top of the previous 2 hours will take us to 10 hours. And then we could go down path I. This takes 10 hours, so we could get to the end in 20 hours. But that's only doing that set of tasks. We haven't taken into account all of the other tasks. Now, if you have a quick look at B, E, and J, that's going to be about 34 hours. So actually can't end on 20. So what you want to do with this is you don't want to kind of rush all the way to the end. You want to work from the left to the right because your first goal isn't going to get you the correct value. So let's look at B next. B takes 9 hours, and then C takes 5 hours. So now we'll have a look at task D, which takes 8 hours. 2 plus 8 takes us to 10. Let's look at task E. That takes 10 hours. So 9 plus the 10 is 19. Could look at G. G takes 7 hours. 5 plus 7 is 12. And then let's have a look at task F. F takes 2 hours. So 9 plus 2 gives us 11. And so we have two values now for this node. Is it going to be 11 or 12? And what you do is you go for the highest one, the latest time. Because if you're 11 in there, at 11 hours, you haven't finished task G yet. Task G's got 1 more hour to go. So you can't continue on with say, well, we can do task K now after 11 hours, because it depends on G and we haven't finished G. So we have to go for the highest value. Next, let's look at H. Now, H takes 11 hours. So 19 plus 11 is 30. And you notice we already have a 10 in that box. Now, we can't go ahead with task I after finishing task D and get 20 hours at the end, because I also depends on task H. And so we have to wait for H to finish as well. So we've got to wait until 30 hours have passed before we start task I. So again, you put in the highest number. So now we can look at task I. That takes 10 hours. 30 plus 10 is 40. We can look at task K. 12 plus 14 is 26. Well, that's not as big as 40, so we'll leave 40. And task J takes 15. 19 plus 15 is less than 40. And so we finished our diagram and we found the length of the critical path. It's 40 hours. So we know that when we start all these tasks, we would have finished all of them by the time we get to 40 hours. Now, we've worked forwards through the diagram, but you can also work backwards through the diagram. So we know that we have to finish all the tasks at 40 hours. But then we could do things like we can take the 40 and we go backwards down path K. And path K is 14. And 40, take away 14, is going to give us 26. Now, why have we done this? Well, what that node now tells us is that we can finish task F and G 12 hours after the project started. And what we could do is then do task K straight away, and task K will be finished after 28 hours. But then you're waiting around a while for all the rest of the tasks to finish. So what the 26 means is that task F and G could finish up to 26 hours. So they could be a little bit late. And you could start task K at 26 hours. It'll be done in time for the 40 hours. So it gives you a range of time in which task K can start and task F and G can end. And you're just going to do that with every single path. So we can go backwards down path J. That's 15. 40 take away 15 is going to give us 25. So we know we've got a range of 6 hours for task J to start. It can start at 19 hours or it could start all the way up to 25 hours. With I, we take away the 10, we get 30, and we've got the same number in both. So task I has to start at 30 hours. It can't start before it, and it can't start after it. This is going to be important in a moment. So then we can go backwards through task H. Now, task H is 30, we take away 10, and that gives us 19. Now, we've already written 25 in the box, so is it going to be 19, or is it going to be 25? When we're working forwards, you choose the highest number, but when we're working backwards, we're going to choose the lowest number, because if we finish task E at 25 hours, and then we start task H, it's not going to be done in time. So we need to write the 19 in there. Always go for the smallest value when you're working backwards, largest value when you're working forwards. Task E has to finish at 19 hours. Now, task J can still start at 25 hours. That's absolutely fine. But the 19 is representing that task E absolutely has to be finished by 19. So this is more about the task before than the task after. Let's look at path D. Let's take away 8. 30 take away 8 is 22. We can do path E. 19 take away 10 is 10. We can look at path F. 26 take away 2 is 24. Now that's larger, so we'll keep the biggest number there. We can go to task G, which is 7. So 26 take away 7 gives us 19. And then we've got 3 options for our last one. Now, we could do 22 take away 2 is 20, or 19 take away 5 is 14, but one of them will always end up giving you 0. Now, an important thing here is the numbers which are the same, and this is what we call the critical path. The critical path goes down B, it goes down E, it goes down H, then it goes down I. And what the critical path is a path through all the tasks where there is no options, no wiggle room. You can't start any of these tasks early or late. These tasks have to happen at exactly these times shown. The other tasks could start a little bit earlier or later. So task A could be finished after 2 hours, or you could wait with task A and then you could start it at 20 hours and finish it at 22 hours. There's a lot of options with task A, but with a critical path, we have no options. The critical path is from B to E to H to I. It's also possible to have more than one critical path. So if you do have any kind of tiebreakers for your critical path, just write down all of the options. The last thing to look at is a Gantt chart, which is another way of showing the information in this diagram. Now you start your Gantt chart off with your critical path. So our critical path was doing task B, and task B should have a kind of a width of 9. So you will be given some kind of grid to draw these onto, so you can write to scale. Then we're going to have task E happening right after, slightly bigger than B because it's 10 rather than 9. Then we'd have task H, a little bit bigger again. And then finally, we'll have task J, which is a little bit smaller. So again, make sure that these are drawn to scale. Now, once we've got the tasks in the critical path, we need to fit in the rest of the tasks. So let's look at A first. Now, A could start at 0 and it can end at 2. And so we'll draw it as if it's at the kind of the earliest time possible. It's going to have a width of 2 because that's how long it takes. But then what we do with A is we extend the box to its possible ending time. And A could end at 22. And 22 is going to be around about up here. And what we do with the extended part is we have a kind of dashed line around it. So we're showing all the possible kind of time slots A could fit in. It could be right at the start, or it could slide along to the end of that box. D starts after A and it lasts for 8 hours. So again, try and draw it to scale. And then D could start once A has finished, and D needs to be finished by 30 hours. So it needs to be finished by the end of H. So we've shown that it starts after A, and then we can show that it ends. It can end at the same time as H. And so now we can see the kind of block of options for D. We can do the same thing with C and G. So C can start at 0, but C could also start at 14. C just needs to finish by 19. So with C, again, we need to draw C itself to scale, but then the box after it, which shows its range of values, can't go on for longer. So we go all the way up to 19 with this, which is the same as the end of E. G starts after C, or it can start after C, you could have a gap, but the earliest time for it is after C, and it's got a width of 7. Now, G can end at 12, but it could end as late as 26, which is going to be around about here. And again, you should have an accurate grid for this so you can draw it perfectly to scale. So let's look really carefully at what we've not done yet. So we've done G. Let's have a look at F. Now, F has to start after B, or it could start after B. It's got a width of 2. So we find B, and we can start F right after. And then, so it can start at 9 and last to 11, but it could finish at 26. That means that F could actually start at 24. It's got to be done by 26. And so since F and G both depend on K, which is the next one, they're both going to end at the same time potentially. So now looking at K, K has to start once F and G are finished. And it's got a length of 14. But K could start all the way up to 26 after. And so the possible end times for K go all the way to the end. It's got to line up with I. There's one more we've not done, which is J. So J depends on E. So it's got to start, or it could start after E, and it lasts 15. This is the longest task actually, but it can finish all the way up to 40. And so we've got our Gantt chart. So what this does is gives a little visual of, where different tasks could go. So if you're trying to assign employees to do these tasks, you can kind of visualize who could do what. So, for example, the same employee could do A, D, then K, because you can see that K starts after D. So they could do A and D where they are and K where it is without sliding anything around. What you could do though is you could maybe move K a little bit later, give the employee a break, so you've got a few options. Then C, G, and F can all be done at the same time. You just need to move F forwards a little bit, and you've got still room to fit in J. So you might be asked, how many employees do you need to do this? And the answer is probably going to be 3. One employee to do the critical path. One employee can do A, then D, then K. And then another employee can do C, G, F, and J. And even though G and F do overlap, you've got that option to move F a little bit further forward. And you can see a gap in between G and J where F could fit. So it's a nice way to visualize how to allocate people to the tasks. And I think to finish off, we'll just highlight where the 3 people will go. So you have one employee does the critical path, one employee does A, then they do D, and then they can do K. And there's a lot of room there to move things, forwards or backwards. And then one employee could do C, then G. They can do F if you move it forward, and then they can do J.